So welcome students. So in this series what we are going to do is that we are going to go through everything that we require in geometry for IOQM, starting with very elementary notions of geometry and then going right up to the point from where so that you are able to grasp enough knowledge about the subject so that you are able to solve the questions that are ultimately asked. So this is a series that is meant for even students of 8th, 9th, 10th, provided I would request all of you who are sincerely pursuing it to go through your standard class text, standard text of your class so that you are not unfamiliar with the terminology that we are going to use. So first and foremost we must understand that what we read is Euclidean geometry. Okay. And all of you must have gone through Euclid's axioms and postulates. So I am okay. You must necessarily understand what an axiom or a postulate means. Axioms are facts that we take for granted, that we assume are true. We don't need to justify it. For example, one of the postulates is that there is only one line joining 2 points. So we just accept it as a fact. If you take 2 lines, we don't give a mathematical justification for it. We assume it to be true. Or from a line, from a point we can draw infinite lines. There are some very elementary notions that we take for granted. I hope all of you go through these, okay? They are inherent and intrinsic in understanding what geometry is. Or when you make any mathematical, when we enter into any mathematical field, you will tend to understand what this means, okay? So please have an idea of what axioms and postulates are. Theorems always require proof, where we use axioms which we have already taken for granted, and then we apply it. Okay, so we must have a notion of theorems, what theorems mean. Then we have corollaries. Okay, so corollaries means something which can be established easily from the theorem. Theorems we prove theorem. Whatever theorems we use, we prove them. Corollaries are the key deduced from theorems. So to say, theorems are deduced from axioms. And then we deduce corollaries from it. So again, a very basic framework of any mathematical study, not only geometry. We must have the notion of what a point is, what a line is, what a plane is, okay. And we are only going to read planar geometry. Everything that we stick to lies in a plane, okay. So please be aware of those. What does two parallel line means? Okay, in Euclidean geometry, two parallel lines, these are two parallel lines, they will not meet. Okay, perpendicular lines, I hope you understand what does it mean. 90 degrees. This is called a transversal, a line intersecting other lines. This is called a transversal. These angles, you must be aware what they are. They are called vertically opposite angles. Okay. So this is say angle, this is some angle, say angle 1. This is angle 2. So you must know angle 1 is angle 2. They are called alternate interior angles. They are corresponding angles. Sorry, angle 3 plus angle 4 is 180 degrees. This is a right angle 90 degrees, 90 degrees. Less than 90 degrees acute angle, greater than 90 degrees obtuse angle. Very, very simple information I am providing, but just that we have to use it on and off continuously. So all of you must be aware of it. That is my sincere request that please go through basic texts so that you are able to understand and learn as we proceed in this series. Okay. This is again two parallel lines, L1, L2. L1 is parallel to L2. So for brevity we write it like this. L1 is parallel to L2. See, if these two lines are perpendicular, say L1, L2, for brevity say L1 is perpendicular to L2. Okay. This angle is 180 degree. Okay. Now angle 1, this is angle 2. Angle 1 and angle 2 are called supplementary angles. For right angles we can say angle 1 and angle 2 are called complementary. To each other. The moment we say one angle is supplementary to other, that means if one angle is x, other is 180 degree minus x. The moment we say one angle is complementary to other, we mean to say that if one angle is x, the other angle is 90 degree minus x. Okay. So these are very, very basic information. I am conveying it, lot of you, I believe all of you must be aware of it, but still we will be using it continuously in our discussion. So just whatever I am able to recall, okay, so that we get into the real things. Before that, we must be very, very, you must not only know it, you must be very fluent in all this. Okay. We must be very, very fluent. Suppose angle 1 plus angle 2 here is 90 degree. Here angle 1 plus angle 2 is 180 degree. Fine. Supplementary angles, their sum is 180 degree. Complementary angle, their sum is 180 degree, 90 degree, sorry. Okay. Moving ahead now, we generally talk of triangles. Triangles play a very important part. So triangle is polygon having 3 sides. Okay, this is the triangle. Okay, we denote its vertices by say ABC, and the sum of angles of a triangle is 180 degree. I hope you are able to prove it. What you do is you draw a line parallel to it. These two angles are equal. We just saw. See, these two angles are equal. So therefore, since these two are parallel lines, okay, they are alternate angles, alternate interior angles. Now this angle is equal to this angle. Again, because these two are parallel, and we just said that these two angles are going to be equal. Okay, so these two angles are going to be equal. Just look at it like this, suppose. Okay, just don't look at the third side. So, and similarly for here, you can say that you don't draw this line, these two angles are equal. So again, the key, this is angle A, this is angle A, this is angle B, this is angle B, and this is angle C. So angle A plus angle B, sum of sides of a triangle is 180 degree. Very, very useful thing. Again, further for a triangle, what we can say is that in a triangle, what is another important fact that we must keep in mind is that, sorry, so here angle C is greater than angle B in the diagrams. What we are saying is that this would imply side opposite to angle C is AB, AB is greater than AC. Okay, prove it, please prove it. Okay, prove it. I am just writing it down. Okay, and I would expect that you comment some of the things that I have directly used. If you feel that we need a proof for it, then please come forward so that we are able to further emphasize that what are the important points, further enlighten you. So I am just giving to you this is an exercise, that the side opposite to is larger. Fine. We use this fact to sides opposite to larger side of a triangle is larger, to prove that sum of any two sides of a triangle inequality, sum of any two sides is greater than third side. Again, see, suppose this is a triangle. Okay, so what we do is that we have to show that, suppose we have to show that sum of any two sides is greater than the third side. So what we do is that we extend, see, we extend BA so that AC is equal to AD, and we draw this triangle. Okay, so this angle is theta, sides opposite to equal angles are equal. These two are again the isosceles triangle. I hope you know what an isosceles triangle is. And then you can say BD what is it equal to? BA plus AD. What is BA plus AD? BA plus AC. Okay. Now you look at it very carefully. This is an additional angle. So what we can say is that in triangle BDC, angle BCD, this is how we write it, BCD is greater than angle BDC. What is BCD? This angle. So side BD will be greater than angle BDC. BDC opposite side is BC is greater than BC. So we have BC is less than BD, which is BA plus AC. Okay, we could have done it with any other thing. So what we generally do is that opposite to angle A, we write the side as A. We denote it by small a. Opposite to angle B, we say it is B, we say C. So we have BC. A we have just established, and similarly we have B sum of any two sides is greater than the third side, and further we can say, second we can say of any two sides is less than third side. Are you able to see? See, B is greater than C minus A. Sorry, A minus you can write from the given, or C minus A you also can write. Okay, A minus C or C minus, whatever you like. B is greater than A minus C, B is also greater than C minus C. C is greater than A minus B, C is greater than B minus C. Whatever is the difference, generally we take positive, whatever, either A minus B is positive or B minus A is positive. So these two things are very, 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 very helpful. Please have them on your tips. Suppose you are given that side, just suppose you are asked a question, How many triangles are there? Suppose somebody says, how many triangles are there? How many different triangles are there? Whose sides are integers? And perimeter is say 8. Okay, perimeter is 8. So how many triangles would be there? So what we will do is that we will start with smaller triangles. So suppose smaller triangles means some sides being lesser. So what you can very easily see is that suppose I take perimeter to be perimeter is 8. So smallest side I can say 1. And I take one of the sides to be 2. Or let us start with the smaller one. 1, 1. What can third side be? 6. So is it forming a triangle? Sum of any two sides must be greater than the third side. So 1 plus 1, 2. It is not forming a triangle. Okay, it is not forming a triangle. Similarly, if I say 1, so the remaining is 7. So the next I have to take at least, say 1, 3, 4. This is also not forming a triangle. So if I take one side to be 1 and say 4, 1, 2, 5. Again, this is not a triangle. Further, I am only writing sides in increasing order. So this is not possible. 1, 2, 5, 1, 3, 4. So you are not getting any triangle. Okay. So none of the sides can be 1. Now if you start with 2, can we have a side 2, 2, 4. 2 plus 2 is 4. 2, 3, 3. This is the triangle. This is one triangle. What other triangle can we get? 2, 3, 3. Apart from 2, 3, 3, what is the triangle that you are able to fathom? See, 2 plus 3 is greater than 3. 3 plus 3 is greater than 2. So you can very easily see this is the triangle that we are getting. Any other triangle? Because the side is 8, we cannot take any side to be 4. We could have also ruled out them from this rationale also. The only triangle we are getting is the side with sides 2, 3, 3. You can say 3, 2, 3, but then they are effectively the same triangle. Okay. So if the perimeter is 8, and the triangle has sides integers, then the only possible triangle is triangle whose sides are 2, 3 and 3. Okay. Now, okay. Now one more question. See, I think I just thought of it. And one side of a triangle with integer sides is 1. Show that its perimeter is always an odd integer. Can you think of a triangle with side 1? So let us say, let the other sides so B is C greater than equal to C, or cell. Okay. So sides are B, C, 1. Okay. So B minus C, difference of any two sides. What we have seen, difference of any two sides is less than the third side. So B minus C is less than 1. And since B and C are integers with B minus C greater than equal to 0, this implies B is equal to C. Their difference has to be less than 1. So that means sides are B, B, 1. So perimeter is 2B plus 1. Okay. So we can say that they are always, this perimeter is always an odd number. What the other fact that we came to know is that if we have a triangle with integer sides and one of whose sides is 1, it will always be an isosceles triangle. Always be an isosceles triangle. Again, see how we are able to use it. Now, further for acute obtuse angle triangles, what we can say is that acute angle triangle assuming C. So, for acute angle triangle we have A square plus B square is less than, sorry, right angle triangle, everybody knows the Pythagoras theorem. And obtuse angle triangle. Okay, just see. Again, I am giving you an exercise. If you know this proof, okay, we must know them also. Obtuse angle triangle, you can understand one of the angles is greater than 90 degree. Here, all the angles are less than 90 degrees. Fine. So, it is my request, and then in your comments, please do tell us if you are not able to prove it, then we will do so in our next engagement. In our next class, we will definitely prove them based on the queries that are raised. Okay. So, sometimes you are asked about this also. So, insofar as the questions in the examinations are concerned, even though we are in our very first lecture, some very basic notions are asked. So, please be aware of this. Again, this is very relevant and useful when we solve problems. Sum of any, again, very normal notions. All of you must be aware of all this, but again they play a significant part in solving problems that are asked in any competition, or you wish to learn and understand geometry. These things are important. Now, suppose somebody says, on this somebody asks a questions, find perimeter of a triangle whose sides are consecutive integers. And the triangle is first right angle. Okay. So, what we are looking for is a right angle triangle whose sides are consecutive integers. Say n, largest side would be the hypotenuse. So, if it is a right angle triangle, n square is n plus 2 whole square. Okay. Now, I am sure lot of you would have gone through a triangle like this. 3, 4, 5 is the obvious thing that people come up with. 2n square plus 2n plus 1. So, you have so n is equal to 3. So, perimeter is 3 plus 4 plus 5, which is 12. Somebody may ask area, but purpose is that again this is a very simple triangle. I am sure all of you would have gone through this. 3, 4, 5 is considered a Pythagorean triplet, a very standard Pythagorean triplet, and it is expected that we are able to use it directly as and when required. So, this much amount of work is generally not done when we are asked about right angle triangle whose sides are 3 consecutive natural numbers. Then we directly write that the triangle, concerned triangle is the triangle whose sides are 3, 4, 5. Now, suppose somebody says is an obtuse angle triangle. So, again sides are n, n plus 1, n plus 2. We want it to be an obtuse angle triangle. So, what is the condition that we will apply? A square plus b square is less than c square. That is okay. So, what do you get? So, you have n square so this is always positive. So, n minus 3 is less than 0, that is n is less than 3. Now, if n is less than 3, what can it be? 1 or 2. But with 1 we have already seen it has to be an isosceles triangle. So 1, you can also see that the sides are 1, 2, 3, which is not forming a triangle. Also we have seen that if a triangle with integer sides has one of its sides as 1, then it has to be an isosceles triangle, and we are taking all the 3 sides to be distinct, so n could not have been 1. If it is 2, the triangle is, so perimeter is 9. Okay. So this is the only triangle, you can see this is the only triangle whose sides are consecutive natural numbers and its perimeter is and it is an obtuse angle triangle. Barring, see, the moment we cross 2, 3, 4 is an obtuse angle triangle, 3, 4, 5 as we just got to know is or you were already aware of, is right angle triangle. Post that, any triangle with consecutive sides has to be an acute angle triangle. See, you can understand sum of consecutive squares. If you take 2 consecutive squares, as we move on to larger number, sum of 2 squares would definitely be, sum of 2 consecutive squares would definitely be exceeding the square of the number of the next number. So 6 square, 7 square, so their sum would definitely be exceeding 8 square. So as we move on, we can possibly fathom it. For a smaller number, this is the only triangle. Right angle triangle with consecutive sides is 3, 4, 5. So I am requesting you to please remember it. Okay. So again, based on some very elementary notions of sum of 2 sides, we have been able to come up with the rationale that the utility of simple notions like triangle inequality is very useful in dealing with problems that we come across. We will do practice of notions like this continuously, but I deliberately chose to come up to triangle inequality so that you come to know as to what are the sort of problems that we encounter. With a few very simple notions I have taken, very standard common notions. This is what we will come up with. Some very basic notion, some very elementary notions that we have gone through, and then what are the type of problems, what are the sort of situations that you handle, and the use of very simple, I would not say simple, very usual and commonplace theorems are used in solving problems, especially in examinations like Olympiad. A special care is taken that not some very arbitrary, not some very unknown facts are used in solving the problems. We have always come across situations where elementary notions are used in solving problems, especially in examinations like Olympiads. See, we have, in all the problems that we have gone through, we have simply used some elementary known facts in solving the problems. Okay. Now regarding triangles, let me also introduce you to the notion of congruency. Okay. Congruent figures you must all be aware of. If one figure can be superimposed upon other, then they are called congruent figures. So two triangles, for their congruency means they are one and the same, just as we said. These are one and the same triangle, that means they are congruent triangles. So the idea that would, rather than saying different triangles, the generally word uses non-congruent triangles. Okay. So congruency. So congruency, the types of congruency, what are the different conditions under which triangles are congruent. I hope you are aware of side, angle, side congruency. Okay. Angle, side, angle, 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 side, 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 and right hypotenuse side. Side angle side means you are dealing with two triangles. Sides and the included angles. Angle side angle would mean angle and the included side. Angle angle side would mean and a side opposite to any one of these angles. You could have taken this. Right hypotenuse side because one of the angle is given to be 90 degree. A lot of issues are sorted. Okay. Again, see angle side is not included here. Okay. So please keep in mind the order angle side angle. That means angle side angle, the two angles and the adjacent sides. Angle angle side angle side. Suppose these two sides are equal and suppose this angle is equal to say this angle, then we won't say that the triangles are congruent. So the ordering does play a role. Okay. Now, so if two triangles are congruent, one can be superimposed on the other. Now see from here if somebody says this is ABC, this is PQR, and then I say BC is equal to QR. So we write it as CPCT. What does it stand for? Corresponding parts. Corresponding parts of congruent triangles. Corresponding parts of congruent triangles. Or we say that this angle is equal to this angle, angle ABC is equal to angle PQR. So we simply write CPCT. Why? Because they are corresponding parts of two congruent triangles, hence they are equal. So the congruency is very much used in dealing with problems. Congruency, and as we move on we will also see similarity. They are very important notions to be used in dealing with questions related to triangles, because if here what happens is that all the angles, all the sides are equal. Side I deliberately didn't draw a picture because side you can see all three sides are same. That ends the debate. Okay. Now, how do we utilize a bit of it? Suppose I draw a triangle. Okay. A, B, C, and say I draw a line AD. I take a point D, which is the midpoint of BC, and draw AD. Suppose somebody says show that AB plus AC is greater than 2AD. Okay. Now let me tell you that this AD, this is called median of the triangle. What is the median? Line joining vertex to the midpoint of opposite edge. We will have three such medians, one drawn from B, one drawn from C. One is drawn from A, one is drawn from B, one is drawn from C. As we move on, we will see that these three medians meet at a point. And lot of theorems related to it. What are the ratios? This point is called centroid. So what is a centroid? We will take up later on also. Point of intersection. So to get to 2AD, what we do is that we extend this. So let me draw this figure in on a new page. What we do is that we extend AD such that to a point E, such that AD is equal to D. Upon extend AD to E such that now suppose I join this. Now look at it very carefully. See, this is medians, these two are equal. Vertically opposite angles are always equal. So, triangle BDA and triangle CDE are congruent by which of the following things? You can see side, angle, side. Okay, side, side, included angle, and then side by SAS. What we write here is generally we write triangle BDA to triangle CD. Okay, they are similar to each other, and again very simply we can see. So therefore we have by triangle inequality sorry not triangle inequality. So we have AB is equal to CE. What we will write here, just now we learned CP corresponding part of congruent triangles. Now we will say by triangle inequality, what we have is that AB plus C is greater than AE. So we have AB. What is CE equal to? AB. No, AB not. Sorry. AC. What is CE equal to? CE equal to AB. Just now we have is greater than AE. Okay. Now what we have is that AE and we just at the beginning said that we are extending AD in a manner such that AD is equal to DE. So effectively AE, what is AE? That is AD plus AD. So this is what we were supposed to prove. From this you can understand what we are going to write. AC plus AB is greater than 2 times AD. You can understand what we can write here from here if you further extend it. What is the corollary that you can draw from this? Suppose let me draw all the 3 medians. For the time being, assume that they are concurrent. So AB plus AC is greater than 2AD. Okay. CA to CE and BC you will get is greater than 2BE. Similarly, so you can very easily see that sum of the 3 sides of a triangle is greater than very elementary things. We will come up with better inequalities. This is a very raw inequality that we have come up with. Sum of any 3 sides of a triangle is greater than sum of the medians of the triangles. So it's simple triangle inequality and notions based on congruency. As we move on, we will focus more on congruency, idea of congruency and triangle inequality to deal with problems. So since this was our first lecture, I just wanted you to have a understanding, have a notion of how we are going to deal with these lectures. In the 12 lectures that we are going to have in this series of geometry, we will complete the geometry that is required to deal with the situations that we encounter in the examination of IOQM. Okay. So kids in 6th, 8th, 9th, 10th who are interested in appearing and excelling in examinations like this, I have been slow and I tried my best to be a bit docile, so that you are able to understand, you are able to fathom what the purpose of these lectures are. Some of the proofs I have left for you, and I'll come back, okay, and please comment, so that in next lecture if you ask, we'll tell the proofs of them. These two. The sides opposite to larger angle is larger. The notion of, okay, these notions I expect all of you to be aware of, and then as we move on, practice such things to learn the notions that we are going to go through in geometry. So, the basic idea of this lecture was that we are able to convey as to what we are going to do in the series, and please, and to make you aware, so that a bit of preparedness is needed if we want to perform well and excel in examinations of this nature. So, I would request all of you to be in constant touch with the text that you have been provided with in your school. Please be a bit faster in going through the chapter of geometry, especially the books of NCERT of 8th, 9th, 10th, so that you are aware of the notions that we come across. Students of 6th, 7th would know what corresponding angles, would know what vertically opposite angles means, what supplementary and complementary angles means, what parallel lines mean, Euclid axioms, Euclid postulates would probably you are made aware in class 9th. So, if you are students of these classes, please go through these texts, whatever have been introduced. If you want some more details, please comment, so that when we come to next lecture, if you find something amiss, we are able to provide it. This will be a very comprehensive and all including series. This is the first stage of our preparation. These lectures are meant for first stage of your preparation. So, specifically the sort of questions that we deal with would primarily be up to the level of IOQM. In the last lecture, we ended with triangle inequality. Prior to it, we had read things regarding lines, angles, alternate angles, vertically opposite angles, then in a triangle what a median is, then congruent triangles, then we ended the lecture with triangle inequality. We did some questions regarding it. Okay. So, moving ahead with triangle inequality, I hope you are now aware of the notation. If sides are A, B, C, generally denoted by small alphabets, vertices by capital alphabets. So, what did we read? That sum of any two sides is greater than the third side. This meant that difference of any two sides is less than the third side. We did some problems based on it. So, just recapitulating what we have gone through in the last lecture, this is just a recap. Okay. So, let us now first solve a problem which is based on triangle inequality. Then in this lecture we will read about similar triangles, and that will then we will move ahead to say Thales theorem or basic proportionality theorem, followed by, if the time so permits, then we will move to quadrilaterals also, but we will primarily stick to triangles. At the fag end of this lecture, we will might be moving to quadrilaterals. Okay. Now, in triangle inequality, we read this. Okay. We even proved it, and even I asked you to prove it. I hope you would have done it. It is very important that anything that you read for Olympiad examinations, without knowing the proof, if you are going ahead, it will generally be very, very difficult for you to elaborate it, to extend it to the questions that will be ultimately asked in the examination. So, a very, very, very sincere request to all of you, whatever theorems you are going through, please know the proofs of them also. Fine. Now, okay. So, in triangle inequality, let us solve a problem. If two altitudes, of a triangle are of length 4 and 9 units, find the sum of all possible integral lengths of third altitude. Fine. So what we can say is that you have a triangle, altitudes are perpendicular from the vertex to the opposite side. Okay, let us draw it to scale. 4, 9 is not feeling that you have 4 or 9. Okay, let us have sides. So let us say that, see, now let us say this altitude is say 4 and this is 9. Let the length of third altitude be h. Okay. Intersection point of these 3 altitudes. Okay. Intersection point of altitude is orthocenter. Fine. It is the name given. So, intersection point of medians is centroid, and then we will see also others also. Now, if these bases are say whatever the base is, this as A, B, C. So, how do you relate sides and altitudes? So, what we say is that area is half base into height. Area of triangle ABC is half A into H is half B into 4 is half C into 9. So, what we have is AH is 4B is 9C. Okay. Now, we will use triangle equality. I hope you are understanding is equal to say some lambda. So, now what we will do is that see B plus C is greater than A, B minus C is less than A. Okay. Now instead of B, what can we write? Lambda by 4. Instead of C, we can write lambda by 9. One becomes lambda by 4 A is lambda by H. Two becomes lambda by 4 okay. So this lambda is the common factor here and it is positive. So you have 13 by 36 and here you have 9 minus 4, 5 by 36. Okay. Hence what we have? We have H is less than 36 by 5 and greater than 36 by 13. Okay. So 36 by 13, that means if H is an integer, what can H be? So 36 by 12 is 3, so this is less than 3, so H can be 3, H can be 4, H can be 5, H can be 6, H can be 7. This is 7.2 and this is 2.8. So these are the possible integral values of H as H is an integer. So what is the sum? 25. Okay, sum of the all possible integral values of the third altitude is going to be 25 and the number of different values is going to be 5. And so you can see a problem simply based on sides of a triangle. Okay. Suppose I give you the three altitudes of a triangle. Is it possible to find area of the triangle? Just think about it. Suppose I say the altitudes are 4, 9 I have already taken, 4, 6, 9. Okay. Suppose I take this question. If altitudes of a triangle are 4, 6, 9, find its area. Just for curiosity, half base into height is the formula. So what you will have is that, let us say, let sides be A, B, C. So area generally denoted by delta will be, say, 2A is equal to 3B is equal to 9C by 2. Now let us keep it even only, so that calculation part is reduced. Now what will we do? We are not aware of ABC. So how to proceed here? What is the expressions that we have? So let us take this to be, for example, see we can take it to be lambda, but LCM of 4, 3, 2. What is LCM of 4, 3, 2? 12. So, this will be 12 lambda, okay. Hence, A is equal to 6 lambda, B is equal to 4 lambda and C is 3 lambda. Now, for area of a triangle, maybe I took this question bit early, but I hope you are aware of Heron's formula. This is Heron's formula. We would, I think I reached this point bit early. Some of you might be aware or lot of you might be aware of Heron's formula, but I think here it will be utilized. Area of triangle is this. S is A plus B plus C by 2, that is semi-perimeter. Fine. Now, what can we write? Area of triangle we wrote as 12 lambda. What is S? 12, 15 lambda by 2. So, this is 15 lambda by 2, 3 lambda by 2, 9 lambda by 2. Okay. So, what do we have? 1 by 4. This 9 will 3 comes outside. 3, 3. Another 3 comes outside. 5, 7. 3, 4. So, what do we get? Your lambda as 3 root 35 upon 60. Fine. So, therefore, area, what does this area becomes? 12 into 3 root 35 upon 60, that is 9 root 35 upon 4 square units. Okay. So, you can see the application. I hope all of you are aware of this expression. Okay, Heron's formula. So, this is how you would have calculated it. Fine. So, we solved a problem on triangle inequality where altitudes were given, and now just to extend, just it came to my mind that let us see how we can expand the notion. So, from the given data we calculated this. Now, the crux of today's lecture is similar triangles. As such, we have similar figures, not only triangles, where sides are proportional. Suppose you have a polygon of say 4 sides, you are talking about a rectangle in which length and breadth are in the ratio 1:2. You extend, say there is a rectangle So, sides are proportional. These are similar figures. Okay. Suppose this is an equilateral triangle. So, they are all similar figures. Things are proportional. Say everything has been say expanded or contracted by the same ratio. You expand or contract something by the same ratio. Suppose you take something into hand and then you squeeze it, press it. If the figure is not distorted and everything gets reduced or expanded proportionally, you have a balloon, okay. So, when you are inflating it, it on most occasions has a similar shape, a sphere you would say. So, if it is a sphere, whatever it might be radius, they are similar in nature. So, that there is some proportionality in some basic ingredients of that figure. So, similar triangles will have same angles and the sides are going to be proportional. Okay. Sorry, sides are going to be proportional. So, insofar as triangle is concerned, equiangular triangles are similar. It need A, B, C, P, Q, R. These angles are same. So, we say in similar triangle sides are proportional. AB by PQ is BC by QR is PR by AB BC QR, so AC by PR. Okay. These are proportional. As we can see, heights too are going to be proportional. Okay. You can see heights are two heights. Suppose we say altitudes, so altitudes are also going to be proportional. I say AD PS will also be equal to AD upon PS. These are also proportional. Now, area is half base into height. So, AB into AD and this will be PQ into PS. So, if this is area of triangle ABC upon area of triangle PQR. This will be AB upon PQ, square of this ratio, half AB into AD, half PQ into PS. Okay, altitudes are in the same ratio, medians will also be in the same ratio. If you draw angle bisectors, they will also be in the same ratio. Fine. So, this is very helpful. Lot of figures that we come across are generally similar. Okay. For example, suppose I give you a triangle, say sides are say 4, 5, 6 and another triangle, say 4, say 8, 10, 12. Okay. So if this a triangle has area delta 1, this area has triangle delta 2. So we can very safely say that delta 1 by delta 2 is 1 upon 2 whole square, that is 1 upon 4. Okay, similar triangles. Fine. Further, suppose I ask you a question like this. Sorry. Suppose we draw a diagram like this. Okay. A, B, C, D. So this is P. Okay. These two are parallel. So if we say if AP is to PC is 3:2 and area of triangle PDC is 16 square units. Find area of triangle PAB. So since these two are parallel, this angle is equal to this angle. We read in the last class, or you are already aware, this angle is equal to this angle, and therefore the third angle of the triangle, and therefore the two triangles are similar. So therefore triangle PAB is similar to triangle PCD. Okay. Hence, area of triangle PAB upon area of triangle PCD is equal to PA upon PC whole square, which here is given to you as 9/4. So, area of triangle PAB upon 16 is 9/4. So, area of triangle PAB becomes 9 4 ja 36. This becomes 36. Agreed? Now here also you must keep in mind, see, if this is delta 1 and this is delta 2. Okay. These two triangles have area root delta 1 delta 2. If this has area delta 1, these two triangles are of equal areas. Because you can see Can you see that these two triangles have area root delta 1, root delta 2? Are you able to see it? How do you go about it? See, they are triangles of equal areas, okay, not similar triangles. These two triangles are triangles of equal areas. Because say if this length is say 3 lambda, this is 2 lambda. If this is 3 alpha, this is 2 alpha. Okay. So, you can see that these, if you are not able to see, I am advising you to please prove it again. And again, keep on in our comments if you are able to write that these are the issues that are not yet resolved, then we will definitely prove it. So, giving this area, somebody could have asked the area of the whole figure. So, this is 16, and this is 36, okay. So, this is 24, 24. So, if area of this whole figure, if somebody asks what it is going to be, 48, 52. So, the number is 100, okay. So, area of this, as we will come across, we will say this figure is called a trapezium. So, area of this trapezium would be 100. Fine. So, because it is lambda alpha, so the areas are root delta. So, please keep this in mind, okay. This figure is called a trapezium, we will come across it as we move on, that these areas are root delta 1, delta 2, root delta 1, delta 2. Fine. Just have a look at it. By proportionality, are you able to observe or not? Another very important thing that is used is Thales theorem or basic proportionality theorem. You get lot of questions based on it. What we are saying that if we draw a line parallel to the base, then AD by BD is AE by EC. Okay. Also, AD by AB is AE by AC. See, these are parallel, so this angle is equal to this angle. So, they are similar triangles. Fine. Also, you can write this as AD now. BD by AB is CE by AB. Very, very, very useful thing. Okay. Fine. This is very, very useful. By similar triangles, we can directly see by simple proportionality. AD by AB. This you can see by similar triangles. Rest all I hope it is very easy to reduce. AD by AB is AE by AC. Okay. So from here you can say okay, AB by AD is AC by AD plus AB. AE. Okay. Now you simply subtract one AB minus AD will be BD and AC minus AE will be EC. Subtract one from both of them. Fine. Very important and useful thing. It is very often used, especially suppose somebody says its converse is also true. Converse we will see after going through parallelogram. Okay. How do we use it? A very simple question could be, so this length is 4, this is 8. If this is 3, what is this? What is this going to be? You can see 4 by 8 is 3 by this. This is 6. Fine. And from this basic proportionality theorems, converse. Okay, we will come to it. Converse we will see later. Okay, once we have gone through quadrilaterals and parallelograms. Okay. Now, here also somebody says, this was a very trivial question. Moving ahead, if somebody says, say question data is given like this. A, B, C, D, E, so this is F. So this length is 2, this length is 4, this length is 5, this length is 3. Suppose somebody says, find DF upon CF. Okay, so I have just given you the lengths. So what you do is that you have to find, see these lengths are known, they might be ratios, but let us say these are length itself. Okay. So what we do is that we try to use basic proportionality theorem by simply drawing a line which is parallel to AE. So this is G. We draw a line DG parallel to this. So you can see, okay, this triangle BDG and BAC, they are similar triangles. So by basic proportionality theorem is this is 2:1. This is BD by DA is 2:1. Okay, BD by DA is equal to BG by GC, which is 2. So BG is 2GC. So we have BG and BG plus GC is 8. So write BG as 2GC. Sorry, it is half BD by, sorry. So GC is 2BG. So BG is 8 by 3, 16 by 3. This length is now 8 by 3 and this length is 16 by 3. Okay. Now, think of these triangles, DGC and EFC. This is 3 and you can find this length, this total is 8, 16 by 3, this is 3. So, this is EG is 16 by 3 minus 3 is 7 by 3. Okay. So, DF by CF again by basic proportionality theorem. What is DF by CF? By basic proportionality theorem, you can say it is GE by EC. GE is 7 by 3, this is 7 by 9. So, DF by CF in the present scenario is going to be 7 by 9. Okay. Just look at it. First we applied basic proportionality theorem on triangles BCA, BGD, and then we applied basic proportionality theorem on triangle DGC, FEC by a simple construction. Its converse is also true, basic proportionality theorems converse. Okay. The converse of basic proportionality theorem that we will take up when that will be easily proved once we come to parallelogram, and therefore we are not deliberately touching it here. Converse would be, what will be the converse? That if a line divides the sides of a triangle in equal ratios, okay, two sides of a triangle in the same ratio, then the line is parallel to the third side. If a line is dividing two sides of a triangle in the same ratio, then it is parallel to the third side. Converse part we will take up as we move on. Okay. So, this was a good practice of the theorem that we have seen. Now, some important points about triangle would be, I think medians, we must know what a median is. Median. Okay, some of the proofs we will take up. I am just sharing the information. Medians is vertex to opposite side. Okay, you can draw the three medians, you can see. Sorry. They are all concurrent. Okay. And this intersection G is termed as centroid. AG is to GD is BG is to GE is CG is to CF is 2 upon 1, 2 is to 1. As of now, I am just writing this ratio. Okay, we will prove it once we see quadrilaterals and parallelogram. That will be easy to see. We are deliberately omitting two things: the converse, proof of converse of basic proportionality theorem, and these things. Okay, median, and then we have, this is called centroid. Now, altitudes, as we read, so altitudes are perpendicular from the vertices. This H is called orthocenter, and at least remember the name. Fine. Then we have angle bisectors. So, in angle bisectors, what you have is that okay. One very important property of angle bisector is that, suppose you are given angle and you are drawing its angle bisector. Now, if you take any point on the angle bisector, we say these two are equal. Why? Because see, this angle is equal to this angle, this is 90 degree, and this is the common side. So, RHS, by right hypotenuse side, these two triangles are congruent. So, perpendiculars from any point on the angle bisector to the two sides are equal in length. Okay. On the contrary, also, if we take suppose we say we draw perpendicular from Q to the angle bisector, then also QS is SR. Are you able to see? By again, this is common, this is 90, right hypotenuse side. So, we say image of Q in this angle bisector will be R, and a very, very, very important theorem, angle bisector theorem, is, suppose this is D, is AB by AC is BD by CD. Angle bisector divides the opposite side. What we write it as? Angle bisector divides the opposite sides in the ratio of sides containing the angle. So, how do we prove it? What we say is that what we say is that these two altitudes are equal in length because they are drawn from point on altitude. We just now showed it. Now I think it is very clear. Okay. The area of triangle ABD upon area of triangle ACD, half base into height. See, if we draw the altitude from vertex A, say E, so this will be half AB, half BD, okay, BD into AE upon half CD into AE. Okay, and you can also write this area as what will be the ratio? If you take AD as base, half base into height, so this is the H, this will also be H. Say in diagram it is not properly, see, unfortunately we were not able, I was not able to draw the diagram as properly as I should have. So this would be half AB into H so you can very easily see BD upon CD is AB upon AC. Very, very important theorem. So please remember these things regarding angle bisectors. Perpendicular from angle bisector on the two sides are equal in length. In a triangle, the angle bisector divides the opposite side in the ratio of sides containing the angle. Okay. Now, angle bisectors to meet at a point, sorry, and that point is equidistant from the three sides. Let me see. I is in center. Okay. I is equidistant from sides of the triangle. Okay. You can draw a circle whose center is I and it touches all the three sides. And this I is point of intersection of, very sorry. Okay. I is point of intersection of angle bisectors. So this is in center. Fine. Moving ahead, we also have perpendicular bisectors. That means lines which bisect the sides at right angles. And then okay, they meet at circumcenter. What is a perpendicular bisector? A line which is bisecting a segment at right angles. So any point on the angle on the perpendicular bisector is equidistant from the two ends of the segment. So this is equidistant from BC, CA and AB. So it will be equidistant from ABC. So circumcenter is equidistant from vertices. So if you have, so you can draw a circle centered at A and passing through ABC. Generally, we represent circumradius by capital R generally and in radius by small r. Okay. Generally, this is how we do it. So the notations regarding a triangle should be known to us. I have just given you the names and some very elementary properties. Some I have proved, some I didn't. I will insist to everyone, each one of our friends, each one of the students, that any theorem that we are going through, some I have deliberately asked you that we are skipping, we will do it once we have gone through parallelogram, but always keep this in mind that those proofs are to be done. If you want to solve problems, knowing proofs helps you in starting a problem. You know how basic theorems were deduced, how they came into being. That is a great help, in starting a problem. You can now think how will you initiate problems. So in that sense, it's a very, very good tool. So requesting each one of you to give special credence and special attention to proofs. We will take up some of the proofs. Some of the proofs I deliberately told you that I am omitting because of the constraint of time, and also I would like you to try it on your own. It is not that you have to do everything on your own. If you are able to conceive it, if you are able to solve it, it's a great thing. But even if you are able to see it, see the solution, try to understand it and then pen it down on your own, that is also a good enough beginning. Say a week past that, if you are able to recall things, so you have lot of information available. Are you able to pinpointedly use the information needed and for the given problem? That is the essence. So you will have lot of stored data. What is necessary is that at the appropriate juncture, the appropriate data comes to our mind, the appropriate theorems comes to our mind, seeing the situation. That is done at the first by being able to prove the fundamental theorems, and by definitely, as in mathematics, lot of practice. Lot of practice is generally good when you are giving normal examinations, but when you are looking for Olympiads and other competitive exams, I have a very my experience says that students falter at this juncture because they don't know the proofs of elementary theorems. They have simply remembered the results. Some proofs are asked prior to it, okay, not the result, a intermediate step of that proof, or you know how to begin in a problem. Beginning of a problem makes, because lot of information is available, we generally tend to have an issue at how to start. So starting problem is solved if you have done the proofs at least once, Some of you may remember, some you may not. It is like a problem, you have solved a lot of problems. After that, you are able to initiate problems, initiate the thoughts to solve the problem. That is the basic aim. So, any proof that you have not done, I will sincerely again request you to do it. If you feel that it is utilizing something that will take up later, once we have taken up, solve it. Okay, but please, if you are serious contestant for these Olympiad examinations, feel that it is necessary to go through this. So, in we have already covered things related to triangles, and in this lecture we will primarily covering topics of quadrilateral, the topic of quadrilateral. So, we have gone through similar triangles, we have gone through congruent triangles, we have gone through triangle inequalities, we have gone through Thales theorem, midpoint theorem, and things like that. Okay. Now, moving ahead, today's topic is quadrilaterals. Once we are through with quadrilateral followed by circles, then we will be covering up the variety of problems that is actually appearing in the, that will actually be appearing in the examination. Okay. Now, quadrilateral is a polygon of 4 sides. A quadrilateral can be of this shape or this shape. Okay, this is a convex quadrilateral. And this is a concave quadrilateral. Now, in convex quadrilateral, all the angles are less than 180 degree, and in a concave quadrilateral, see, this angle is greater than 180 degree. Some very elementary facts that you must understand is that the sum of angles of a quadrilateral is 180 degree. You can see you are getting this triangle and this triangle. So, first and foremost is sum of angles of a quadrilateral is 360 degrees. Even in the case of a concave quadrilateral, that will be the case. Fine. Now, we generally discuss convex quadrilaterals only. Most of the properties, most of the things that we come across, that we know, are things related to convex quadrilateral. Unless specified, we treat quadrilaterals as convex quadrilaterals. Even though it is expected that it is always explicitly told which is the quadrilateral that we are dealing with, but invariably a conventional way is to deal a quadrilateral as a convex quadrilateral. Okay. Now, what are some of the quadrilaterals that you go through? So, a very important quadrilateral is trapezium. Okay. So, what you say in a trapezium, one pair of opposite sides, okay, one pair of opposite sides are parallel. Okay, one pair of opposite sides are parallel. Now, what you can possibly say is that in a trapezium, see, as a consequence of it, what do you get? See, these two angles are equal. this angle is equal to this angle, and therefore this angle has to be equal. So if this is P, intersection point of what we say, the line joining the alternate vertices, we call them diagonals. These two triangles are similar. So one of the things is that diagonals divide each other in same ratio. Okay, in a trapezium. And it is also the other way around. If diagonals divide each other in the same ratio, then the trapezium is a, then the quadrilateral is a trapezium. Further, we say that area, if this triangle has area delta 1 and this is delta 2, then delta 1 is equal to delta 2. And we did it last time, if you remember, this is root of delta 3 delta 4. So please have this in mind. In last class, if you remember, if you see the video of last class, we explicitly used it. Further, moving ahead, in a trapezium, if we have the line joining the midpoints of non-parallel sides, EF. Okay, so EF is called median of this trapezium. EF is midpoint of this trapezium. Further, EF is parallel to parallel sides and EF is half their sum. It is parallel to the parallel sides and equals half their sum. These three are these are parallel sides of a trapezium, and this would be parallel to it. Okay. Now, further you can also add here if suppose this is G and this is H. Okay. So GH is AB this will also be the midpoint. Okay, once we come to parallelogram, we will be proving. This is basically the converse of Thales theorem, midpoint theorem. The converse of midpoint theorem is giving this. You can see from this point you are drawing a line parallel to this, so it will be bisecting AC also, it will bisecting AB also. Okay. And insofar as length is concerned, you can say this is half and this is also half of AB. This is half of AB, this is half of AC. So what is this? Half of this minus this, from converse of midpoint theorem or basic proportionality theorem or Thales theorem. Okay. So these are the facts that we need to know about trapezium. Okay. We have gone through areas too. So moving ahead now, say somebody says, Suppose I give you something related to trapezium. A question, let us solve a question regarding trapezium. Okay. Suppose this length is L, this length is M. Suppose we extend it and they meet at some point. Now from here we draw a line parallel to the parallel sides. So let us name it A, B, C, D, E, F. So if L is 10, let me give you, or let us be in terms of expression only. Find EF in terms of L and M. So I have deliberately omitted the language part. The language would have been ABCD is a trapezium. The non-parallel sides are further extended to meet at a point P. From P, a line is drawn parallel to the parallel sides. The diagonals are extended to meet this line drawn, this parallel line drawn at E and F. Find the length EF. So that language part I have drawn the diagram right in front of you so as to save some time. Now, so much parallelism is involved, you can possibly think of it as question where a lot of angles are going to be equal since we are dealing with parallel lines. So a similar triangle notion can be used. This is a triangle. These two triangles are similar. You can see. And of course, if this L and M are known, okay, we can find the proportionality part here also, isn't it? So what should we do? Suppose this length is X. So what can we say? PC. This is PC. This is opposite to this angle upon BC. Okay, is equal to PC. Opposite to this angle is X upon L. PC upon BC. Now, can we find the ratio PC upon BC? Because these two triangles are similar. So, what will PC by BC be? You can say PC by PB is M upon L. Now, PB is PC plus BC. Is M upon L. Fine. So, you can say BC upon PC plus 1 to BC upon PC PC upon BC is so you can write X as LM upon L minus M. And very simply you can say this is going to be the same here also. So this is also going to be LM upon L minus M. I hope you are able to fathom this. These two triangles are going to be similar and the same ratios are going to come. So EF is nothing but, what is EF? Two LM upon L minus M. This is the length EF. So we could have done it earlier also using similar triangles only, but to use the terminology of trapezium, we deliberately are doing it here only. Okay. Now, suppose somebody says in a trapezium, in a trapezium, this ratio is 2:3. Diagonals are dividing in the ratio 2:3. And this has area 16. Find area of trapezium this triangle has area 16. So this is again 2:3. Diagonals are dividing each other in the same ratio. This is a trapezium. So we can very easily understand how these ratios are going to be. This area is going to be in the squares of ratios of sides because the triangles are similar. So if this is delta upon 16 is, so delta is 36. This is 36. And what is this area we have read? Root of delta 1, delta 2. 4 into 6, 24. What is this area? 24. So the total area of this trapezium is 52 and 48, that is 100 square units. Okay. Moving ahead, we have a parallelogram. What do you have in a parallelogram? Both pair of sides are parallel. Special case of trapezium. Both pair of sides are parallel. Okay. Further, the opposite sides are equal in length. AB is parallel to CD. BC is parallel to AD. Further, AB is equal to CD and BC is equal to AD. Very, very, very important property is diagonals bisect each other. Diagonals bisect each other. This, please remember, is necessary and sufficient for a parallelogram. Please remember it. It is a very, 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 very important property. In a parallelogram, diagonals necessarily bisect each other. In a parallelogram, diagonals necessarily bisect each other. And if diagonals bisect each other, it is a parallelogram. So, for sufficiency, insofar as necessity is concerned, it is very trivial. Since these two are similar, these two sides are equal, so this will be equal to this to this. Okay, and by diagonals bisect each other, we can say that if diagonals bisect each other, these two triangles are going to be congruent triangles. You can very easily see this is equal to this is equal to this, these two angles are definitely equal. So, this angle will be equal to this angle will be equal to this angle, hence the opposite sides are parallel. Okay. So, will be the case here. So, one pair of sides being equal and parallel, but what is mostly used, you will be very often using it is this. So, you can see that there is a step more. In trapezium, what we have said, diagonals bisect each other in the same ratio. If that same ratio is 1:1, it becomes a, what does it become? It becomes a parallelogram. In a trapezium, what we are saying, diagonals divide each other in the same ratio. If that ratio becomes 1:1, you get a parallelogram. One pair of sides being equal and parallel is sufficient for parallelogram. Okay. One pair of sides being parallel and equal is sufficient for a parallelogram. Sufficiency part, please keep in mind. Sometimes if we have to justify that a quadrilateral is a parallelogram, we just say that since diagonals bisect each other, it is therefore a parallelogram. Diagonals are not equal in length, as you can see in a parallelogram. Now, if you are able to see that all the four triangles are of equal area in a parallelogram, or these two, okay. A diagonal divides a parallelogram into two triangles of equal areas. You can see this and this. These two triangles are going to be congruent. So, a lot of times bisection plays a very important role in proving this. Converse, for example, converse of basic proportionality theorem is generally done through converse of basic proportionality theorem is generally done through the Thales theorem that you go through is generally done through this only. Okay. Now, we must be well versed in utilizing them. Suppose somebody is asking us regarding, say, show that centroid divides medians of a triangle in the ratio we had just used it as a fact earlier. There are various proofs available. I am using the proof which utilizes the diagonals of a parallelogram bisect each other. Okay. We have to show AG is to GD is 2:1. Fine. So how would we go about it? We extend GD to EFG to say some point K. Extend GD to K such that GD is equal to KD. Now look at it very carefully. What are we going to do? See, these two are definitely equal. We have extended it like this, so we can safely say therefore BKCG. In quadrilateral BKCG, diagonals bisect each other. Okay, in quadrilateral BKCG, diagonals bisect each other. Hence, it is a parallelogram. Hence, it is a parallelogram. Now, if you look at it now properly, see triangles. Now, triangles AFG and ABK. See again, this we have shown that they are parallel, are similar. Therefore, by midpoint theorem, okay. See AF by AB, or let us now write only by corollary, we can say by corollary of Thales theorem or basic proportionality theorem. Let me write by corollary of basic proportionality theorem, AF upon BF is AG upon GK, which is 1, since this is the midpoint. So AG is equal to GK. GK is 2 times GD. So AG is to GD is 2:1. This is one proof where we are using parallelograms. So medians are divided in the ratio 2:1. Okay. Further, we should also keep in mind that in a triangle, this triangle, and this triangle, medians divide the triangle like this. These three triangles are of equal areas. Okay, you can see this is 2:1. So the height, this height is 1/3 the height of the triangle. This is 2:1. So this will the same will be for height. Okay, 3:1. So 3:1. Base remains the same. So we must remember this also. I may have forgotten it, that if you form a triangle and if G is its centroid, G is centroid of this triangle. So area of triangle ABG is area of triangle BCG is area of triangle CAG is 1/3 area of triangle ABC. Maybe I don't actually recall that I explicitly told you. So even if I told you, it will be a revision or just, we should keep this in mind. We should have done while dealing with similar triangles only, but maybe probably I didn't remember maybe. Fine. Further, if somebody is asking you, see, further this too is can be proved like this, see, the converse of midpoint theorem. If D and E bisect, for simplicity let us say bisect AB and AC respectively, then DE is parallel to BC. Okay. Midpoint or same ratio, suppose somebody says. So we simply extend it, suppose. Okay. We extend it to points at the BC and say DEF are equal, and then we join it. Now oh sorry. Okay, we extend it like this. So are you able to see something? See, or you can draw something parallel to this and then extend it. Anything will work. See, suppose DE and EF are equal. Suppose we extend it like this. Okay. There are various ways to deal with. Suppose D is, okay, these two are already equal. So this angle and this angle are definitely equal. So it's these two are equal and parallel to. Why? Because this angle will be equal to this angle by congruent. So these two are therefore parallel. Okay. Now okay, equally. So this becomes a parallel. How come these angles are equal? Hmm. This is parallel to this, fine. And then we have to show that these two are parallel. The angles would suffice. Fine. Okay. These two are already parallel. So this angle is equal to this angle. Okay. So this third angle is going to be equal to this angle. So since these two angles are equal, they are going to be parallel. Fine. So lot of things are done using the notion of diagonals bisect each other in a parallelogram. Okay. Now if you move ahead to say special quadrilaterals like say rectangle, rhombus, square. Okay, so in a rectangle the diagonals are equal in length. Is a parallelogram in which diagonals are equal in length. All the angles are right angles. In a rhombus, it is a parallelogram all whose sides are equal in length. So diagonals bisect each other at right angles. And in a square, all four sides are equal. It is a rectangle, special case of a rectangle as well as a rhombus. Of course, special case of a parallelogram too. So we are simply shrinking the set. Larger version would be your trapezium. Say, trapezium, we have a family. In the family of trapeziums, we have parallelograms. Further inside it would be, very sorry, rectangle, rhombus, square. Sorry. So in a rectangle, diagonals are equal. So in a parallelogram, if diagonals are equal in length, it becomes a rectangle. In a parallelogram, if diagonals are perpendicular, it becomes a rhombus. In a parallelogram, if diagonals are perpendicular and equal, it becomes a square. Okay, but bisection is a very important tool. Okay, here diagonals are equal in length and they are bisecting each other. This angle is not 90 degree. Okay, here diagonals, of course, because it is a parallelogram, diagonals bisect each other. Okay, they are not equal in length. In a square, diagonals are perpendicular and equal to each other. Bisection plays an important role. If somebody says, suppose somebody says, in a quadrilateral, diagonals are equal in length and are perpendicular to each other. Then it is a square. True or false? Okay. So see, I am drawing two lines which are perpendicular to each other and are equal in length. Say this is A, B, AC is equal to BD and AC is perpendicular to BD. Okay, now you can very easily see that it is not a square. So bisection, I have emphasized it for say last 15, 20, 25 minutes that bisection is a very important tool. Property is a very important tool in solving problems and is a very intrinsic and important property of something being a parallelogram. See, of a quadrilateral being a parallelogram. So bisection plays an important role. Otherwise, if they bisect each other, so bisection in a parallelogram, we told, in a parallelogram, if diagonals are equal and perpendicular, it is a square. In a parallelogram, if diagonals are equal in length, it is a rectangle. In a parallelogram, if diagonals are perpendicular, it is a rhombus. Fine. All the sides of a rhombus are equal in length. Okay. So please keep this in mind. Fine. Similarly, see what we say is also to be kept in mind is that the quadrilateral formed by midpoints of sides of any quadrilateral is a parallelogram. So what we are saying is that if you take any quadrilateral then the quadrilateral formed by midpoints So we have to say PQRS is a parallelogram. What we can say is that SR is half of AC and PQ is also half of AC. SR is parallel to AC and so is PQ. So one pair of sides are equal and parallel. Hence this is a parallelogram. Okay. Fine. We could have done it for the other also. You can similarly show that other pair of sides too are parallel by joining B and D. So please keep this in mind. That one pair of that in any quadrilateral, the quadrilateral formed by midpoints of the sides is a parallelogram. Now moving ahead, okay. Suppose I would say given 3 non-collinear points in a plane, how many parallelograms can be drawn three of whose vertices are these 3 points. Okay. So you are given, suppose I am saying you are given 3 points. And we have to draw parallelograms, 3 of whose vertices are these points. So you can safely say, see what is the situation? See, you have 3 line segments being provided. You can treat these 3 as 2 of them as sides and 1 of them as diagonal. Suppose I draw this one. See, one very obvious one is this one. Okay, this is a parallelogram. We have taken these 2 as sides and this as diagonal. Now suppose somebody says I take these 2 as sides and this as diagonal. Okay, so what are we going to get? Let us use a different color pencil. Okay, so this is the parallelogram. Okay, these 2 are sides and this is the diagonal. These 2 are sides and this is the diagonal. Now these 2 being sides and this being diagonal. So suppose these 3 points were A, B, C, P, Q, R. Okay. These are the 3 parallelograms that you are able to do. If you look at it very carefully, okay, if you look at it very carefully, these are nothing but, see, and ABC are nothing but midpoints of PQR. Midpoints of PQR. Okay, and these sides are nothing but half of sides of this triangle. You can be asked further questions. Suppose area of this triangle is delta. What will be the area of triangle PQR? They are just twice the sides, 4 times. Okay. Now somebody may ask you, see medians. See, please keep these things in mind. Okay. Median of, suppose we draw these 2 triangles. Okay. What we have done is that we have taken midpoints. Okay. Now, see, look at it very carefully. This sides of this triangle DEF are half the sides of triangle ABC. So, area of triangle, we must area of DEF is 1/4 area of triangle ABC. You can say BDEF, this is a parallelogram. BFEC is a parallelogram. AFDE is a parallelogram. Further, what you can possibly see is that, see, if you draw medians of the original triangle, what you can see for DEF, what will they be? So you can see that since these are parallel, okay, if this is x, this is x, this is x by 2, and similarly this is x by 2. So this is median. This is median for triangle DEF also. This line you can see. See, if this is x by 2, because this is bisection, and these are parallel definitely. This is x by 2. So centroid of DEF coincides with centroid of ABC. They have same centroid. Okay. Further, somebody can also ask you, see, okay, if we are drawing it, let me complete today's lecture using this. Suppose these are midpoints. D, E, F. Fine. Now, if you look at it, see, if I draw perpendicular bisectors of ABC, perpendicular this point O is what? O is circumcenter of ABC. And if you look at it very carefully, it is the point of intersection of altitudes for DEF. Are you able to see? See, this is perpendicular, these two are parallel. This angle will also be 90 degrees. So, O is orthocenter of DE. So, just we will keep, once we come through, go across circles, then also we will come across new results. But as of now, the purpose of today's lecture was to come to quadrilateral and then some properties of triangles as has been deduced. See, a very important property of parallelogram: diagonals bisect each other, necessary as well as sufficient. That is the crux of today's lecture. A lot of theorems you would be requiring this elementary property of parallelogram in solving problems, in proving theorems. So, please keep this in mind apart from definitely other well known facts. So, I hope starting with quadrilateral and then ending with some properties of triangle, this session would have been beneficial to you. Today we will be discussing some important theorems related to triangles and quadrilaterals. We have already gone through triangles, similarity, congruency, quadrilaterals, angles, parallelism. So, we have discussed these things. Now, we move on to some notions that are known to us based on notions that are known to us based on what we have gone through. Pythagoras theorem we have gone through. So, different things that we have gone through, we are now going to, as such, say we are now going to apply those things to come up with theorems that we are going to use in solving problems. Some of the things that we did earlier helped us in solving few problems, because in a time bound examinations certain things need to be known. As I have repeatedly kept on saying that whatever theorems you know, it is necessary that you know their proofs. Okay. So, one very important theorem that is used is, say, is Stewart's theorem. We will also go through Seva's theorem and Menelau's theorem today. Okay. And then we will see how we will apply in problem solving in so far as triangles and quadrilaterals are concerned. Primarily this is related to Stewart's. These theorems as such are related to triangles only. Okay. Now, in a triangle ABC, suppose you draw a transversal from A to meet side BC at D. If these lengths are MN, this length is D, this is C and this is B. So, Stewart theorem states that and so this side is A. What does the theorem states? It is generally remembered as MAN, M-A-N, plus DAD. Okay. Bomb, B-M-B. Bomb sink, C-N-C. So, actually it is A-M-N plus AD square is MB square plus NC square. Okay. These theorems indicate that we will be using Pythagoras theorem to prove it. How do we prove it? We draw an altitude from A. Suppose say this length is x, say A, B, C, D, say this is some M. So let this be some P. So this is x, this would be n minus x. Okay. So what all we have in triangle? Suppose APD we have. See, AP square, if we write from here, is B square plus n minus x whole square. Sorry, 8. Oh, oh, D square, very sorry. D square is AP square plus x square. We can also say B square is AP square plus n minus x whole square. Now, if we take this triangle, we have C square is equal to, what is C square? AP square plus, what do we have? M plus x whole square. So you can see, how do you get to this AD square? How will we get NC square MN square? So you can say this, you multiply this by A. Then you have MB square. And then you have NC square. M plus N everybody knows is A. So suppose this is 1, this is 2, and this is 3. So we have to get rid of AP and X. So one can very easily see, what do we do? 3 what will you get? NC square minus AD. You can very easily see M plus N AP square minus AP. This will get cancelled out. What you are going to get is AMN. Okay. What you are going to get is, see, M square N plus N square N. See, M square N two MNX minus 2 MNX, that gets cancelled out. And NX square plus MX square minus AX square, that gets cancelled out. This you can write as Mn into M plus N, which is A. So AD square goes that side and you get the Stewart theorem. A very useful theorem, especially because not every time we will be having so much time that we are able to apply the theorem. So please remember this, it is something that is used especially when some lengths are given, some lengths are provided. For example, you have to find length of a median given sides of a triangle. This is a D is the unknown, everything else is known. A fantastic way. And with median, the theorem is called Apollonius theorem. What will we get for a median? You can just see. If we are drawing a median, this is A, B, C. Okay, these two are equal. Okay, so here your M is BD, N is CD, so both are equal, that is a separate issue. Okay, this is your AC, this is what you need, and as always C is AB. So MAN, what do you get MAN? BD, A is BC, N which is CD plus AD square is BMB, BMB. CNC, CD into AB. So now BD and CD are all equal. So you can see BD, sorry, this was BC, BC was 2BD, MAN plus DAD. So BD, 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 CD and BD are equal. What is BC? BC is nothing but 2BD. Okay, so you can say 2 times, this is 2BD, this is also BD, so 2 times BD square plus AD square is equal to okay. This is called Apollonius theorem. Fine, in fact this is giving you the length of median. Okay, what will be the length of median? You can very easily see d square, let me write AD as d square, it is AC square, AC square is B square plus AB square, AB square is minus, what do you get? 2 BD square, that means so this is length of the median. So on occasions, if somebody gives you 2 sides and the median, you can find this. If somebody is asked, suppose these two lengths are given, these two lengths are given, this is given. So it is very useful when you know, because see in the proof we drew an ulterior. It will not always be possible to do it literally every time. So it is advisable that you remember this, so that when such lengths are concerned, we are able to solve it. Okay. Now suppose ABC is a triangle and this is an angle bisector. These lengths as always are M and CB. Okay. If you want, because and suppose this is D. So if you want to find the length of angle bisector in terms of this, now we recall, if you remember, I hope you remember, we have already gone through this, M by N is C by B, okay, and B plus C is, and C, M plus N is A. So you can see M plus N so N is AB upon B plus C. So N is AB upon B plus C. And what is M? You can very easily say AC upon B plus C. From this we can find, and the thing that you must remember is that D square plus Mn is equal to BC, relating to, so D square is, if you want to find the length, BC minus Mn, M and N we are able to write like this. How do we get to it? I think we can apply again. You can see what you will write is Mn into M plus N plus D, AD square MB square plus NC square. Now we know M and N. M plus N is of course A. So you have A into Mn plus D square. What do we get? M AC upon B plus C plus so A gets cancelled out. What you are left with is BC into B plus C upon B plus C. So Mn plus D square is BC. Okay. So related to angle bisectors, this needs to be kept in mind. Okay, see, finding the length will be an issue. See, as we move on, you see finding angles is generally demanding, but demanding intellectually. But if you want to find length associated, then it is generally an exercise, a laborious exercise. And for length, the theorem that we have, either we use similarity or we apply Pythagoras theorem. Just we are constantly expanding the horizon, and therefore in case you have to calculate length, it is definitely useful, it is of great help that you remember these things. So in this is, I would say, this will be the sum total of angle bisector theorem. Bisector divides the opposite side in the ratio of sides containing the angle, and so this gives you the length of angle bisector, and this gives you the length of median. See, an explicit expression here will not be great. You can see if you write Mn, what it will be. In trigonometry, you do get a reasonable expression. If you write D square is BC minus Mn. What is Mn? You can write A square BC upon B plus C whole to B square not a very viable thing to remember, okay. B plus C whole square, sorry. B plus C plus A, B plus C minus A, you can use as S minus C A type thing, but it is not a very good I think this is something that we can remember. Is it not? This is something that we can very easily remember. Okay. Now you can see what sort of problems could be countered using Stewart's theorem. Now let me take a very simple problem. A very simple problem is two sides are say 4, 9 are two sides of a triangle. One of the sides is 6. One of the medians from vertex is 6. Okay. Somebody says find BC. Somebody may ask you length of other medians. Okay. So what we have just read, 2 times BD square plus AD square is AB square plus AC square. So 2x square is 81 plus 81 minus 79 is 25. So x, so 4x square is 50. So what is this side? This side is 5 root 2. Just what is the length of other medians? So I hope we just went through this formula. So suppose median through B, let's say median through B. Root 2B square 50 2B square, sorry, 100 plus 2C square 32 minus 81. 19 plus 32 root 51 by 2. And median through similarly we will use it 1 by 2 root of this 100 162 minus 60. This will be the longest median. Fine. This is semicircle circle. So I am avoiding it. Okay. Now, suppose somebody asks you a problem like this. Okay. In a right angle triangle, D and E trisect the hypotenuse. Okay, and this length is x. Okay, so we have to show that p square plus q square is 5x square. What we already know is that AB square is 9x square. Fine. Now how to proceed? It is very simple, I think. How do you write P? So when we say MAN, suppose this is this is M and this is N. So M is x, N is 2x. So MAN, MAN plus D, which is AD square. So it is BMB. Okay. So AC square BMB. BMB is AC square into x. CNC. This is AB square into 2x. So what do you have? 6x square plus p square is AC square plus 2AB square. Similarly, if you are able to see, what you are going to get again is 6x square plus q square will be AB square plus 2 AC square. You simply add them. What you are going to get is 12x square is 3 AB square 9x 27. So will it be 2x into x into 3x? 3, where did this 3? 3 भी तो यहाँ आएगा ना यार 3. Okay, so this is now 27x square. So p square is 5x square. Okay, so these type of questions you can get in IOQM. P square plus q square by x square is. I am not saying that this would be the only theorem. Otherwise, people what do? They may draw altitude. So basically, what you will get involved into? You will get involved into proving the theorem as such. Okay, so remembering Stewart's theorem is of great help. Just as you can see, you found out the length of medians, you found out the relation between length of angle bisector. So if you want to find length of angle bisector, I think these two lengths can very easily be found out, because this is the ratio known to us. So length of any other process would be more demanding. Apollonius theorem would be of great help. So Stewart's theorem does has a wide variety of uses in length chasing. In length chasing it is of great help, because in length chasing we use either Pythagoras theorem, you can say that these things have been deduced from Pythagoras theorem. So that is definitely the case. But knowing the length of median is an asset. Knowing the expression for length of angle bisector, at least in terms of Mn, if not the final expression, is also an asset. And of course, questions where you are given a situation like this, okay, this median, this being median is just incidental. Any other case we are able to counter it, we are able to settle it using Stewart's theorem only. Okay. So, please be well versed, solve questions from say assignments or Pathfinder book of Prashant Jain sir, so that you are able to fathom what can be asked and you are able to very comprehensively grasp what sort of different situations you will encounter in this. I have taken some examples. As we move on, once we are through with circles, you will see that it is really, geometry will really explode very beautifully. Okay, now at this juncture, because we are doing it very systematically, we are confining ourselves. We are confining ourselves to the sequence that we are following. We are not randomly taking things. Okay. Now, what does Seva's theorem says? That if you take any point and you draw lines like this, say, so what does it say? Suppose they meet at O. BD by CD, this ratio, just we complete the whole path. CE by CA, sorry, EA, and then AF by FB is 1. Ratios we are deliberately taking as positive, even if the point is outside, suppose, okay, and we have a situation like this. Now, in terms of, we have drawn only when point is inside, point could be outside also, okay. So, in fact, similar triangles can be used, or half base into height can be used in proving this. So, I am using say area ratio. So, BD upon CD is area of triangle ABD upon area of triangle ACD. Same height, so it will be in the ratio of bases, is also equal to area of triangle BOD upon area of triangle COD. So, if you subtract it, ABD minus BOD, this is area of triangle AOB upon area of triangle ACD AOC. Now, CE upon CA, CE upon CA you can similarly say is, just as we said, the area of triangle AOB. So, from similarly C you can say it is area of triangle BOC, area of triangle AOB, isn't it? AOB, yes, and then AF upon FB, AF upon FB, the area of triangle AOC, upon area of triangle BOC. So 1, 2, 3, you can multiply, you can see. Okay, so this is the proof of Sevastopol. I have even some of the theorems which I didn't prove, I deliberately skipped some of the proofs in our earlier class, and I specifically told you that please prove them, and if you have any issues then you can get back to us, but don't just remember things as a result, always try to prove them. Take your time, even if it takes half an hour, 30 minutes to establish the theorem, but that effort will bear fruit as we move on. In actual problem solving, when you solve problems of actual that have actually appeared in examinations, you say somebody may even ask you find ratio of area of these two triangles. In that case, if we have gone through this, we know it is the same thing. So this is the final result that we get, but the process in between that gives you the hint of how to proceed in different problems. Now the converse of theorem is the same. Converse of is that if BD by CD into CE by EA into AF by FB is 1, then AD, BE, CF are concurrent. Okay, this is of great help in proving the concurrency of medians, altitudes, angle bisectors. How? Or even perpendicular bisectors. So perpendicular bisectors are will not be there because it is not passing through the vertex. Sorry, so BD by CD. How do we prove it? The converse part. We say let AD and BE meet at O. Okay. Let me write it down formally. Let AD and BE meet at O and CO meets AB at F dash. Okay. So by Severs theorem, what we have? BD by CD AF dash now we already know what is given to us is so therefore what we have is AF dash upon BF dash is equal to AF by FB. So what does this gives you? Just add 1. AF dash plus FBF dash AB upon BF dash is AB upon BF. So you have BF dash is BF. And since F lies on AB, this implies F dash coincides with F. So converse also holds that if the product of this ratio is 1, then the 3 lines, we say the three savions are concurrent. These are called savions. AD, BE, CF, they are called savions, are concurrent. So, if you want to prove, say, medians are concurrent, in fact, initially, if you recall, we just took it for granted initially that they are concurrent. There are various ways. This is a fantastic way to prove it. One upon one, one upon one, one upon one. It is very trivial. In case of angle bisectors, I think it is very easy to observe in case of median, I think. So, I have not. In case of angle bisectors, we already know the ratio. BD upon CD is BD upon CD. We know it is AB upon AC, CE upon EA. And AF upon BF is AC upon AF PC. Multiply it, you get it as 1. So, hence they are concurrent. What angle bisectors are concurrent. In altitudes also, you can similarly say that they are concurrent, but in that case you need to know the ratio. Okay, fine. So, I hope you are getting it what we are into. Okay, so the very standard things are solved using Sever's theorems. This is a very common question that is asked. Okay, suppose this is 6, this is 5, and so this is 8, and you are given, suppose you draw AD, this is 3, this is 5, then you draw BE, okay, this is 2, this is 3, they meet at O, and the question asked is CO meets at F. So, AF, what is AF? This is a very common question. Once we have seen what the situation is, you can very easily say 5 upon 3 into 2 upon 5, okay, into, say, this is x, so this is 6 minus x, into x upon 6 minus x is 1. That's it. So, this completes the problem. 2x if somebody is asking you the length of CF, okay, somebody is asking you the length of CF, then what we have? Stewart's theorem. Okay, somebody may ask you AF, somebody may ask you CF. So, if you want to find CF or BE, anything, then we have Stewart's theorem. Otherwise, this is Sever's theorem. So, what you are able to, I think you should be able to grasp is that we have to see how they are applied in actual problems that we get in the examination, and for that I am again insisting that if you are able to, if you are confident that as and when needed you are able to prove it, then only you will be able to solve it in the solve the problem. That means you are able to use it because you know the steps prior to the final results. Now, suppose I say what is the area of triangle AOB upon area of triangle AOC, you can say it is 5:3. because you have gone through that process. It is not that you can remember everything, but if you have gone through the processes, you are able to recall how do you initiate problems. That is the crux of competitive exams, that instead of finding corollaries to the theorems, corollaries to the standard result, they go backwards. How did we get to those theorems? Do you know those steps? So therefore, probably for the nth time I am saying that if you are able to recall the theorems, not only the theorems but also how did you prove them, that is the real asset that you will possess, rather than the final formula itself. Okay. Let me also share with you Menelaus theorem. So, if suppose you draw a transversal which cuts the three sides. Okay. So, and say, let me use a different color. Again देखिए D, E, F. So, a transversal intersecting the three sides. So, again BD by CD into CE into AF by BF. This algebraically we say is -1 because you can see two of the ratios are internal and one ratio is external, or all three can be external. Okay. Suppose this is the line. So, all the three ratios can be external, all three cannot be internal. In such variance, we deliberately say positive because suppose this is the situation. So, what you get is that two of the ratios are external. So, two are negative and one is positive. Okay, so product will in effect be positive, even though in length we rarely use the sign of plus minus, but if you algebraically proceed external division negative, internal division positive, then you can see this is the situation that Saver's theorem, Savians, either two of them will meet the sides externally and one internally, or all three are internal. Here either all three are external or one is external. So, algebraically it will be -1. In terms of proving it, what we do is that we draw a line parallel to the base and say this is P. Okay. Now, can you see these two triangles are similar? Okay. So, BD upon AP. So, BD upon AP. What is it? BD. So it is BF upon AF, because the triangles are similar. Okay, this is parallel. We have drawn a line parallel to the base. These two triangles are similar. These two triangles are similar. So what will you have? You will have AP upon CD. See, these two are similar triangles, APE, CDE. So AP upon CD, what will it be? AE upon C. So if you multiply, what do you get? BD by CD is BD by CD into CE by EA into AF by BF is 1. We have taken the absolute values. We have taken this. We have not taken the sensed distances. We have not catered to. See, if this is how you measure AP, then this will be negative. So that is why in length, generally in geometry, we confine ourselves to positive things only, but algebraically internal division is positive, external is negative. So that is how you factor in those things. Okay, a transversal cutting like this. Again, you can see it is a simple application, not a simple, not necessarily very simple, but again I would say a reasonable application of similarity of triangles. So I deliberately skipped it in the previous lecture. I told you about quadrilaterals primarily, so that there is a sense of maturity when you come across these theorems. I could have very well gone into from triangle. These are theorems related to triangles only. Okay, theorems related to quadrilaterals also, some of them we discussed, that the quadrilateral formed by midpoints of sides of a quadrilateral is always a parallelogram. We also went through what is a trapezium, what is an isosceles trapezium, and stuff like that. Okay. So this is Menelaus theorem. So again, whenever you are asked something like this, a line cutting sides of a triangle at 3 points, Menelaus theorem is at your disposal to dwell into those issues. I would say Stewart theorem is very useful. You can see from Stewart theorem we went to Apollonius theorem, which was also, you can say, that helped us in determining the length of median. Always that I was able to remember the length of the medians. Okay. Now let us solve some problems. Suppose you are given a triangle ABC. So this is length 6, 6, 8, 10. And let me draw a line. Say D, E, F. So this is 4, this is 6. Okay. This is say 2. Okay, this is 1. this is 5 and this is x. Suppose we have to find x. And then we can use Stewart's theorem to say find sine the sides. Okay, find x and AD. So how will you find x? I think that is pretty easy. Okay, AF upon BF, 4 upon 6 into BD upon CD, BD upon CD into CE upon EA. Okay, so this is 2, 3, 8 plus x upon x is 15 upon 2, isn't it? So 16 x is 16 by 13. Now somebody may ask, just as I told you, somebody is asking you to find length AD. So we can apply Stewart's theorem. We have to find length AD. We know AC, we know AD. So this is something that we need to find. So what is the formula? So by Stewart's theorem, what will you do? M-A-N, M-A-N. So 8 104 plus 16, 120 by 13. AD square, okay, man plus dad, A D square. What is AD square? This is A. What is D square? 36. Man plus dad is BMB, okay. So B is something that we have to find. AD, M, 8 into AD square plus CNC. So C is 10, okay. So CNC 16 by 13 into 100. CNC, isn't it? CNC. So 8 2 15. Okay. Now you can find AD square. Collect terms at one place and determine it. Okay. So somebody may find you this. So Menelaus theorem, Stewart's theorem, Severs theorem, Stewart's theorem. So Stewart's theorem is very versatile. Please give special treatment to it. Okay. Because in length we don't have much, barring Pythagoras, similarity and congruency, we don't have much theorems. As we move on, once we go through circles, you will see that there are a lot of theorems regarding angles. But in terms of length, there are few. So we, as and when needed, we must stick to these 3-4 standard principles. In examinations, they generally don't go beyond it. Okay, now moving ahead, let me recap some of the things, and let me recap the notions that we did in the previous lecture also regarding quadrilaterals and some questions regarding that also. Now somebody says, okay, just one or two questions at this fag end, okay. Now somebody says you take an isosceles trapezium. And what you do is that you draw its diagonals. Now if we take midpoints of the diagonals and parallel sides, and join this. What is PQRS? Parallelogram or rhombus, rectangle, what will it be? Okay, so by midpoint theorem, you can say in triangle ACD, PQ is half AD. In triangle ABD, RS is half AD. So these two are equal. Okay, let me say these two are equal. Similarly, here you can say QR is half of BC and PS is again half of BC. So you can say all the four sides of this quadrilateral are equal. This will be a rhombus. Otherwise, it would have been, see, in any case, it would have been a parallelogram. Okay, in any case, it would have been a parallelogram. It is rhombus because this is an isosceles trapezium. Okay. Similarly, say suppose somebody says in a parallelogram, just one or two questions for practice I am taking, not much time is left. So, suppose we draw angle bisectors. What is the figure that they are forming? So, I think you can understand, if this is theta, this is pi by 2 minus theta. So, this is 90. Similarly, all the angles are 90. So, diagonals of a parallel, okay, angle bisectors, very sorry, angle bisectors of a parallelogram. What do they form? They form a rectangle, isn't it? Suppose this is a rectangle. So, angle bisectors 45, 45, what will this be? Here it is a rectangle, what will this be? ABCD is a rectangle. Definitely it will be a rectangle. Is it a square? See, these are angle bisectors. See, diagonals of a rectangle, they do not bisect this angle, okay. These two angles are not equal, these two sides are unequal. In case of square, they will all coincide at a point. Angle bisector is as good as the diagonal, but here that is not the case. So definitely it will be rectangle. Will it be a square? Will it be a square? This PQRS. Okay, just give it a thought. This is where we are ending today's lecture. Okay, so Stewart's theorem, Apollonius theorem, Sever's theorem, Menelaus theorem, these are the theorems that we have tackled today. Most of the things regarding to triangles and quadrilaterals are over. Areas we have also catered to on most occasions. We will now in our next class be moving to circles followed by angles. Okay, so I hope them. Now we will be coming to the part of circles. Once we have gone through circles, you will say that a huge box of questions where length chasing and angle chasing specifically opens, and you will see that the primary difficulty that one encounters in dealing with problems of geometry is angle chasing. That will be more fascinating as we move on. Now I am sure all of you would have heard the term circle. At a fundamental level you would have understood what it means. So we are discussing a circle, it has a center, P is a point on the circumference of the circle. This distance Cp is always equal to radius of the circle. C is center of the circle. This is circumference of this circle. Circumference of the circle everybody knows is 2 pi r. Area bounded by this circle is again pi r square. Basic terms I am absolutely sure you would all have gone through it. Now certain things related to circle, every point which is equidistant from the center will lie on the circle. Now some theorems related to circles. Okay, so the very important theorem of angle chasing involves this, that is angle subtended by the circle, by a chord at circumference is half the angle subtended at the center. I am sure you would all be knowing how to establish it. Okay. So how do we go about it? If these two sides are equal, they are all center of the circle. This is center of the circle, they are all radii. So if this is theta, this will be theta. If this is alpha, this will be alpha. So this angle is this angle is 2 theta plus 2 alpha. Okay, so this is what we were saying. Now you can say possibly that the diagram could have been like this. Let's suppose this is the center and say you are dealing with this point. Okay, when center lied inside the triangle PAB, then it was this, another possible figure could have been this. Okay, here also we are saying that the same thing. So, as such, there will be no change, you will do the same thing. You will be doing the same thing if you are able to see. If this is theta and this is theta, okay, this is theta, this is theta, this would be pi minus 2 theta at the center. And if this is alpha, and this is alpha, sorry, okay, and if this is alpha, and this is alpha, okay, what is this angle? Pi minus 2 alpha. This angle was pi minus 2 theta. Okay. Now you can very easily see what this angle is. This angle is alpha minus theta. And what is this angle? This minus this is 2 times alpha minus theta. So whatever may be the situation, okay, I just wanted to make sure that everybody recalls this. As I have been continuously saying, that if you read any theorem, please try to prove it. That is an essential, because you have learned. See what I have done. See, one of the triangles here was PCB. So you are doing the same thing. One of the triangle is PCA, other triangle is PCB. I know what the mistake I was doing it was I was considering the triangle ABC. So in either cases we are effectively doing the same thing. Okay. Now moving ahead, this is a theorem that we very frequently use. As a consequence, we say angle subtended by circumference, sorry, by diameter, sorry, very sorry, is right angle. Okay. So please remember this, angle in the semicircle is right angle, angle in the semicircle is right angle, that is what is also said. And therefore, if somebody says that AB subtends an obtuse angle, so we can say it will lie inside. If it subtends an acute angle, we will say it lies outside. So this plays a very important role in geometry. Suppose I am saying that P is a point moving such that angle AB and fixed points, P is a point such that angle APB is always obtuse. So we can say that it will lie inside the circle with ABS diameter. It will be of great help in solving a lot of problems. The moment we say that the angle subtended by a fixed chord is 90 degree, we are able to assume that there is a circle with AB as diameter can be drawn. On occasions it might be useful. Post that things are of great importance, especially while chasing angles. We will come to problems as we move on. Okay. Sorry. Now, suppose somebody wants to do a problem on this. Okay. Let me say the problem could be suppose somebody says in an acute angle triangle ABC H is the orthocenter. Now, somebody asks you to show that, let me draw with a different color. If this angle is theta, so this angle is theta. If angle BAC is 70 degree, find theta. Okay. Find angle AD. Again, see two right angles. What are they indicating? What they are indicating is, see, this is a right angle, this is a right angle. So, what we say by observation is that this too is an altitude. Circle with CH as diameter. Circle with CH as diameter passes through this is the utility of angle in semicircle is right angle. Okay, circle with CH as diameter will pass through E and H. Now, just by the theorem we have gone through this, what will be the corollary of this? Angle in same segment are equal. You can very safely say, if I draw this diagram, this angle 2 will be theta plus alpha. If I draw this, for every one of these points, the angle at the center is 2 theta plus 2 alpha. Okay, so what we see is that angle in same segment are equal, even when the diagram is like this. All these angles are going to be equal. Fine. So, if this angle is theta, this angle is also theta. This is angle A, this is 90. So, theta is 90 minus. So, what is theta? Theta is 70 degree, 20 degree, very sorry. This is how I am saying that the angle chasing plays a very important part. Even when lengths are involved, once we get angles and one of the sides, other things just follow. So just I was giving you an example where angle in same segment, angle in semicircle is 90 degree. These play very important role in solving our problems. As a corollary or as a independent theorem, this is arguably the most versatile of them all. Whenever you are dealing with angles, please keep this in mind. Okay. Now you can here see that if, sorry, it will be too clumsy. If this is theta, this is 2 theta, and if this is alpha, this is 2 alpha. This I will leave to you as an exercise. Okay. Just look at this, that just as I hope you would have learned something from the first proof. What we are saying is that if this is alpha, this is 2 alpha, meaning thereby that two theta plus 2 alpha is 2 pi. That is the sum of opposite angles of a cyclic quadrilateral is pi. This, just as I told you how to proceed, I expect that you start in the similar manner. Okay. This is the chord. What did we do here? A, B, P, C. There are 4 points. Okay. So A, B, P, C. So I hope you will be able to deal with it. Hai? First think of PCA. Okay. If so this is again, this is theta, this is pi minus 2 theta. So this would be 2 theta plus 2 theta. Okay. And this whole angle you can say. Now this is a cyclic quadrilateral. Whose cyclic quadrilateral means vertices lie on a circle. Fine. Now moving ahead, please think that this is the most widely used theorem or corollary, that is angle in same segment are equal, angle at the center is twice the angle at the circumference. You will see whether you are dealing with problems IOQM, RMO, INMO, almost everywhere you would come across a situation where this is to be used. Be absolutely sure, whenever in doubt, at least this thing can always be utilized. Now, regarding chords, what we can say is that equal chords are equidistant from center. Further, perpendicular from center bisects the chord. Equal chords subtend equal angle at the circumference. Of all the chords that pass through a point inside the circle, shortest chord is the chord whose midpoint is the given point. Length of a chord nearer the chord is to the center, the longer it is. And you can see that the smallest chord, theoretically speaking, the tangent would be having length 0. Okay. Now, how do we justify all of them? Equal chords, you can say, suppose you are in a circle, you are taking two chords of equal length. These two are equal, others are automatically equal. So, these two are congruent triangles. So, if they are congruent, their altitudes from center are going to be of equal length. Now, insofar as perpendicular from center bisects the chord, suppose you draw an altitude. So, by RHS, these two triangles are congruent. So, it is bisecting. Equal chords subtend equal angle at the circumference. You can see that these two angles are equal. So, angle subtended by this chord at the circumference and this chord at the circumference, they are going to be half of this angle. So, they are obviously equal. Now, of all the chords that pass through a point inside the circle, shortest chord is the chord whose midpoint is the given point. So, how do you get to it? say suppose this is the chord whose midpoint is, suppose this is the given point. Now there are infinite chords that you can draw passing through this point. Now what you can see, that if you draw a perpendicular from center, if you draw a perpendicular from center, CM is hypotenuse of these triangles. So all other chords are nearer to the center. The nearer the chord is, the lengthier it is. Okay. So this is the chord which is going to be farthest from the center. The farther it is from the center, the shorter it is. So that is what we are saying. This is the shortest chord of all the chords that pass through a point inside the circle. The shortest chord is the chord whose midpoint is the given point. So these are few facts that we came across, something that we use very often in dealing with problems. There are a lot of theorems as we move on that we go through, but at the initial stages, these things might suffice in dealing with various problems of circles that we come across. Okay, there are definitely a lot of other theorems that we go through. We will go through as we solve different problems. Okay. Angle in semicircle is right angle, angle in same segment are equal, they play a very significant part in dealing with problems. That is why earlier also I told you that angle chasing substantially increases once we get involved in problems of circles. Fine. Now moving ahead, let me solve one or two problems. Suppose you are given a circle, a very simple problem is, if radius of the circle is 13 and length of the chord is 24, how far the chord is from the center? So very easy, you can almost understand what we are going to do, isn't it? What we are going to do, say perpendicular from center will bisect the chord. This is a right angle triangle, this is 24, this is 12, this is 12. So its distance from center is 5 units. So it is a distance of 5 units from the center. Okay. Now suppose I ask you a problem like this. Okay. Suppose this is a circle and this is center, this is A, this is B. This is 1:3. Now if somebody is asking you to find, given that radius, suppose I give you radius as say 8 and this distance as 4, what is length of this chord? I am sure what you are going to do, we are being asked to find length of this chord. Okay. This is ratio 1:3. So what are you going to do? Stewart's theorem can be used. I hope you remember it, that if this is lambda, this is 3 lambda. Okay. So this is your m, this is your n. A is So what it is? It is MAN. Will the calculation be too tedious? MAN plus DA D CNC plus BMB. So what is CNC? This BMB, so 64 lambda BMB plus 64 into 3 lambda. So 12 lambda cube plus 64 lambda is equal to 64 lambda plus 64 into 3. So this gets cancelled, and what do you get is 60. So lambda square is 60. So lambda is 4. If lambda is 4, so this is 4 and this is 12. The length of the chord turns out to be 16. How is this possible? There is some error in the way we have solved it. So what is the error that we have done? MAN plus DAD BMB CNC 64 lambda. Oh, 16 for the 64. That's fine. So how could this be 16? Okay. If this is 16, so be it. You know? If this is the chord. So what is the situation? The situation is like this. This is 8 and this is 8. Fine, everything is fine. You know? Just I just randomly took the data. It turned out to be the diameter. Okay. No issues. You know? If that is the situation. Other way we could have done is that suppose we are not able to recall Stewart's theorem, then ideally we would have done it like this. This is how I would have done it, because so this is 4. So we drop a perpendicular, okay. So if this is lambda, total length was 4 lambda. This is also lambda and this is 2 lambda. This is 8. So you could have written the altitude as this altitude in this right angle triangle. Suppose this is C M. So we, by Pythagoras theorem, we would say Cm square is Cp square minus Pm square, and (16) minus lambda square is, so 3 lambda square is 48. Lambda is 4. This is also one way we could have proceeded. So just the fact that angle in same that chord perpendicular from center bisects the chord. You can use that the perpendicular bisector of the chord passes through the center. So these are just one and the same thing, converse of it. Okay. So what you can see is that initially the problems that we are doing, these problems are primarily of length chasing, but the properties of circle that we have gone through has helped us in solving it. We could have used this also, I am not denying it, but I would have preferred it being done this way. Again, it is not something, it is an individual's priority, what priorities he had set up. Okay. Now, some more problems regarding the theorems that we have gone through. So, one very simple thing that as a corollary is that even if I treat it as a problem, you can say that suppose you have two chords, okay. So, PA into PB is PC into PD. Two chords AB and CD meet at point P, the rectangle contained by PA and PB. Okay, if two chords meet at P, the rectangles, this is how it is written, the rectangles contained by PA and PB is equal to the rectangle contained by PC and PD. So, you can very easily see, okay. Angle in same segment are equal, okay. Suppose you say this angle is alpha, then this 2 is alpha, this is beta, this 2 is beta, these two are definitely equal. So, these two triangles are similar. The rest follows, I think. Opposite to alpha PA, opposite to alpha PC, opposite to beta PD, opposite to beta PB. PA into PB is PC into PD. Now, this point could very well have been outside. Okay, in that case, what do we do? See, the process everywhere is same. If this is alpha, okay, this angle is alpha. We just went through this. If this is alpha, this is pi minus alpha. Okay, just now if this is theta, this is alpha, their sum is pi. So, if one is theta, the other is pi minus theta. Okay. Similarly, if this is beta, again triangles PAB is similar to PCB, PAD sorry, is similar to PCB. So, you can see opposite alpha PB, PAD opposite alpha PD upon PB, okay. PA opposite PC. PA into PB is PC into PD. And what is PA into PB is PC into PB. So, what does this tell you? That if you draw from external points different chords, different lines which meet the circle at 2 points, the product of the two segments, they are always going to be equal. Suppose this is EF. So, PA into PB is PC into PD is P into PF. Once we come to tangents, we discuss other things also. Okay, what is this length equal to? You can understand as these 2 points coincide, what you get is tangent. So, PT into PT. There would be other proofs too, but this time for the sake of argument I am saying that if these 2 points coincide, PA into PB, PC into PD, P into PF is PT into PT. That is PT square, square of length of the tangent from an external point. Okay. Now, regarding tangents, let us first in this class understand all the major properties that we encounter. Problem solving is something that we learn slowly. In my belief, that would be better, so that we are not hindered by problems, that this has not been gone through, this has not been gone through. So, insofar as tangents is concerned, it is a line which meets the circle at only one point. Okay. So, you can say this angle is 90 degree because this point itself now becomes midpoint of the chord of length 0. Okay. So, perpendicular from center rather than saying perpendicular, what do you say? Radius. Radius at point of tangency is perpendicular to tangent. Okay. This is also a very useful thing. Further, this is said angle in alternate segments are equal. Angle in alternate segments are equal. Fine. See, if you wish to establish it, how do you establish it? You can see this is 90 minus theta, this is 90 minus theta, so this is 2 theta, so this will be theta. Okay. So, this is 90 minus theta, that would be theta. This is center. So, angle at the circumference is half the angle at the center. Okay. Just I told you just some moments ago that this is PA into PB is PT square, if you recall. Okay. So, I would ask all of you to prove this. Okay. You can draw, so this is T. PTA, PTB. So, suppose this angle is theta. Which angle is now going to be theta? Angle in alternate, this is theta. This angle is definitely common. So, therefore, these two angles are equal. So, these two triangles PTA, PTA and PBT are similar. PTA, है ना? Now, opposite to theta, in PTA, opposite to theta, you have PA. In PBT, opposite to theta, you have PT. Okay. Now, opposite to this, in PTA, you have PT, and opposite to this, you have PB. So, PA into PB is PT square. A very, very useful thing. You will see that it is very often utilized in dealing with problems. So, today lot of time I have deliberately spent just on deducing the basic theorems that we are going to continuously use. I was advised by Prashant sir that we should teach the basic theorems too. So, I am definitely sticking to it. So that all of you get the gist. I am saying that we could have solved a problem where this was to be utilized. We will do so as we move on, but any theorem, suppose I have not told you the proof, please go to your home as and when you get time, please try to prove it. Otherwise, you will see that ultimately they will be of no use. You can see these two angles being equal, alternate segments being equal. Okay, angles in the alternate segment being equal have led us to this. There are different ways to come to this conclusion, but we have utilized this at this juncture. Further, say you can draw two tangents from an external point. Okay. This is PC. So you can very easily now see that PA and PB are equal. These two triangles are congruent by RHS. So PA and PB are equal in length. Fine. Now if we have gone through sequence and progression and stuff like that, we can say that C is midpoint of say QR. QR. So PC is arithmetic mean of PQ and PR, and PA square is PQ in PR is geometric mean of PQ and PR. In fact, the term geometric mean comes from here only, that if you have a circle and what is this length? Perpendicular, if you draw a perpendicular, this is the diameter say. What is this length? X. So the term of geometric mean comes from this only, that you simply extend it. And you say perpendicular from diameter bisects the chord. So this is also X. So X square PC into PD is PA into PB. So what is X? Root PA into PB. So the term geometric mean, if geometric mean of A and B is root AB, is in effect named because in a geometrical situation this is what appears. That is why it is called geometric mean. You can say this is 90 degree, this is 90 degree. So what can we say? If you recall just few minutes or say 20-25 minutes ago, we went through this circle with CPS diameter, circle with CPS diameter passes through A and B. In fact, this circle is circumcircle of triangle P. Circumcenter would be midpoint of PC. Okay. Now, just based on this fact, if somebody asks you, see a question like this, you consider a circle of radius r, say 2r. Now, draw another circle of radius r. From B, draw tangents. Okay. What we are saying is that this circle has radius r, this circle has radius 2r. From B, you draw two circles touching at D and E. Fine. So, if O is circumcenter of triangle BDE, determine CO upon C, let's say CE, CA, that will be one and the same thing. Now, you can very easily see what is the length of these tangents. If this is r, BC is 2r. This is r root 3. This is also r root 3. Fine. So, can we find the angles also? This is r root 3, this is r root 3. I hope you are aware of a bit of trigonometry, or let me avoid it. Let me avoid using any trigonometry. Let me deal with it in a different manner. So, I have to find this length, okay. Suppose this length is x. So, I would say area of this triangle is half r into r root 3. Area of this triangle is also half base into height. So, x is r root 3 by 2. So, this is all in all r root 3. So, this triangle now becomes equilateral. Now, we can safely say they are all 60 degrees. Now, just some moments ago we said circumcenter of PC, circumcenter of PAB is midpoint of PC. So, circumcenter of this triangle is midpoint of BC, which is nothing but A. Since this is an equilateral triangle, A will coincide with O. So, your answer, what is the answer? CO by C is simply 1. Got it? So, these facts do help us in dealing with problems. This is a good problem. I knew the solution, so I directly took it the way it should be. But determining that this is an equilateral triangle is an ask. I deliberately avoided trigonometry for the purpose that, say, if we are able to do it geometrically, that will be better. In this, what we used is length of the tangent. So, length of the tangent from an external point, I hope you are able to see. We said, okay, so length of this tangent PT, whenever we have to find length of the tangent, what do we do? This is 90 degree. Okay. So, what is length of the tangent? Root, we say it is root of d square minus r square. More on common tangents to two circles and other things. In this lecture, we will deal with some properties of tangents to circles. Even though in the previous class, we did discuss things about tangents also, but here today we will try as much as possible to deal primarily with tangents, and if the time allows, we will move forward with, say, Ptolemy's theorem and stuff like that. So, tangents, as we know, the things that we covered in the last lecture were the very elementary notions. Say this is center, that radius at the point of tangency is perpendicular to the tangent. This is what we covered, followed by angle in the alternate segment are covered. This is basically just a recap of our last lecture. These are the things that we covered in the previous lecture. These two things we went through. Also, we saw that tangent from an external point are equal in length. We also went through this theorem, we proved it if you remember. PA into PB is PT square. This is also something that we covered in the last lecture. And at the fag end, what did we cover? Since these angles are 90°, circle with CPS diameter will pass through these points of tangencies. So I just took your first 5 minutes to make you recall the things that we covered in the previous video. Now we also did questions on it. Now further we are going to see common tangents to two circles. Tangent is something that we covered. Now insofar as common tangents to two circles are concerned, this is the new thing that we are going to take up today. I just made you recall all this because as we proceed in this lecture, we will be requiring to use this. Okay, this is something very trivial. You would have gone through in say class 8th or 9th. This is a theorem that you would have angles in alternate segment are equal. This is something that you would have seen in say your NCERT text of 10th. This I think is something which can very easily be calculated because these two triangles are congruent. PA into PB is equal to PT square is something that we did using similar triangles, if you recall. Okay, so these stuff is something that has been constantly asked, and you should try to correlate problems given with the situations that we are dealing with. Now insofar as common tangent is concerned, if you take two circles, say one lying outside the other completely, okay, these are common tangents to these two circles. AB and so this is PQ. Okay, so AB is direct common tangent. PQ is transverse common tangent. Okay. Now this is also called external common tangent. And this is called internal common tangent. Now, say if this is the center, so C1, C2, this is say T1, T1 and T2. What we see is that in circles, sorry, line joining the centers C1, C2. So, what we see is that internal common tangent divides the line joining the centers in the ratio of radii. External common tangent two divides the line joining the centers externally in the ratio of the radii. Okay. This is something that should be kept in mind. It is a very vital thing. We will further move with finding the length AB and PQ, but at the very first go we should be able to remember this. What is this? That the line joining the centers. Okay. So, the internal common tangents divides the line joining the centers in the ratio of radii internally. External common tangent divide the line joining the center externally in the ratio of radii. Okay. I think we will be able to prove it. How do we prove it? Say first and foremost, let us prove that they meet on the line joining the centers. So, what we say is that suppose we draw this line, say C1, C2, this is T2, this is marked as AB. Okay. So, what we are saying is that suppose AB meets line joining centers at T2. This is R1 and this is R1, sorry, this is R2. Now, we can very easily see that these two triangles are similar. Which two triangles? T2A C1, T2B C2. Okay. So, what is the ratio of C1 T2 upon C2 T2? This is R1 by R2. Okay. Now, let the other tangent, common direct tangent meet it at, say, for the sake of simplicity I am taking it T2, otherwise ideally we should take it to be some other point. And then we can again say, suppose this is T2 dash, then we can say C1 T2 dash upon C2 T2 dash 2 is R1 upon R2, meaning thereby that T2 and T2 dash coincide. I think we can very easily see that this is the same thing that we are going to do for internal common tangent. So, this establishes the fact that direct common tangent meet on the line joining the centers, and so would, I think you can now understand how we will do for this one. We will draw this diagram, and similarly we will draw this diagram, and then we will say T1 and T1 dash, they divide in the same ratio R1 is to R2, so they must be coinciding. So, this is the first thing. That okay, direct common tangent divide the line joining the centers. In the ratio of radii externally, and so would be internal common tangent divide. Agreed? Okay. Now, if you want to find length AB, what do we do? Suppose we have to find length AB. Okay. C1, C2, A. So what we do is that from point B, we draw a line parallel to C1, C2. Okay. So if this is R2, this 2 is going to be R. So what is the remaining length? R1 minus R2. This you can very easily see the parallelogram. This is C1, C2. This angle is 90 degree. So we can find AB as this is the length of direct common tangent by simply Pythagoras theorem. Okay. Now, for transverse common tangent, what will be the length? Diagram is bit rough, so please pardon me. So this is R1. This is, sorry, R2. Now what we do is that let us extend it. Okay. Fine. Say this is R2, we extend it, say, like this, and then we draw a line parallel to the tangent. So parallel to PQ. So since it is parallel to PQ, this angle is going to be 90 degree. Okay. So you can see that, see, we have drawn a line, this, see, these two are parallel, fine. Since this angle is 90, this angle is also 90. Further, if you are able to see, since these two are parallel, they are always parallel. Okay. So, what you will have if this is R1, so this becomes as such a parallelogram. In fact, not even a parallelogram, this becomes in fact a rectangle. So, if this is R1, this too is going to be R1. So, I think we can find now further PQ will be equal to say C1 T. PQ will be equal to C1T in this rectangle. Now, PQ and C1T are equal. What is C1T? By Pythagoras. So, this is length of transverse common tangent. Fine. So, length, see if you are able to recall the expression in the previous one, in direct common tangent, this was simply R1 minus R2 whole square. So, insofar as remembering the expressions are concerned, C1, C2 is what distance between the two centers, and for direct common tangent, it is of say its length is more than transverse common tangent, just we can have a perception like that. This will be R1 minus R2 whole square, and for transverse common tangent it is R1 plus R2 whole square. So, these two things we must keep in mind. Okay. So, a very simple question that is asked is that suppose somebody say if square of length of direct common tangent is 100 and square of length of transverse common tangent is say 36, find product of radii. So, what we just found out the expression is 36 C1 C2 whole square is 100. If but that's it, just subtract it. Okay, so 4 R1 R2 is 60. So, R1 R2 is 60. Fine. Now, again, this is a very trivial problem, generally not expected in exams. You are generally given diagrams to deal with it. Okay. So, if you are given length of the two common tangents, then we can find what are the then from that data we can get what is the product of radii of the two circles. Okay. Now, moving ahead, what we can see is that if distance between center is R1 plus R2, so length of transverse common tangent becomes 0. So, what are the various possibilities? When is the distance between centers R1 plus R2? That is when the two circles touch each other externally. So, what are the possibilities? How can two circles be placed? See, you can see two circles can be like this, as we had earlier drawn. So, here what happened was that they were not meeting each other at any point, not So you have 4 common tangents. Now when these two circles move towards each other and this is the situation, what do we have? These two, see, if you see these two tangents, they, as the two circles move towards each other, these two tangents, they keep on, they are getting rotated and finally they coincide to become one tangent. So when C1, C2 is R1 plus R2, we have 3 common tangents. Okay, we have 3 common tangents. Please remember this. In this case, we are, if you see, what is the length AB? So here you are going to put R1 plus R2. So R1 plus R2 whole square minus R1 minus R2 whole square. What do we get? Here you see AB, the length of direct common tangent is 2 root R1 R2. Okay, this becomes, of course, these two points are one and the same, the point of contact remains same, so transverse common tangent, the length effectively is 0. Now moving ahead, if these two circles intersect each other, okay, if these two circles intersect each other at 2 distinct points, then you only have direct common tangents. So when C1, C2, distance between centers is less than R1 plus R2 and greater than R1 minus R2, we have 2 common tangents. Now if the circles touch each other like this, one lying inside the other, okay, one lying inside the other, that is when C1, C2 so we only have one common tangent. Okay. Now what is the other situation that is remaining is that if one lies inside, completely inside the other. In this case C1, C2 is, so we have no common tangent. Okay. So these are the possible situations insofar as common tangents to circles are concerned. That is, if the circles do not meet each other at any point and one lies completely outside the other, we have 4 common tangents. Okay. If they touch each other, this is what we say is they touch each other externally. Okay, if they touch each other externally, then we have 3 common tangents. If they intersect at 2 distinct points, so please remember this. This is the condition that the circles intersect at 2 distinct points. The distance between their center is less than sum of their radii and greater than the absolute difference between their radii. Okay. When they touch each other internally, distance between the center is the difference, absolute value of the difference between their radii. And if one completely lies inside the other, then this is less than mod R1 minus R2. Okay. Now suppose somebody says a question like this. Okay. Let me say, let C1 and C2 be center of 2 circles. One with radii 10, radius 10, and other with radius r. Where r is a positive integer. If C1, C2 is 15, find the sum of all possible values of r for which these 2 circles have point in common. Now see, have a point in common. I could have rephrased this, have at least one common point. See, these 2 would mean one and the same. So what are the situations that we are looking for? What is the possible situations that we are looking for? Primarily, we want circles to be like this. Okay, this is C1, this is C2, this is given to you as 15, this is 10, this is R. Okay, they could also be touching each other externally or internally. A point in common. Have meet at 2 distinct points is not the language. Have a point in common does not mean that there is only one point in common. Okay, so please keep the language of the problem in mind. Have a common point. Okay, these 2 curves have a point in common. That does not mean that there is exactly one point in common. That means that there is at least one common point. So what we are going to say is that C1, C2 is less than R1 plus R2 and greater than R1 minus 15 is less than 10 plus R and greater than So we can very easily say R is greater than 5. Okay, from this inequality. What does the other inequality tells you? Oh, sorry. So we can square it. Okay, so R is this is for this situation. Now, do we want the circles to touch? Because we want they have a point in common. So I think these two situations would also be acceptable to us, isn't it? So ideally, because we want a point in common, we should put equality sign everywhere. That would suffice. So R can be any number from 5 to 50. Okay, so sum, insofar as sum is concerned, we have 11 numbers. This is 110. Or we could have simply drawn a diagram. See, if you see, this is one circle. If we are comfortable with geometry, I would say this would be a better way. So this is 10. This is 5. With this as center, we need to draw circle. Okay. So we have to draw a circle of at least radius 5. So that we can draw a circle of larger radius, no issues. And what is the maximum possible that we can go for? Is C2 as center. This is 15. Did I make some calculation error? This is 15, sorry. Oh, this is 15 is square. This is oh, so this would put together give you R is from 5 to 25. Very sorry. This would be 21 by 2 into 5 plus 2 and 15 into 21. That is 315. Very sorry. So the maximum radius that could be is 25. Okay. So algebraically, if you make an error, you don't get to know it, even though this is a very bad error. Such error should not be made. That 15, I wrote it as 5 only. Okay. That is why I was worried. How come we got 5 here? Anyways, so this is a question that is very easy, so to say, one of the easiest problems you can possibly conceive of. Now, further, suppose we ask you a question like this. mm, suppose somebody asks you a question like this: given two circles which are touching each other, this circle passes through three cones, say let us not use coordinate geometry, say A and B are two fixed points. A circle is drawn passing through A, another circle is drawn passing through B. These two circles touch each other externally at point P. Okay, so if AB is 10, find AP square plus BP square, given that AB is common tangent to the two circles. This is our question. Okay. So, what further data is provided? We are being provided with the data that AB is common tangent. So, what is the situation? That AB, okay, fine, touch each other. So, AP square plus BP square. Now, if it turns out, say, that this angle is 90 degree, then we are through. Again, this is not the solution to the problem. What I am saying is that if this turns out to be 90 degree, our issues are solved. Okay. So, primarily what we are going to do is that we are trying to find the angle at this point. These two angles are of course 90 degree. Okay. Now, if this is theta, this is 90 minus theta. Okay. This is theta, this will also be theta. If this is phi, this is 90 minus phi, and this is phi. What is this angle? 90 minus theta, 90 minus phi. So, this is going to be theta plus phi. Now, you can see 2 theta plus 2 phi is 180 degrees. So, theta plus phi is 90 degrees. Okay. That means what is the situation? The situation is like this. Now I think this is known to us. So AP square plus VP square, you can very easily say, is nothing but 100. So one thing that you can keep in mind or probably remember is that if the two circles touch each other externally, then their direct common tangent subtends a right angle at the point of contact of the two circles. Okay, at the point where the two circles touch each other. Again, we should be vigilant enough, we should have the wherewithals to write these 3-4 lines. You can see it is not a very typical ask that we are going for. Okay, this is something that we should be able to do it very easily. Further, we can say since this is 90-degree, circle with ABS diameter will pass through point P. So, these are the things that we can expect. Now, moving ahead, if you see, suppose you are given two circles, okay. I am not deliberately writing the languages of the problem, I am drawing the diagram itself, okay. Suppose you have two circles like this. And we have their direct common tangent. And so this is a smaller circle. Okay. Suppose this is R1 and this is R. Say R1 is greater than R2 and this is small r. So we have to find R. So what is the language of the problem? The language of the problem is that two circles touch each other externally and they are also tangent to a line. A third smaller circle or say a third smaller circle is drawn touching the two circles externally and also their common tangent. What is its radius given that the two circles have radii R1 and R2. So, I think direct common tangent notion can be used. What is AC? What is the length AC? We just have seen that it is when the circles touch each other externally, the length of direct common tangent is 2 root R1 R2. So, what is AC? What is BC? And what is AB? So, AB is AC plus DC. So, you have okay. So, what is the situation? We divide it by say root R1 R2 root divided by root R root R1 root R2. So, what you will have is that 1 upon root R is So, what is R? I think you can very easily see is this is the radius. Now, I was given a smaller circle. Otherwise, what would have been the situation? Suppose you would not have been given a smaller circle. What are the possibilities that we could have seen? See, these are two given circles. Suppose the word smaller had not been used. Okay. R now, had this not been the case, we could have drawn a circle like this if you are able to fathom. Okay, something like this. Very large circle. Let me draw the diagram properly. These two circles have turned out to be too big. Suppose this is R1 and R2. So we would have drawn a circle like this. Okay. This two is satisfying both the conditions. So here what we would have had is 1 upon root R. So subject to the given situation, had the problem not been specifically stated as find a smaller circle, we would have had two circles. We would have had two circles like this. Okay. Just wanted to know generally what happens is that you are given the diagram and we just write this, but we should be able to conceive the fact that there are two such possibilities. Okay. Now let me come up with one more problem. C1 and C2 are two circles of radius 10 and 6 respectively. Such that these two circles have three common tangents. such that these two circles have 3 common tangents. Okay. Now, in circle of the triangle formed by common tangents C1 and C2 is drawn, and let R be the radius of this incircle. Find the value of R plus 6 upon 10 minus R. ठीक? So this is our question. I have just framed the question. Now what is the possible situation? When do two circles have 3 common tangents? When do they have 3 common tangents? We have just seen it is when they touch each other externally. So, if they touch each other externally, what is the situation that we have? This is the situation. In this case, we have two direct common tangents. And one transverse common tangent. Now, just look at this diagram. I think this completes the solution, isn't it? If you look at it, the smaller of these two circles plays the role as incircle of this triangle. These are the tangents. So, this is smaller circle is playing the role of incircle of this triangle. So, what can very easily be seen is that R is nothing but the smaller of these two, which is 6. 10 is radii of one of the x circle. So, this is a very simple question. 6 plus 6 upon 10 minus 6. That is 3. Isn't it? Okay. So, just by drawing an appropriate figure, we got to the crux, or we actually got the solution. So, if you are trying to find the incircle, you should understand the tangents, the 3 tangents are touching the circles. Okay, the 3 tangents are touching the circle. So, these two circles will effectively be either the incircle or the excircle of the triangle that is formed by these tangents. The smaller one is the incircle and the larger one is one of the excircles opposite to say Q. Isn't it? So, just looking at this, we can possibly fathom this rationale. Oh. what more we can think of related to problems regarding this? Now, let me take you to a problem which has very often been asked in various examinations. Earlier, it has been asked in KVPI also. Question of similar nature. Okay, IOQM, JE, or KVPI, NTSE. These problems based on simple notions could be asked. They have been, I think the problem that I am taking has been somewhat asked in these examinations in one way or the other. May not literally be the problem that I am discussing it, but in terms of the idea that the examiner wished to ask, it is the same. So, what we are given is, let me write the language so that you draw the diagram. Okay. For my own benefit, I generally draw the diagram so that that part at least can be excluded. But in examinations, that will not be the case. You will be given statements and you draw a diagram on your own. So, because we are in conversation, this is a lecture, we have been in conversation. So, just to save time, on some occasions or effectively on lot of occasions, I have taken the liberty to draw the diagram and then explain you the problem. Generally, it is the other way around, because we are in conversation with each other. We have taken certain liberties, but the examiner will be in conversation with you for the first time. So, you should be good enough to grasp the situation given in the problem, comprehend it and draw appropriate diagrams. Generally, I see diagrams are very rarely drawn. Okay? You have to draw it on your own. But drawing a good diagram in geometry is on most occasions effectively, in my opinion, half the solution. Okay? So, just understand, therefore, you should definitely practice previous year problems or problems from standard text and books, so that you get to know that how do you comprehend from the given language, from the given data, an appropriate figure, a proper diagram, which will lead you to solving the problem. Now, insofar as this question is concerned, let me say that let C1, C2, C3 be circles such that circle Ci externally touches Ci minus 1 and Ci plus 1 for all I equal to also. R1, R2, R3 are radii of C1, C2, C3 respectively. Further, R1 is equal to 1, This is our problem. Find n given that there exists a line L tangent to all the circles let me write this also. It is given that it is given that centers of C1, C2, C3 are collinear. This is how generally questions are given. Okay, I may have not written it properly. As the question came to my mind, I have tried to provide you with the information, language, but generally a very typical language is used, mathematically precise language is used, so that nothing is left ambiguous. I could have simply drawn the diagram and told you that find this, okay. But now this is how generally you see the problems that occur in examination. So what is the question saying? Let C1, C2, C3, C4, Cn be circles such that circle Ci externally touches Ci minus 1 and Ci. So C2 touches C1 and C3 externally, C3 touches C2 and C4 externally, okay, C4 touches C3 of course and C5 externally, and so on. Cn minus 1 touches Cn minus 2 and Cn externally. Also their radii C1. Further, you are given radii of 2 of these circles, you are given sum of the radii, and you have to find the number of circles. What other data is provided? That there is a line which is tangent to all the circles, and centers of these circles are collinear. So what is the possible situation that you are reckoning? So what is the possible situation that we are reckoning? Look at it. There is a line on which all centers of all the circles lie. These circles, the information which is provided at the last would be the initiating one, I think. Say first circle, first circle is of 1 radius, then you have C2 which is touching this one externally, okay. And what is given is that there is a line which is tangent to all of them. You can possibly easily understand that it cannot be the transverse common tangent. It has to be a direct common tangent, okay, something like this. In fact, if there is one line, you can say that there will be one more line. This line bisecting the angle. Okay. Now, and then we can keep on drawing. So, this is the situation. So, first and foremost, from the given data, are we able to draw the appropriate figure which would help you out. Now, what to do? Okay, you are given R1, 2, 3, 4. Let me draw one more. And we can keep on drawing. Now, what to do? I think you can understand here, just as we saw while proving that external common tangent divide the line joining the centers externally in the ratio of radii. So, we can deal with similar triangles, stuff like that. Okay. Suppose I say this point is A, C1, C2, R1, R2. Okay. So, we can say AC1 upon AC2, AC1 upon AC2 is R1 upon R2, isn't it? Now, this angle AC1 upon AC2, okay. So, how can we proceed further? Now, this angle you can say, this angle is fixed, okay. This angle theta is fixed, isn't it? There exists a line L and C. So, angle between the tangent to all these circles and the line on which center of these circles lie, this angle is fixed. So, AC1 upon AC2 is R1 upon R2. Now, basically I am deliberately trying not to incorporate trigonometry, okay. Otherwise, we would have, since it is a right angle triangle, but I think sin theta cos theta is something that you might very easily be aware of. So, let me use that, okay. AC1, what is AC1? AC1 is R1 by sin theta. And what is AC2? It is AC1, that is R1 by sin theta plus R1 plus R2, because the circles are touching each other externally. Now, we can very easily see that this is also equal to R2 by sin theta. Theta is fixed. So, what does this give you? R1 into 1 plus sin theta is R2 into 1 minus sin theta. So, what is R2 by R1? And so will be R3 by R2, so will be R4 by R3. So, this, since theta is fixed, this ratio is fixed. That means the radii of this circle, the radius of these circles are in GP. This is a fixed ratio because theta is a fixed number. Okay, if that common ratio is R, you are given R5 is 16, it is R1, and let the common ratio be, say, capital R. R1 is given to you as 1. So capital R is 2. Somebody may ask you theta also. What is theta? I think you can find 1 plus sin theta by 1 minus sin theta if it is 2. What is theta? But here the question is if so the common ratio turns out to be 2. Okay. Now what you are given is that sum of all the radii is 4095. Okay. So 1 plus 2 up to 2 raised to n minus 1 in fact. So this is 2 raised to n minus 1 upon, this is given to you as 4095. So 2 raised to n is 4096. So this is 4096. 64 square. 1024 into 4. So number of circles is 12. Okay. So this lecture completely covered questions regarding common tangents. Now other things about circles we will read as we move on. In today's lecture what we are going to do is some remaining stuff of circles, Ptolemy's theorem, and moving ahead to say polygons, okay, especially regular polygons. So now let me start with Ptolemy's theorem, okay. I think Ptolemy's theorem is something that we So what does Ptolemy's theorem states? That in a cyclic quadrilateral, the product of opposite sides, the sum of product of opposite sides is equal to product of the diagonals. What is the theorem? The sum of product of opposite sides, that is say AB into CD plus AD into BC is equal to product of diagonals AC into BD. This is the theorem named after the mathematician Ptolemy. It will help you in solving lot of situations when quadrilaterals are involved. Primarily it is helpful in length chasing. If you are asked regarding length, some of the data is provided, some is not provided. But as always, the first thing that we are going to do is just to establish it. Just remember basic, there are a lot of ways to prove it. One way is that what we do is that we draw a line. Yeah, we take a point, say P. Let me change the color. We take a point P on BD and join AP. Just appreciate the manipulation that is being done, okay. We have taken a point P in such a manner that these two angles are equal. Okay. One of these two angles would be larger. We are assuming that this one is larger, BAC. Now we are saying, now take a point P and draw a line like this such that these two angles are equal. Now what does this does? if you are able to see this angle is the angle subtended by chord AD is equal to this angle, isn't it? Angle subtended by chord AD at the circumference. So, these two angles are going to be equal. Fine. As a consequence, this angle BPA and this angle, they are going to be equal. So, what you are getting is triangle ABP triangle ABP is similar to ABP is similar to triangle ACD, isn't it? Now, if you see carefully, and therefore, what are you going to say? AB upon AC is equal to BP upon AD is equal to BP upon CD. Or rather, what we do is that let us write it like a AB into CD. This is what we are looking for is AC into BP. Let us call this as our first expression, okay, first equation. Now, you are able to, I think now you are able to fathom what we are going to do next. Now, if you are able to see this angle, watch very carefully, this angle and this angle are equal. Are you getting it? Say if this is some theta, this is alpha. So, this pink angle is theta plus alpha, this is theta, then this pink angle is also theta plus alpha. So, these two angles are equal, and similarly, what we can say is that this angle subtended by chord AB. Okay. So, as a consequence, the third angle here they are similar, they are equal. Hence, the triangles. Now, let us write again which two triangles are similar. A, B, C and A, P, D. The triangle APD is similar to triangle APD is similar to triangle ABC. So, therefore, what we can now write? BC. BC BC. Let us choose properly. Triangle AD. AD upon opposite to this angle is AD, opposite to this angle is AC. AD upon AC. See, we have already got BP, not what we want is PD, and PD is opposite to this angle is BC. AD. Okay, so it will be PD upon BC, meaning thereby AD into BC is AC into PD. Okay, so by 1 and 2 you are able to see AB into CD plus AD into BC. What is it equal to? AC into BP plus PD. What is BP plus PD? BD. So this is what our Ptolemy's theorem is. Again, this is why I have always insisted that you should all try to prove things, for the simple reason that once we are aware of it, once we make use of these, once we get accustomed to the proofs, what helps, it largely helps you in dealing with problems. See, a beautiful construction was thought of to justify it. I am not saying that this is the only way, there are other ways to establish it, but using pure geometry we have just considered a point. So, later on in problem solvings, this thing can be thought of. There can be points of time where in dealing with a problem you consider a point, let us consider a point such that this angle is equal to this angle, and then we have proceeded. So, it has given you one way to explore a possible geometrical situation. So, always try to remember, to recall how have we initiated the proofs of the basic theorems that we have encountered right throughout geometry. That will give you a very good platform to start solving problems. Because what is the general thing, what generally occurs is that we are not able to initiate. We may know a lot of facts regarding certain, regarding circles, regarding triangles, regarding quadrilaterals, but based on a certain piece of data, how do we initiate the solution in such a manner that we get the desired things. It is not possible that if I know 10 facts about circle, I do it one by one always. So, therefore, it is very, very, very important. I am probably for the 100th time in last few lectures I am saying, always remember how we started the proofs of the theorems that we have gone through, so that you have various ways of initiating the problems. Okay? Now, this is the theorem. Now, what are few problems that we can do regarding it? Say, so the question is, if ABC is an equilateral triangle and P is any point and P is any point on arc, say AB. On arc AB. Sorry, let me write it properly. On circumcircle of triangle ABC lying on arc AB. Find, let me make it a numerical problem. Find PA plus PB upon PC. P does not coincide with A, B, C. Okay? So let me draw an appropriate diagram. Whenever you have to draw circumcircle of a triangle, draw a circle and inscribe a triangle in it, rather than drawing a triangle and then circumscribing a circle about it. Okay, now we have taken a point P on it. So, PA PB, we are being asked to show that PA plus PB is PC, isn't it? Now you can see PACB is a cyclic quadruplet. So therefore, by Ptolemy's theorem, by Ptolemy's theorem, what can we say? See, product of opposite sides, AC into PB plus BC into PA is equal to product of diagonals. What is it equal to? Product of diagonals. What is that here? AB into PC. So, since it is an equilateral triangle, PA plus PB is PC. So, this is what have we got. Now, insofar as the question is concerned, answer is 1. Well, we could very well have thought it that if P coincides with A, PA is 0, PB and PC are equal. Okay, that is one way we could have done it, you know? But just an application of Ptolemy's theorem. Moving ahead, suppose, let me take one more problem, you know. Say, find the ratio of length of diagonal to its side in a regular pentagon. Regular polygons we have taken up, we will take up as we move ahead, even hopefully in this lecture only. I'll try that we take up in this lecture only, but I think regular quadrilateral is square. Regular pentagon means a pentagon, all whose sides and all whose angles are equal. Now, in case of a pentagon, if you see, I am drawing its circumcircle, okay, and what I am saying is that See, all its sides are equal in length. All regular polygons have a circumcircle, followed by, see, if you look at its diagonals carefully, this is a diagonal, okay. This too is a diagonal. You can see by symmetry that these two diagonals are equal in length, and so will be the other diagonals. So, if these lengths are y, okay, we can draw one, say, some more diagonals. That is not a big deal. Say, let me draw one more diagonal. This will also have length y. Now, if I think you are able to conceive what we are going to do. We are going to consider a cyclic quadrilateral. Say I consider the quadrilateral A, B, C, D. Okay. Consider A, B, C, D. Quadrilateral A, B, C, D. So, by Ptolemy's theorem, what we have? AB into CD, sorry, AB into CD plus BC into AD is equal to AC into BD. Now, as with every diagonal, so with this diagonal, this length is also y. See, you are able to see the symmetry, isn't it? If for this diagonal, there is one vertex to the left of it, two to the right of it. Draw a diagonal. There will be one vertex on one side and two on the other side. Just by symmetry, I am saying they are all of equal length. So, AB is x, so is CD. BC is x, AD is y. AC is y, BD is y. To its side. So, we have to find y by x. So, dividing it by x square, what do you get? The golden ratio. This is the answer. So, what is to be kept in mind is that not only square, in square also both the diagonals are equal in length. There is one more regular polygon in which all the diagonals are equal in length. Okay. Square and pentagon are two regular polygons. Square and regular pentagon are two regular polygons in which all the diagonals that you draw are of equal length. You can see in pentagon you can draw 5 diagonals. I have drawn 1, 2, 3, 4. One diagonal you have drawn. You can draw 5 diagonals. Okay. So, this is how we use Ptolemy's theorem. I have taken rather simple examples. As we move ahead, we are going to take some good problems where Ptolemy's theorem would be utilized, especially in case of circles. If we are dealing with length of sides and diagonals in a cyclic quadrilateral, it plays a very important part in dealing with problems of that nature. Fine. Now, one or more important things that we need to know. Once in a while you may come across circle of Apollonius. it says if A and B are fixed points and P is a moving point such that PA upon PB is equal to K not equal to 1, then P lies on a circle. PA by PB is a constant. This circle is called circle of Apollonius. Again, a very fantastic geometric problem. There would be other algebraic ways once you go through coordinate geometry to deal with them. But in geometry, it is done fantastically by angle bisector theorem and stuff like that. We will find what the radius is, what the center is. Okay. So, what we are given is that PA by PB is K. Now, suppose, so let me draw the diagram in a separate page. Suppose A and B are, you are given that A and B are two fixed points. Okay. This is some point P. PA is to PB is K is to 1. Now, on segment AB, suppose this is 2 is to 1, for example, there will be a point Q which divides AB in the ratio 2 is to 1. And there will also be a point R such that this will be equal to AR by RB. Okay. So, what we are saying is that we can also take our point P to be this point, we can also take our point to be this point. Now, by angle bisector theorem, what we can say is that if PA by PB is AQ by QB, then PQ is the angle bisector. Angle bisector divides the opposite side. Angle bisector divides the opposite side in the ratio of sides containing the angle. So, therefore, Q must lie on the angle bisector of APB. In similar vein, we can extend and say that the external angle bisector divides the opposite side externally in the same ratio. That means, say, now we know, what do we know? We know that the internal and external angle bisectors, internal and external angle bisectors are internal and external angle bisectors are mutually perpendicular. They are mutually perpendicular. That, see, Q is a fixed point on AB, R is a fixed point on AB, and what we are getting is that angle QPR is always going to be 90 degree. So, what have we read? Angle in semicircle. Angle in semicircle is a right angle. So, therefore, Q lies on circle with P lies on circle with QR as diameter. Fine. So you have to think in a slightly nuanced and a different way while dealing with problems of geometry. This is called circle of Apollonius. You can say midpoint of QR, whatever that point is, S. Midpoint of QR is the center, and what is its radius in terms of AB and K? So we can say that see, what is this length? AK is to KB is, AK is to QB is K is to 1. So K by K plus 1 times AB. Okay, and this is 1 by K plus 1 times AB. Now AR, what is the AR is to BR, you can say AR upon BR is also K upon 1. So subtract AR minus BR upon AR, we have to find B upon BR is, what is AR minus BR? AR minus BR is AB. So what is BR? AB upon K minus 1. We are assuming K is greater than 1. So BR is 1 by K minus 1 times AB. So radius of the circle this distance AB, what is this distance? Now if you add 1 by K plus 1 by K minus 1 is 2K by is K upon and K is greater than 1. Okay. So this is what you are going to get. Again, it is a beautiful combination of two things. One, the angle bisector theorem, and the other, the angle in semicircle is right angle. By combining these two, you are able to do it. Okay. This is something that we will, as we move on, be required to utilize in solving problems. There are various things that we have accumulated in our study of geometry, especially in these classes, and also prior to it when you have gone through your regular school classes. A demanding problem or a problem which requires a bit of ingenuity are those problems where they combine 2 or 3 notions, 2 or 3 generally known and utilized notions in a single problem, and that creates an issue. How to start, how to initiate. Okay. Now, don't try to remember it. If you have the ability to recall how are we getting to this point, then we have ample time in exams like IOQM to come to this point. Okay. So generally somebody may ask you what is the radius and stuff like that. Okay. Just I wanted to make you all know this fact also, because it's a beautiful combination of angle bisector theorem that we have read in triangles and this. Fine. Now moving ahead, let me give you a question. Okay. quite unrelated to this, to stuff that we have gone through. Just I was going through something, you know, and I found a problem which said related to circles, and then I will come to something called radical axis. Okay. So, what we are given is that we are given a diagram. Let me draw the diagram. And common chord of these two circles is also drawn. Centers O1, O2 is given. So, let this be A, let this be B. Now, we are given a point P on this line, and from this point P we are being told that tangents are drawn to these two circles. So, these points are Q, R, and say this is M. Okay, since it is the common chord, okay, line joining the centers will be bisecting. Fine. Diagram I have this 90 degree need not be given. The question said if AM is equal to 2, AP is equal to 4, find PQ. Find PQ plus PR, because that is common to all of them. This is our question. Okay. So, how do we proceed? This angle is 90. We simply draw PO1. Okay. So, we can say if this radius is R1, what can we say? O1P whole square is PQ square plus R1 square. Okay. Further, in this right angle triangle, we can say this is equal to MP square, is it not, plus O1M whole square. What is O1M whole square? This is also R1. So, you can say PQ square plus R1 square is MP. MP, I think length is given. AM is 2 and AP is 4. So, this is 36. What is O1M whole square? O1M whole square is R1 square minus AM square. Is it not? What is O1M square? R1 square plus AM square. R1 square gets cancelled out. What you get is 36 minus AM square. What is AM square? 4. This is 32. PQ square. So, PQ is 4 root 2. Now, if you are able to fathom that we are going to have similar calculations here. Is it not? We are going to have similar calculations here. This is 90 degree and I am going to say PO2 is, I think I am not writing it, O2 P whole square is PR square plus R2 square. It will be equal to MP square minus O2 M square. We will write R2 square, R2 square will get cancelled out. So, what we learn is PQ is PR. So, PQ plus PR is 8 root fine. So, this is what we have. So, this line, the common chord in a circle is called radical axis of these two circles. Okay. Length of the tangent drawn from are equal. If you keep this in mind, it might on occasions be of help. In the case the two circles are intersecting, it is nothing but the common chord. Of course, from a point inside you won't draw circles. That to generalize it, what we say is to generalize from point inside, you can say how can you draw a tangent. So, to generalize it, what we say is that radical axis is set of points whose power with respect to two circles are equal. What is power? I hope you are able to recall. I believe I have told you once. If the point is outside or inside, the expression is same. If this is O P, so power of point P, say this circle is some omega. So, power of point P with respect to omega is equal to OP square minus R square, where R is the radius. So, what happens is that if the point is outside, you can say OP square minus R square is length of the tangent. Of course, if it is inside, and if it is inside, then this is not the length of the tangent, okay. But if it is outside, it is length of the tangent. So, PA into PB, if you remember, PA into PB is PT square, we proved that. That is power of the point, PA into PB. For internal point 2, we say PA into PB is equal to the power But then what happens is that for an internal point we talk about sensed magnitudes. Okay, if this is PA is positive, this PB we say is negative. In that case it works. For internal points, PA minus PA into PB will be R square minus OP square. What I am trying to say is that suppose there is a point P inside and you draw a chord like this. So I hope you PA into PB we have already gone through is PC into PD, is it not? Now, if P is the midpoint, O is the center, so what is PC? What is PC or PD? This is R square minus OP square. We may say it is OP square minus R square if we say, suppose if this side is positive, PD is negative. That is called sensed magnitude, we do not get into it. But even when the point is inside the circle, this is useful. And therefore, if the point is inside the circle, we say power is negative. We always take power to be OP square minus R square. So, if the point is inside, it is negative. If the point is outside, it is positive. So, for outside points, what do we get? For outside points, what do we get? That the root of power is nothing but length of tangent. And thereby we say if the two circles are intersecting, their radical axis is the common chord. Radical axis, in fact, you can understand very easily, I think, that power of this point is going to be these points where they meet. So, our radical axis has to pass to this. Incidentally, it is a useful thing for the simple reason that incidentally they are nothing but, it turns out to be nothing but a straight line. So, there will be other properties of a straight line that we will be required to use. It is a straight line that makes the whole situation fascinating, okay, which is perpendicular to the line joining the centers and stuff like that. In algebraic geometry, coordinate geometry, you will see how it is utilized in different manner. Okay. Now, in so far as the theoretical content is concerned, we have tried to cover almost everything. Angle between the circles or orthogonal circles are when the angle is 90 degree. So, angle between circles, but for that we will need trigonometry. Let me only tell you orthogonal circles. And then any arbitrary angle we will take care of later. Even at the point of contact, tangents pass through centers. Okay. If somebody is asking you to find the length of the chord, you can very easily find it. Orthogonal circles, that means the circles, the tangents, the normals or tangent, the radii at the point of intersection are perpendicular. This is what orthogonal circles would mean. That means the radii of this circle would be tangent to this one, and the radii of this circle would be tangent to this one. What you can see is that if somebody asks you to find the length, you can very easily find it. I hope I am very clear. Area would be half R1 R2 is half, suppose this is PM into O1 O2. So, PM is R1 R2 upon O1, O2. So, length of the chord PQ is going to be, see, these are all problems, you don't have to remember these results. Draw a diagram, draw a worthwhile diagram, 90-degree stuff, and you can come across these things. I wanted to take up polygons today only, but I thought that the time did not, that the time available was not good enough. So instead, I told you something about circle of Apollonius, then radical axis, and then orthogonal circles. Next class will deal with polygons and circles related to polygons, then something about trigonometry. I hope you know the basic definitions of trigonometry. We will extend it and see that how it is utilized in problems of geometry, because geometrical intuitiveness on occasions is very demanding, just like if you recall the proof of Ptolemy's theorem, circle of Apollonius, those stuff required a bit of ingenuity, a knowledge of how things work. Probably you may have a perception that you can only deal with them if you know them beforehand. So that sense takes time to develop. If we start using algebra, trigonometry, on occasions we are more accustomed and used to it, and therefore what you find is that when you use them, because we use the algebra in almost every domain, you feel more comfortable, and you also have additional tools to deal with the situation at hand, whether it is geometry or anything else. So at this, what we have gone through till date is almost most of the part of pure geometry. The only part that is remaining is a bit of say polygons, and then we will move to trigonometry, so that some of the questions that are very demanding in trigonometry can be used by using algebraic methods of trigonometry. So I am telling you some normal stuff related to polygons, and generally we will confine most of our discussion to regular polygons. Polygons as such are convex or concave. Convex polygons means all the interior angles are less than 180 degree. Concave, you will have say something like this. This is a concave pentagon. So one of the angles, this is called the reflex angle, is greater than 180 degree. As such, a concave region is a point such that segment joining any two points lies completely inside it. This is not a convex region, because if we take these 2 points, the segment joining these 2 points will not be completely lying inside the region. So this is a convex region as such. So this is a convex polygon. Mostly we concern ourselves to regular polygons. Okay, so let us now discuss something regarding regular polygons. Triangle is a regular polygon, square is a regular polygon. Okay. So a regular polygon means all sides and all angles are equal. In triangle, angles implies sides equal implies angles equal. That is not the case. Even in a quadrilateral, you can say a rhombus is not a square even though all its 4 sides are equal. A rectangle is not a square even though all its angles are 90 degrees. So post a triangle, regular polygon, would all angles of a polygon are equal may not imply it is a regular polygon. All sides of a polygon are equal may not imply it is a regular polygon. Sides as well as angles need to be equal if you want it to be a regular polygon. Now some very elementary facts that we need to remember is that sum of interior angles polygon is n minus 2 into 180 degrees. That is, if you want to write it in radians, it is n minus 2 into pi. So, how do you justify it? So, this is okay. So, if you take a point inside and draw all these triangles, what do we get? We get n triangles. Here, as we have drawn a hexagon, we have 6 triangles. Angle at the center is 2 pi, and since we have n triangles, sum of the angles at the vertices of all these triangles is going to be n pi, out of which 2 pi is here. So, the sum is n minus 2 pi. So, interior angles of a regular polygon, what will it be? All the angles are going to be equal. Pi by n. Fine. Sum is n minus 2 pi. A very good question of this appears in say NCERT also, insofar as sum of angles of a polygon is concerned. It is a beautiful problem. We will take it up as we move ahead, because that is not a regular polygon as such. Okay. So, interior angle of a regular polygon. Now, regular polygons have incircle as well as circumcircle. See, let me draw a circle, and for simplicity, let me draw hexagon, say a regular hexagon inside it. Okay. So, it also has an incircle. So, regular polygons have incircle as well as circumcircles. Now, at the center, they all are going to subtend an angle of 2 pi by n, because all the chords are equally in length. So, in a hexagon, it is going to be pi by 3. So, angle subtended by sides of a regular polygon at its center is 2 pi by n. Further, exterior angle of a regular polygon, if you see, this is the exterior angle. The exterior angle is 2 pi by n, you can see. Subtract this from pi minus this. So, you have 2 pi by n. Also, if its side, suppose the side is A. So, I think you can very easily understand what is its sorry, this angle is going to be pi by n. So, if this is capital R and this is small r, this is A by 2. So, by simple trigonometry, I think you will be able to get perpendicular upon base, perpendicular upon hypotenuse, base upon hypotenuse. I think you can all get it. So, small r in radius, what it is? This is A by 2. So, tan theta is A upon 2r. So, r is tan theta and pi by n. So, tan pi by n is A upon 2R. R is capital R. You can see sin theta is A by 2R. Is A by 2 cosec pi by n. Okay, where A is side of regular polygon. What other data we may possibly remember is that as we study trigonometry, we will be able to see lot of other facts using trigonometry. As you can see, this is very simple trigonometry, so I directly wrote it. But as we move on, we will come across different formulae of trigonometry, which will give us different other results, which is going to be very, very helpful. Area, you can find area of a polygon is nothing but if you find area of one triangle and simply, so area is half is n times half base is A. What is height? Height is small r. Okay, what is small r? In fact, any polygon having an in radius, this is going to be delta upon S. Area upon semi-perimeter. Small r is always this. If a polygon has a in circle, this is what the expression is, as in the case of triangle. Okay, so these are some facts regarding regular polygons which we must be aware. Now let me pose a question regarding regular polygon, okay, or simply polygon. This is a problem from NCERT. It's a good problem. The smallest angle of a polygon is 120 degree. Its angles are in AP with common difference of 5 degree. Fine, with common difference of 5 degree. Find number of sides of this polygon. Find number of sides of this polygon. So, sum of the angles of polygon. What is sum of the angles? We just went through it is n minus 2 into pi, where n is number of sides of this polygon. Now we can find sum of an AP, n by 2 into 2a, 2a is 240 plus n minus 1 into d, which is 5. So this is so 5 4 ja, and then this is 5 36. Okay, so n into 47 plus n. 36 into 2, 72. So, what is the quadratic that you get? N is square, 72 minus 47, minus 25n plus, so you get 16 and 9. Now, if n is 9, the angles are 120 degree, 125 degree, and what is the largest angle? 120 plus 40, 160 degree. If n is 16, 120 degree, 125 degree, and what will be the largest angle? 15 into 5, 75 plus 120, 195 degree. Are you able to understand the situation? See, prior to it would be 190 degree, prior to it would be 185 degree, and prior to it would be 180 degree. So, sides cannot be such. You cannot have an angle of a polygon equal to 180 degree, and therefore 16 is ruled out, and the answer is only 9. Okay, so it's a problem that incidentally appears in NCERT, and it's a beautiful problem. We must understand why we are rejecting 16. It is not the case that this formula holds even when the polygon is concave. So, the sum of angles being n minus 2 into pi holds even when the triangle is even when the polygon is concave. This 16 is not rejected because the polygon turns out to be concave, but because one of the angles in that case turns out to be 180 degree at, but no angle at the vertex, otherwise it will be the same line. Okay. Now, moving ahead, let me give you a question like this. Okay. We have read Ptolemy's theorem, so let me use Ptolemy's theorem also. Let A be the site of a regular heptagon. If B and C are length of its diagonals B not equal to C, find the value of lambda such that 1 by B okay. Can you think about it? Okay. Now, you are given a regular polygon. Heptagon, okay. Let me draw it. So, this is the regular heptagon, suppose, okay. So, what are C? You can understand possibly that the possible length of the diagonals are C. And I hope you are able to reconcile to the fact that this diagonal, suppose this is A, B, C, D, E. AD and AE are of equal length. F, G. And AF and AC too are going to be of equal length because of the symmetry. Means I think very easily understand. Okay. Now we have to show, we have to effectively find, if you see what is lambda. Lambda is A into B plus C upon BC, isn't it? So this is say B, C, C. What will be this length? This length too is going to be B. These sides are A. So if you consider quadrilateral, see ACDE is a cyclic quadrilateral, isn't it? It is a cyclic quadrilateral. What do we get here? By Ptolemy's theorem, AC into DE plus CD into AE is equal to AD into CE. AC, what is AC? C into DE, A, CA, CA we have got, CD, A, AE. AC is B, sorry, AC is B, BA we need notice. CD, A, AE, C, AC, BA plus AC is equal to AD, C, CE, B. So what you get is, in fact, if you divide by AC, what you get is 1 by C. This is the relation between sides and length of diagonals of a heptagon, and therefore we can safely say lambda is nothing but 1. Okay. If you remember, this is the thing associated with a heptagon. Okay. Fine. Now, say let me take a question like this one. Okay. I have a collection. You are given a regular 7-pointed star. One, two. Okay. So A, B, C, D, E, F, G is a regular 7-pointed star. Find this angle theta. We have to find this angle theta. So, as such it is vertices of a regular polygon. Okay. And okay, let me draw it like this. Okay, so let us give the nomenclature A, B, C, D, E, F, G. So, draw AD. BF. In fact, this is the angle we are looking for, isn't it? Now, you can very easily understand that each of these vertices, each of the vertices are equally, the vertices are equally placed along the circumference. So, all the chords are of equal length. So, all the chords are going to subtend equal angles at the circumference, isn't it? So, it is 1/7, 1/7, 1/7, 1/7, 1/7, 1/7 and 1/7. So, what is, suppose somebody says what is AEB? Can you tell me what this angle will be? 1/7 of the angle pi. So, this is going to be pi by 7 and this is going to be pi by 7, isn't it? And this is going to be pi by 7. Fine. Now, if this angle is theta, I hope you are able to understand this is also theta. Now, can you let this, no, let this angle is say phi, this is also phi. Now, can you tell us what is this angle theta? See, area angles of triangle AB you can say is 2 phi plus 3 pi by 7 and angle of triangle say ABM is theta plus 2 pi. So, theta is nothing but 3 pi by 7. These sort of questions you can expect in examinations. We can take some more demanding questions also, okay. But you see, even in the case of regular figures, pentagons, hexagons, heptagon, octagon, it takes time to deal with them because we are generally could be dealing with problems of say quadrilateral or triangle we are well versed with, okay. In quadrilateral, post quadrilateral, it is always a ad hoc exercise barring the cases when we deal with regular polygons. Otherwise, it will always be an ad hoc exercise depending on the situation, what possible triangles, quadrilaterals can we fathom. As in the previous question, we used Ptolemy's theorem, making an appropriate quadrilateral. Here also we said because it is a regular 7-pointed star, that means the vertices are regular polygons, okay. This to me, I think this is a reasonable problem. Let us do one more problem, okay. I do not exactly remember the data, okay, this is how I get it. And just look at the beauty of this problem. Let A, B, C, D, E, F be a regular polygon, sorry, a regular hexagon of area 1. Let M be the midpoint of DE. Let X be the intersection of AC and BM. Let Y be the intersection of BF and AM. And let Z be the intersection of AC and BF. If P denotes area of polygon P, evaluate area of triangle BXC plus area of triangle AYF plus area of triangle ABZ minus area of MXZY. This is the problem. Read the problem carefully. Area of a hexagon you can form, if you see hexagon, angle at the center is 2 pi by n, so that is pi by 3. So all the 6 triangles that you form, they will turn out to be equilateral triangles. So in that case, polygon case of hexagon, a regular hexagon calculation can be dwelled into stuff of triangles, in fact equilateral triangles. Now let me draw the figure A, B, C, D, E, F. DE, DE इधर ही रखते हैं, DE बेस पर रखते हैं, ठीक रहेगा, टेढ़ा मेढ़ा लगेगा नहीं तो. Isn't it? M is the midpoint of DE. AC and BM. AC and BM. This is X. BF AM. BF, BF, AM. This is Y. The AC, BF, AC, BF, BF, AM. Why be the intersection of BF, AM? Okay. AC, BF. This is Z, okay. Fine. So we have to find BXC, BXC, okay, this AYF, AYF, ABZ probably, you know, ABZ. And then we have to subtract MZ, MXZY. Okay. We have to find area of these three triangles and then subtract it and subtract this part. So, this is delta 1, delta 2, delta 3, delta 4. So, what we have to find? Delta 1 plus delta 2 plus delta 3 minus delta 4. Now, look at it carefully. Okay, fine. So, insofar as a regular hexagon is concerned, please have these things in mind, okay. Suppose this diagonal. So, if you draw these two perpendiculars, if this side is A, this is 90 degree, this is 90 degree, so this angle is going to be 120 minus 90, 30 degree. This is 60 degree. So, this is A by 2, this is A, this is A by 2. Further, if this is 60 degree, you can understand. So, these two are parallel. Okay, so the longest diagonal is 2A. You have one more diagonal. Since suppose this is the okay. If we draw AD or BE or CF, they will be the longest diagonals. Okay. Now, and the longest diagonal will be parallel to it. So, if these sides are A, we can find, and we can say BE is twice that. We can also find length AF if need be. Let me tell you that also. Then we will solve the problem there. I am deliberately avoiding complex trigonometry, only Pythagoras I am using, or sine 30 degree, sine 60 degree, that is all. Suppose I want to find length of this diagonal. So, what do I do? This is A, this is 60 degree. So, this is A by 2, this is A. By Pythagoras, what do I get? A root 3. So, if you want to find length of the diagonals, we can easily determine in terms of sides. Sides you can very easily find because you are given area of this hexagon, but that will be a very tedious exercise. Okay. So, we have to find delta 1 plus delta 2 plus. Now, we can say, see, think of it very carefully. is say area of this ABCDEF. Minus area of, say I will subtract this whole thing and this whole thing, area of BMEF. Okay, so this is subtracted, so this remains and this remains, minus area of ACDM. Look at it very carefully. What I am subtracting this. Further, I am subtracting this. So what happens is that you are only left with this, and this portion appears twice, and we have to actually subtract delta 4. So delta 4 appeared here as well as here. So delta 4 gets subtracted twice, which is what we need, because this includes delta 4. So delta 4 minus delta 4 minus delta 4, in effect it is going to be delta 4, isn't it? Now this we know what is the area of, we can by symmetry say area of BMEF and ACDM. Okay, this is equal, this diagonal are equal in length, this is common, this is half, this is half. So all the four sides, in fact these two quadrilaterals are in effect, so to say, congruent. So you can say this is area of ABCDEF minus 2 times area of, say, BMEF. Okay, now if you look at it very carefully, this area is half the area of this, so you can very easily say okay. Okay, now if you are able to, let me draw one more diagram, okay, and then I will tell you, because it has become very cumbersome here. A, B, C, D, E, F, M. If you look at it very carefully, area of this triangle so what will be the height? The height is going to be 2. Area of triangle, this is, if suppose this side is A, this is A by 2, and the area of triangle BME is half, base is A by 2 and height is 2. A square by 2, if side is A. What is area of triangle BAF? ABF, I think that is also going to be, see if you are able to, this is A, and I think No, 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 this is not, oh, sorry, this is not 2a, very sorry. Root 3a square by 4. And area of this triangle. What is the area of this triangle? You can very easily see. This triangle you can also find. This is A and this height is A root 3 by 2. Area of triangle ABF is half A into root 3A by 2. Root 3A square by 4. That means these two triangles are of equal area. Okay, that means, and we have to find area of BMEF. So area of BMEF is this plus this. This is equal to this. So all in all, we are looking at half the polygon. All in all, we are looking at half the polygon. So what do we get? That this is nothing but half of A, B, C, D, E, F. These two had equal areas already. So our answer turns out to be big 0. See, no matter whether we dealt with regular hexagon or anything, if you see, most of our calculations were confined to, almost all of our calculations were confined to being triangles or quadrilaterals. That is what I am telling you, that when dealing with polygons of side greater than 4, so 6, 7, 8, we try to come up with quadrilaterals and triangles, which we can then generalize in different ways, which we already know, which we have gone through while dealing with quadrilaterals and triangles. Okay. So, more or less this is what we have to go through in polygon. We have gone through the part which is primarily referred to as pure geometry. Now, what we have to understand is that thinking in geometrical terms on occasions may be a bit demanding. So, we would like to come up with some methods which are bit algebraic in nature, so that the normal operations that we do based on certain functions that we will define and you might possibly be aware of, would be helpful in dealing with problems. So, in that series, one of the things that we must be reasonably aware of is trigonometry. A bit of it you would have covered in your school classes, that in a right angle triangle we define the legs as perpendicular base and this side as, and the side opposite to 90 degrees hypotenuse, and you know that sine theta is P by H, cos theta is B by H, and tan theta is P by B. This is also 1 upon cosec theta, one upon sec theta, and this is 1 upon cot theta. The identities that you must be aware of are sine square theta, cosec square theta is 1. So, I hope all of you are aware of these things. We have to build, we have to know a bit more trigonometry, so that we are comfortable in dealing with problems, especially of triangles and also of higher degree polygons. Even in our previous discussion, we saw how in radius, circumradius and side of a regular and sided polygon were connected. So, these things in that scenario turns out to be of great help. Today what we are going to do is we are going to extend the definition of sine cos to angles which are beyond 90 degree, because angles of a right angle triangle barring this angle is going to be an acute angle. So, post 90 degree, how do we define sine cos? So, what we say is that if we take a unit circle, okay, and if we are moving counterclockwise, the measurement is positive. If we are moving clockwise, the measurement is negative. And if you move an angle theta, you reach a point P whose coordinates are x and y. So, what we say, x is cos theta and y is sin theta. Okay. So, even if when you are at this point after moving this much distance, this point will have some x and y coordinates. Okay, this too will satisfy what is x coordinate will be cos theta, y coordinate will be sin theta, and it is in consonance with the definition of sin cos that we do. This is x, this is y, this is 1. Base upon hypotenuse is cos theta, perpendicular upon hypotenuse is sin theta, tan theta would be y by x. So, from here you can understand that x coordinate can at max be 1 and least be minus 1. So is the case with y coordinates. Okay. So, cos theta always lies from -1 to 1 and sin theta always lies from -1 to 1. Okay. The identities that we have gone through, they remain the same. You can understand that when you reach this point, tan theta is not defined because x is 0. When you reach this point, cot theta is not defined, okay, because y is 0. So, sin cos are defined for all theta, tan is not defined for, say, this is 90 degrees, then 270 degrees, and then we can move on like that. But I am not getting into that typical part. Our primary aim is how will we use it in geometry. So, I am not getting into the proper definition and stuff like into too much details. The purpose of going through trigonometry here is to let us be comfortable with so that we are comfortable with the problems that we are required to solve in trigonometry. Especially solution of triangles we will be using. So, a bit of trigonometry is did there, that is the sole purpose of going through this, not per se studying trigonometry. Now, when we talk of allied angles, okay. So, what we say is sine, I hope you are aware, sine 90 minus theta is cos theta, cos 90 minus theta is sin theta, and thereby tan 90 minus theta is cot theta. Okay. Now, if we talk of, say, sin 90 plus theta and stuff like that, how do we get to know it? See. Suppose this is theta, add 90 to it. Okay. Now, you can very easily see this is 1, This is one, this is 90, this is 90 minus this is theta. So these two triangles are congruent. So if this side is x, opposite to 90 minus theta, this side is x. This is y, so this would be y. So what are the coordinates at this point? If this is x comma y. Okay. So what is sine? Can you think what is sine 90 degree plus theta? Y coordinate. Y coordinate is x, and what is x? Cos theta. This is cos theta. Cos 90 degree plus theta will be nothing but y coordinate, which here is cos 90 degree plus theta will be nothing but x coordinate, which here is minus y. Minus y is minus sin theta. Simply for other allied angles, we can extend it. Say sin 180 degree minus theta, cos 180 degree minus theta. So how are you going to do that? Say, let me draw the figure here. Okay, this is theta, this 2 is theta, and these two triangles therefore are congruent. So if this is x comma y, this is minus x comma y. So sin 180 degree minus theta would be sin theta, cos 180 degree minus theta would be minus cos theta. Just by congruency we look at it. Tan 180 degree minus theta is therefore minus 10. Generally this one would be sufficient, okay, but okay, for the sake of completion let me tell you this also. Pi plus theta, this would be minus x comma minus 1. So this is pi. So sin pi plus theta, that is sin 180 degree plus theta, is minus sin theta. Tan 180 degree plus theta, you can say minus minus gets cancelled out. Okay, similarly I can make you prove also the relation between say 270 degree minus theta, 270 degree plus theta. I am simply writing it, okay. Fine. And then if you talk of say this minus theta or 360 degree minus theta. So sin 360 degree minus theta is minus sin theta, which is sine of minus theta. Cos 360 degree minus theta is cos theta, which is cos of minus theta. So, these are trigonometric ratios of allied angles. So, we need to just keep in mind, and we should at the initial level you have to practice a lot. I will ask you to solve initial exercises of trigonometry SL only, so that you are well aware of this stuff, because without practice there would be so many formulae that you will not be able to recall at the appropriate juncture. Not much of trigonometry would be needed. Elementary trigonometry expression would be needed for what we have to do. At least this part we must know, this part we must know, okay. 90 plus theta up to 180 degree, because mostly we will deal with situations of a triangle or a quadrilateral. So, it is hardly the case that angle exceeds 180 degree, okay, because we generally deal with convex polygons. Moreover, post 360 degree you can understand that if I move theta plus 360 degree, I will reach the same position. So, for any trigonometric ratio, if you add 360 degree, that will be equal to the trigonometric ratio itself, where n is an integer. Okay. So, any multiple of 360 degree, suppose somebody wants to find sine 390 degree. So, it is which is nothing but. Also from this you are able to understand that in second quadrant x coordinate is negative, cos is negative, sine is positive, cos is negative. Here sine is negative, cos is negative. Here sine is negative and cos is positive. Okay. So, therefore, people remember it here all sine, tan, cos, all sine, tan, cos. Add sugar to coffee. Quadrant wise, which one is positive, which one is negative. So, what we do is, suppose somebody asks you to find cos 120 degree. What we do, this is cos 90 degree plus 30 degree. Okay, what is our formula? Cos 90 plus theta is minus sin theta. So, this is somebody is asking you sin 135 degree. So, sin 90 degree plus 45 degree. So, this is cos 45 degree. This is 1 by root 2. Okay. What we want is that over a period of time you are able to remember it and recall it as and when required. More often than not, the purpose for which we are reading this part is more often than not our discussion would be confined to angles which are less than 180 degree, because as I have told you, our angles are going to be angles of polygon, angles of triangle, okay, and all those angles, as you can see, is less than 180. Most of the things that we study are are angles of polygons which are convex polygons mostly. Fine. Okay. Now, after this I am going to tell you lot of formulas. So, it is my sincere request that please solve SL only trigonometry part 1, so that you are well versed with the formula. Otherwise, you will find it very difficult to remember them. They turn out to be very cumbersome, so much expressions are involved, and we need to switch from one to other very swiftly. We are generally expected to be very fluent in it. Okay. But the purpose of us going through that is to know a bit of to use it in solving problems of geometry. Okay. So, I will tell you just a plus b and 2 theta formula, and then I will come to solution of triangle part. Okay, trigonometry in itself involves a lot of things, but we are not getting into it. Okay. Now, compound angles is formulae for stuff like sin A plus B and cos A plus B. So, what we do is that suppose there are various ways to come up with it. Let me draw a very beautiful proof in which we use sides of rectangles to justify the expressions. Okay. Now, consider this triangle, okay, a right angle triangle. This angle is A plus B and its hypotenuse is 1. Fine. So, what is this side? What is this side? Cos A plus B. Okay. Now, what I am doing is, from here, say, draw a line which is making an angle A. Sorry, not drawn proper. Perpendicular lines, okay. Okay. So, if you remember, if this is A plus B, this is 90 minus A minus B. So, let this angle say for simplicity be B. So, what we do is that we complete this rectangle. So, if this is 1, what is this? This angle is going to be A. So, if this is B, this is 90 minus this angle is A. Okay. So, this is cos B and this is sin B. Okay. Now, if this is cos B, what will this side be? A, this is cos B, cos A, cos B. Is it? Hypotenuse is cos B. So, base is cos A, cos B. What will perpendicular be? Sin A, cos B. This is sin B. So, this is sin B, cos A. And this is sin A. Now, it is easy to see sin A plus B is sin A cos B plus cos A sin B or sin B cos A. What is cos A plus B? Cos A cos B minus sin A sin B. Tan A plus B, if you want, simply divide these two. Okay? If you divide these two, what do you get? This upon this, and divide the whole thing by cos A cos B. So, in the denominator, what do you get? One minus tan A tan B. And if we divide this by cos A cos B, sin A by cos A tan A. Divide by cos A cos B, sin B by cos B tan B. So, tan A plus tan B upon 1 minus tan A tan B. Now sin A minus B, simply replace B by minus B, cos minus B is cos B, sin minus B is minus sin B. So sin A cos B minus cos A sin B. Cos A minus B is cos A cos minus B, which is cos B, sin A sin minus B. So this becomes plus. And therefore tan A minus B is tan A minus tan B upon 1 plus tan A tan. Other formula that we derive is that if you multiply these two, sin square A cos square B, cos square A sin square B. So this is sin A plus B into sin A minus B, sin square A minus sin square B, and simply cos A plus B into cos A minus B. Cos square A minus sin square. And do the same exercise again. Again, as I have been telling you right from the beginning of this lecture, that trigonometry will involve lot of formulae. At least this much we must be aware of. Okay? Fine. Now, we will just move to double angles and that's all. Okay? We will not get involved in too much of other formulae, pure trigonometry stuff. Okay? So one thing that in a triangle, if A, B, C are angles of a triangle, none of which is show that we will prove it here and we are required to remember it. So what we know is sum of the angles is pi, angles of a triangle. So what do we get? Pi minus c. And now we take tan both sides. So tan A plus B is tan pi minus c. Tan A plus B is tan A plus tan B tan pi minus c is minus tan c. Simply cross multiply and get the result. Okay. So in a triangle, sum of angles of the tangent is equal to product of the angle of the tangents. Product of the tangents of the angle, sorry. And sum of the tangents of the angles is equal to product of tangents of the angle. So please keep this in mind. Okay. Now if we move ahead to multiple angles, sin A plus B we know. So what will be sin 2A? Can you make it out? put A here. So sine 2A is sine A cos A, cos A sine A, that is 2 sine A cos A. So sine 2A is 2 sine A cos A. Put B as A here, what you have? Cos 2A is cos square A minus sin square A. We can also write sin square A as 1 minus cos square A. Okay, so cos 2A is cos square A minus sin square A, 2 cos square A minus 1, 1 minus 2 sin square A, tan 2A upon 1 minus tan square A. Also, remember this 1 plus cos 2A is 2 cos square A. 1 minus cos 2A is 2 sin square. Okay. So up to 2 theta, if you are able to recall, say, or 3 theta also, I may tell you, 3 theta you can simply write B as 2A, and then we have formula for them also. Okay. Let me tell you that formula also. Okay. Sin 3A is sin 2A plus A. This is sin 2A cos A so 2 sin A cos A. This is 2 sin A so what we have sin 3A is 3 sin A minus 4 sin 2. What is cos 3A? Simply do it. I am finally writing the formula. Sin 3A cos 3. We can also write tan 3A, tan 2A plus A, and then, okay, why leave it? Similarly, you can find tan 3A by writing tan 2A plus A. This is 3 tan A. You can understand how many formulae are there, okay? So, please practice it. The best text is definitely SL only. If you use SL only, you will get lot of problems based on a single formula. It gives you 3-4 formulae, it gives you 20 problems. I am deliberately not using the uh, not taking up lot of problems, because my purpose is not to teach you trigonometry. The purpose is that while solving problems of geometry, we will need some trigonometry, and we are just adding a bit of flavor in it. Okay, so that is the sole purpose of what we are doing today. This might feel very burdening and boring to you, and therefore I am saying that please go through the questions and solve them on your own, so that you are relatively well versed in terms of the formulae. We are expected to know sin A plus B, cos A plus B while dealing with properties and solution of triangles. Okay, so that is the purpose I have taken up this. Otherwise, we could have done it some other way, because trigonometry, reaching till this point while we normally teach pure only trigonometry, will take 5-6 lectures. But here the purpose is simply to introduce you to the formulae, and thereafter when we actually go to the part where we will use trigonometry to solve questions of geometry, we must at least not be found unawares. What is this? So, that is the sole purpose of this. Okay? So, just know the expressions. Okay? Now, let me take up questions. Like say, find the value of 6 sin 10 degree. So, what will this be? Take 2 common, this is what is this? 3 sin theta minus 4 sin cube theta, sin 3 theta, which is simply 1. Okay. Some more formulae that we need to know are formulae from this point. This is sin A plus B is this. Now, if we add these two, 2 sin A cos B, sin A plus B plus sin A minus B, product to sum. If we subtract, here also you can add and subtract. So, some more formulas are okay. Some more formula says that 2 sin A cos B. How are we getting it? Adding sin A plus B sin A, 2 sin A cos B, sin A plus B plus sin A minus B. So, changing product to sum. Two cos A sin B. Now, in cos A plus B is cos A cos B minus sin A sin B, cos A minus B is cos A cos B plus sin A sin B. See, if you add these two, what do you get? 2 cos A cos B. The 2 cos A cos B. Fine. And from here, what generally people do is that if we say A plus B is C, we write sin C plus sin D is 2 sin C minus D by A is 2a is c plus d, 2b is c minus d. Sin c minus sin d. You get 2 cos cos c plus cos d. And cos c minus cos d. So this is, you see, this is just the other way around, okay? It is minus 2 times sin c plus d by 2 . So now you can see how do you change product to sum or difference to product as the need be. So these are the formulae I am telling you, okay. 4, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, these 20 expressions you need to know, and initial part, this is something that I told you. This one, this is tough. Okay, this also we need to remember. So today you have seen that we have used lot of formulae, okay. And this one also needs to be remembered, okay. We need to remember it, okay. So after going through all these formulae, let me tell you the purpose for which we were going through it. These 45 minutes may have been bit demanding, bit torturous to you, but I am telling you that if you remember these formulae, they will be of great help and will be beneficial in solving the problems that you encounter, because as we see, geometry requires a lot of ingenuity. Here, once we know the expressions, we are able to use sine, cos and stuff like that, sine, cos, tan and stuff like that to deal with the situations in hand, especially in case of triangles and quadrilaterals, higher degree say polygons of say 5, 6 sides, pentagon, heptagons, hexagons stuff. That also we generally see we do it by reducing it to appropriate triangles, appropriate quadrilaterals. Fine. Now, in heights and distances also they are of great use. You would have gone through heights and distances. I am deliberately not getting into it. Okay. So, we are going through sine law and cosine law. Okay. So, in sine rule what we say? In a triangle, A upon sine A is B upon sine B is C upon sine C, which is 2R. This is called extended sine rule. R is circumradius. I hope you remember small ABC, okay. They represent sides. What is A? A is BC. We went through all this when we were dealing with trigonometry, okay. So, it is very easy to prove if you look at it properly, you draw this altitude. So, what is AD in this right angle triangle ABD? C sin B, and in it 8 CD it is. So, C by sin C is B by sin C. Similarly, draw one more altitude and get to it. How do you get to 2R? If this angle is A, angle at the center is going to be 2A. This is A, this is A, this is R, this is R. So, this is R sin A and this is R sin A. So, this is nothing but length of side BC. So, BC, which is A, is nothing but 2R sin A by sin A is 2R. So, while dealing with questions of triangles, this is of great help. Okay. You do come across lot of things where sine rule and cosine law on most occasions is sufficient to deal with the problems that we generally encounter. So, I would request all of you to be well versed in sine law, and after this class, maybe in the next, we will take up cosine law. So, today we will confine most of our discussion to sine rule only, all of our discussion. Let us introduce cosine law in our next class. Okay. Now, how do we deal with the situation of sine rule? Whenever you are solving problem of trigonometry which involves say angles which are not nice, then we can use sine or cosine law. For example, if I say, let me start with this problem like this question. In a triangle, A is equal to R into find perimeter or find area of triangle if its largest side is 4 units. Symbols, these are all sides, this is circumradius. Okay. So, this is AR. What we have read? A is 2R sin A. So, A upon R is 2 sin A. Okay. So, A upon R so this is 2 sin A, and by AM GM we can say B plus C is greater than equal to 2 root BC. AM is greater than equal to GM. All these are positive numbers as we are dealing with sides of the triangle. So, 2 sin A is, you can see, root B by C. So, sin A turns out to be, this implies sin A is 1 and B is equal to C. equality holds. So what all in all we have an equilateral triangle. Largest side is 4. This is 45 degree. So these sides are 2 root 2, 2 root 2, and I think other will follow. Area is a very trivial thing. Half eight by 2, 4, isn't it? Area is 8 by 2, which is 4. From sine rule also you can possibly understand, as we did the proof here. C sine B. C sine B is the altitude and this is base. So area is half AC sine B or half AB sine C, or what you can write further, AC AB BC, half BC sine. Fine. This is how we have used sine rule. Now in a triangle, if somebody says, see, A, B, C are proportional to sine A, sine B, sine C. So if sides are in AP, sides of a triangle, if they are in AP, then sine A, sine B, sine C, they too are going to be in AP. Okay. Let me say, in triangle ABC, in triangle ABC, altitude from vertex A has length ABC upon B square minus C square. If angle ACB is 23 degree, find angle BAC. Okay, so just now we saw the length of altitude from vertex. That is why I have always told you, remember how did we initiate the proof, how we prove things. What is the length of altitude, C sin B or B sin C, as you wish. Okay. So length of altitude, from vertex A. So C sin B. So sin B is AB upon, now either we write everything in angles or everything in sine. Either we change here as this as B by 2r. Either we do that, or we change this as A is 2r sin A, B is 2r sin B upon 2r sin B whole square minus 2r sin C whole square. So sin B is sin A sin B upon sin square B minus sin square C. Now we have read this formula. Sin square A minus sin square B sin A plus B into sin A minus B. Okay. So this is sin A upon sin B minus. So sin B gets cancelled out. What we are left with is 1 is equal to sin A upon sin B plus C. So what is B plus C? Pi minus A. Okay. And what we have read today? Sin 180 degree minus theta is sin theta. So this is why see this is how formulae are required to be. These two are equal. So sin B minus C turns out to be 1. It is an obtuse angle triangle, meaning thereby B minus C is 90 degree. Okay. So angle C is 23 degree. So B is 113 degree. C is 23 degree, 136 degree. So what is angle A? 44 degree. Okay. So we were going through those things in trigonometry for the simple reason that we, when needed, we are able to apply the formula. As such, the purpose was not to go through trigonometry because it is a helping tool. It is an auxiliary thing. That is why we have gone through it. We get some good problems in whenever you have to introduce a variable or your own, whenever you are into solving triangles, sine rule is of great help more often than not. Whenever you are in doubt in so far as triangles are concerned, sine rule generally is of great help. This has been my experience. Let us take one more problem, last problem of today, so that you are able to do some practice of sine rule at your home post this lecture, and of course remember the formula of trigonometry. Make it a priority. We will give ample time to sine, cosine law and other stuff related to solution of triangle. Unfortunately, we are not able to give that much time to trigonometry, but to remember the formulae, it is necessary that you practice them. So to practice them, the standard text for last close to 1.5 centuries is S.L. Dhoni, written in say 20th, rather 19th century. Okay, 1880, still is a classic and extraordinary text. Now, sine rule, problem, okay, AP and sine rule, okay. Suppose I say 3 theta, formula of 3 theta would be needed now. In a triangle, A plus C is 2B. Let me ask you a simple question. Find the value of Very simple problem. Okay. Sorry. Okay. So how do we solve it? 2r sin A. You can see 2r will appear everywhere and it will get cancelled out. So sin A plus sin C. Hmm. Sin C plus sin D. 2 sin C plus D by 2 cos C minus D by 2. And also we will use sin 2A is 2 sin A cos A. So sin A is 2 sin A by 2 cos A by 2. If here we use A, this is A by 2, A by 2. Okay. So sin A plus sin C is 2 sin A plus C by 2 cos is 2 times 2 sin B by 2 cos B by 2. Now what is A plus C? A plus C is sin now sin pi by 2 minus B by 2 is cos B by 2. Into cos A minus C by 2. This is equal to 2 sin B by 2. So cos A minus C by 2 upon sin B by 2 is 2. Okay, so let us complete today's lecture by a very simple problem. Cosine law, very powerful tool, and sine law put together would be of great help insofar as solving problems are concerned. Okay, and it is my sincere request to all the students who have watched this and hopefully gained from it to practice formulae of trigonometry. Just don't pen it down and try to remember. Okay, do problems. When we use a formula twice or thrice, pen it down on your own, you tend to realize what are the situations when they will be used. Okay, trigonometry. Okay, in the class we also started sine law. Okay, in the previous lecture at the fag end, we started with sine law and we said A by sin A is B by sin B is C by sin C. Okay, and then whatever it was. Fine, and then we said extended sine law what, that this is equal to 2r. We did some problems based on it. Okay, let me refresh your memory by doing one or two more problems. Okay, and then we will move on to cosine law and other things that would be needed. Okay, so at the very beginning I said that in solving problems, please use sine law insofar as solving lot of problems of notion where angle and side simultaneously are given, and the angles are not angles. Somebody last class we solved a problem which had an angle of 19 degree. So those are the angles that geometrically even we are not able to draw, and simultaneously they are ratios and stuff we don't know. So we hope that by applying trigonometry, there is a chance that we are able to deal with them in a much better and convenient manner. Okay, now I am those students who missed the last video, please go through it so that you know how did we prove it, how did we prove it. That was done at the last 15 minutes of that lecture. We introduced sine law. Fine. So while solving problems, it is advisable that you use sine rule as and when needed. Say in trigonometry, if I ask you a question like this, suppose this is triangle ABC. And we take a point inside the triangle. Suppose this angle is theta, this angle is theta, and this angle is theta. We have taken a point P such that this is the situation. Okay, and somebody is asking find cot theta upon cot A plus cot B plus cot C. Or we can give you the triangle ABC, angles of ABC, and we can find, and we are asked to find this angle theta. That is how generally, let me first tell you, then I will tell you what will be the case. Okay. Now, in situations like this, if we are not able to proceed geometrically, it is advisable that we use sine rule as a de facto method that we apply is sine rule. So, how do we start? This angle is theta. This is A minus theta. This is B minus theta. This is C minus theta. Okay. See, these sides are C, A, now here we can say PA upon PB. That can be done, or let us take AB. Let PB be the common thing, PA. So PB upon sine theta is C upon. Can you tell me what this angle is? This is B minus theta, this is theta. So sum of these two angles is B. So this is nothing but A plus C. Sine A plus C. Now let us take this PB only. PB upon sine C minus theta is equal to, this is C minus theta, this is theta, so this would be, as in the previous case, A plus B. This is A upon sine A plus B. The purpose of introducing PB on both occasions was that now we can find PB from this and equate, or we can simply divide these two. So if we divide these two, PB gets cancelled out, and what do we get? Let us write in the next page, sine C minus theta upon sine theta is equal to, you can write sine A plus C is sine pi minus B, isn't it? Sin pi minus theta is sin theta. This is C upon sin B. A upon sin C. A upon sin C. Now C upon A is sin C upon sin. So if you are able to see, it is sin square C upon sin B sin. Okay. Now, because you want cot, you want sines in the denominator. Sin C minus theta upon sin theta sin C is equal to sin C upon sin B sin. What is sin C? Since in the new denominator you have A and B, we will write this as sin of upon sin B sin, and sin pi minus theta is sin theta. So this is sin A plus B upon sin A sin B. The formula for sin A minus B is sin A cos B cos A sin B. This is sin A cos B cos A sin B. Okay. So sin C gets cancelled out, you get cot theta. Here sin theta gets cancelled out, cot C is equal to C. Sin A gets cancelled out, you get cot B. Sin B gets cancelled out, you get cot A. So cot theta is cot A plus cot B plus cot C. If the triangle is equilateral, corresponding point will be the centroid. Okay. Fine. So this is the use of sine rules. So whenever you are not able to think of a geometrical way to proceed in the problems, a very good way to deal with such problems is this. Now, because of this fact, what did we prove? Here also somebody may ask you, show that cosec square theta is in the previous problem. So how will we deal with it? We had proved the fact that is available to us is this. Fine. Now if we square it, what do you get? Plus 2 times cot A cot B Now, if you remember what we learned in the last class was, in a triangle tan A plus tan B plus tan C is tan A, tan B, tan C. I hope I very specifically told you to keep this in mind. In a triangle, sum of the tangents is equal to product of the tangents. So, what do you get now? If we dividing both sides by tan A, tan B, tan C. So, if you divide both sides by tan A, tan B, tan C, here you will get 1. And what are you going to get on the left hand side? Tan A gets cancelled out, cot B, cot C plus cot A, cot B. So, this is nothing but 1. So, what you have got is cot square theta is cot square A plus cot square B plus cot square C plus 2, and you can now very easily see cot square theta plus 1. If you add 1 on both sides, you will get 2 here, and you will distribute that 3 each one of these cot squares. So, cosec square theta is cosec square A plus cosec square B plus cosec square C. So, this is how we use trigonometry, sine rule in things like this. Okay. Let me give you one more example. Okay. So, in a triangle, sides are in AP. In a triangle, sides are in AP, and the largest angle is twice the smallest. And the largest angle is twice the smallest. If sides of the triangle are natural numbers, find least possible area. Find least possible area of the front. Okay. Unfortunately, there is some lag in the board. Some issues are there. Okay, so I have deliberately written the whole expression very slowly because otherwise it was all getting haywire. Fine. Here also, let us say sides of the triangle are A minus D, A, A plus D. The smallest angle is say theta. So this would be the largest angle would be 2 theta. So the remaining angle is pi minus 3 theta. Okay. What I am trying to convey is that the moment you see the data, the only possibility that works out is trigonometry. And a viable way turns out to be sine rule. So please keep these things in mind. Okay. Now what do we get now by sine rule? Let me write in next page. By sine rule, A minus D by sine theta is A upon is sine 2 theta. Okay. So now if we from these two, what do we get? Sine 3 theta upon sine theta. What is sine 3 theta? 3 sine theta minus 4 sine cube theta. So 3 sine 3 theta is 3 sine theta minus 4 sine cube theta. So this is one thing that you get. If we take these two, what do we get? Sine 2 theta upon sine theta. Is what is this? Sine 2 theta is 2 sine theta cos theta. So this is 2 cos theta. Incidentally, we here have sine square theta. So what we are going to do is that here we will write this as A upon A minus D is 3 minus 4 into 1 minus cos square theta. So this is 4 cos square theta minus 1, 2 cos theta whole square. So what is 2 cos theta? A plus D upon A minus D whole square. So what you are going to get is denominator is, and what will be the numerator? A plus D whole square minus A minus D whole square. 4A D. So A and A gets cancelled out. You have A minus D is 4D. So A is 5D. So sides are 4D, 5D, 6D. Okay, I think now since we gave our sides as natural numbers, we have to find the least possible area. So we take our sides to be for least possible area. The sides are 4, 5, 6. Okay, for least possible area, the sides are 4, 5 and 6. So that is, if you want, I think that this calculation is very trivial. The important part was this. Another beautiful problem of the same genre that appears, in fact it appeared in JEE Advanced 2. Unfortunately, when solution of triangle was removed from the syllabus, was sides are in AP and the largest angle is 90 degree more than the smallest angle, then ratio of sides. Okay. In the language of this problem, only this thing needs to be changed. Okay. The largest angle, okay. Let me just refresh you. Question is, sides of a triangle are in AP. And largest angle is 90 degree more than the smallest angle. Find ratio of sides same thing. I hope you are able to understand. A minus D, A plus D, just as we did in our previous problem. If this is the angle theta, the smallest angle, the largest is 90 plus theta. So this is 180, 90 plus 2 theta, total sum is 180, so it is 90 degree minus theta. Agreed? Now we have to use the sine law. A minus D by sine theta cos 2 theta is upon cos theta. Getting it? Sin 90 minus 2 theta is cos theta. Sin 90 plus theta is cos theta. Now, in the previous, because most of them I think were sine, it was easy to deal with them. Cos 2 theta, if you remember the formula, what is the formula for cos 2 theta? Cos square theta minus sin square theta. So somehow we have to plug in this expression. So it is cos plus sin into cos minus sin. So we try to create cos plus sin. So I think by componendo, we can say just add these two. So 2a upon cos theta plus sin theta. We can subtract it, it is 2d upon cos minus sin. Now, if we plug in these two, cos 2 theta. So, what is half is equal to, you can see a upon 2a is cos 2 theta upon cos theta plus sin theta. What is cos 2 theta? Cos square theta minus sin square theta, which is cos plus sin into cos minus sin. Cos plus sin gets cancelled out. You get half is cos theta and first and last okay, in a similar manner, because here we have minus, so what will be left would be cos plus sin. Now, how to get rid of cos sin here? In this a minus d a plus cos square plus sin square is 1. So we can what we can do here to get rid of theta, square and add. Square and add. What are you going to get? 1 by 4. What is this? 7 by 4. 2 minus 1 by 4, 7 by 4. A square is d root 7. So, root 7 minus 1 is to root 7 is to root 7 plus. Just an algebraically same thing, only the difference was in terms of the notional thing that we had to use. It was sine rule. But then, since trigonometry involves a lot of expressions, subject to a certain situation, what are the expressions that would be helpful? In the previous question, we used sine 2 theta, sine 3 theta. Here we use cos 2 theta. So, depending upon the angles involved, therefore, it is very necessary, as I have been telling you in the, at the right from the beginning of the previous video, that it will be necessary to remember the formulae of trigonometry. They must come naturally. Otherwise, solving see, if we are not able to express these formulae, it will be very difficult. You can see these formulae play a very trivial part insofar as problem solve is concerned. It is presumed that we know these formulae and we have to just at the appropriate juncture, we are just applying it. Knowing the formula is not an issue. The issue broadly appears that which one to use, how to do manipulations, as this one we did here. So, such stuff is expected from us. So, please be ready for that. Okay. Just I think these are questions from SL Loni. Even in JEE Advanced, they ask questions from SL Loni. Okay. Almost always the same. So, a fantastic book, and therefore I told all of you to practice from that book, so that so that you are able to write the formulas and when needed. The best part about Loni is that, or in this standard text, is that there are a lot of questions on single formula. So if you practice enough, you will be able to deal with it very, very, very efficiently. Whether you are giving your school examinations, whether you are appearing in Olympiad, whether you are appearing in JEE Main, whether you are appearing in JEE Advanced, you will see that almost all the problem have the flair of the questions that are there in SL1. That is the beauty of the book. Okay. Now, moving ahead, let me also tell you cosine law and projection formula. Okay, so cosine law says cos A is and I think in a similar vein you can say, or you can write, somebody may write it as A square is B square plus C. People may write it like this, people may write it like this. So, sin cos you can write, say, suppose I draw this already. This is C, this is C cos B. Okay, this is C sin B. What is this? A minus C cos. Now apply Pythagoras theorem. C square sin square B. Square of the plus base square is equal to B square. So this is C square sin square plus C square cos square, you get C square. B square is this. You can draw altitude from B and get the same result. This is basically the expression we have obtained for cos B. We could have done it the other way around. We could have said this is B cos C. So this is A minus B cos C. This is C sin B. In the sine rule, you can say is B sin C. Okay. Now, insofar as projection formula is concerned, I think it is very easy to see that if this is C cos B, this is B cos C. A is what? B cos C plus C cos. And in similar way, we can write B is C cos A and C is A fine. So this is called projection formula, this is cosine law. So two formulae which would almost be sufficient in dealing with the problems that we will encounter, almost be sufficient. To introduce a variable on your road would invariably apply either using sine rule or cosine law. Barring this, whatever we come across in solution of triangle, you will see that they will primarily be stuff like if something is proided, if somebody says this is circumradius, If somebody says this is angle bisector, so then those formulae of trigonometry, if we are applying trigonometry, then only they get introduced. Either they are asked or they are provided. Otherwise, on our own, if we have to use variables and stuff like that, we generally prefer using sine cosine law. Okay? Now, if you look at it as how are you going to use cosine law? So, when angles are asked, the sine law generally, cosine law is generally preferred because sine A is root 3 by 2. So, you may have an issue whether the angle is acute or obtuse. But otherwise, you are able to, in cosine law, you are able to easily gauge what is the situation because second quadrant cos is negative. Very simple question is, if a plus b upon 10 is b plus c upon 11 is c plus a upon 12, find cos a. So, a plus b upon 10 is, this is given. So, what we do generally in this type of problems, let this be some lambda. So, a plus b is 10 lambda, b plus c is 11 lambda, c plus a is 12 lambda. You simply add, 33 lambda by 2. C is 11 lambda by 2, isn't it? 12. 9 lambda by 2. Sides are in AP. Cos A now we can very easily find. This is B. This is A. So, what is cos A? Lambda square will get cancelled out. B square plus C square minus A square. To BC. So, at the very beginning we could have got rid of this 4. Even though I wrote and then cancelled, but it is only an issue of proportionality. So, we could have taken the proportion 13 is to 11 is to 9. So, what is this? 169 minus 121, 48. 48 plus 81, 129. 117 into 2, 234. So, this is cos. Not a reasonable number, but so be it. Okay. Use of cosine law. How else? Let me give you one more problem where we are using cosine law simply. See, in a triangle, A square plus B square is 11C square. Okay. Find cot C upon cot A plus cot. Information being provided in this manner is indicative of the fact that a possible way to deal with the situation would be cosine law. Okay. So let us see what is cot A. What is cot A? Cos A by sin A. What is cos A? We have just gone through the formula. B square plus C square minus A square upon 2BC. Two BC sin. Okay. If you recall, area of the triangle we wrote as half BC sin or half AB sin C or half AC sin B. So this is B square plus C square upon 4 delta. This is B square plus C square minus A square upon 4 delta. Okay. Now we see what to do. Similarly, what we will get cot B as C square plus A square upon 4 delta, and similarly for cot C. Okay. So cot A plus cot B. 4 delta, you can see what it turns out to be, cot C. So cot C is upon 4 delta. 4 delta will get cancelled out, cot A plus cot B. A square gets cancelled out, B square, 2C square. So is 11C square Okay. So this was some where we could very easily conceive the fact that this expression was required to deal with the situation. Now, in some cases, suppose I say in triangle ABC, say side A, or rather I would say side AB, sorry, BC is suppose say 6, CA is suppose 8, and angle ABC is say 60 degree. Find possible value of AB. So simply by cosine law, cos B, okay, cos B is half, is C square plus A square minus B square upon 2 into C into this is cos AB, C. B, cos B is C square plus A square is 6. 2 gets cancelled out, you get 6C is C square minus 36 minus 64 is 20. C square minus 6C minus 28 is 0. You can see one of the values of C will be positive and one will be negative. We will take up the positive. 36, 112. 148. So 148 30 3 plus root 37. 3 minus root 37 is root log. Now, if we just shift these two, suppose this is 8 and this is 6. Are you able to see that the equation is going to be 6C is C square plus 28. So, probably in general you get a quadratic, there is a possibility that you get two triangles. Okay, the data can be appropriately taken. You can consider it like this, okay, that see, you are given a side, this angle is given to you as 60 degree, okay. CA, BC. BC is 8, isn't it? BC is 6, CA is 8. So if this is A, BC is also given, okay. And BC and CA, okay. No. BC and CA. What is BC? 6. Okay. So if this is 6, okay. So what you have to understand is that from this point as center, C as center, what you are doing is you are drawing a circle of radius 8. Suppose you know the radius has to be at least, C, 6 sine 60 degree, that is 3 root 3. The radius has to be greater than 3 root 3. That means this has to be greater than, this side has to be greater than 3 root 3. 3 root, if you take something greater than 3 root 3, you will get 2 triangles. The moment you take your side to be greater than 6, okay, you are going to get a circle like this. So this point is ruled out. Only this triangle is something that we are getting. So this is 6, this is 8, and this is 3 plus root 30. So that is 3 minus root 30. So had our side, had this side been less, had this side been say 3 root 3, the 17, 3 7. Suppose BC is 6, CA is 11 by 2. In that case, you would have got 2 triangles, because the moment you say this side is greater than 6, you only get 1 triangle. The idea is not to remember these stuff. The idea is to always apply cosine law. You get a quadratic. If both roots of the quadratic are positive, you get 2 triangles. Sometimes you are asked question on what we introduced you to a bit of trigonometry. So in this lecture today, we will see how cosine law is applied to various situations, how projection formula is applied, and then we will move on to other things. So starting with solution of triangles, and in the previous class primarily solving would involve sine law and cosine law. We have gone through them. A bit of projection formula has also been told to you. Okay. Now in cosine law, one of the questions that we did earlier, probably somewhere in geometry while dealing with right angle triangles, we will do the same thing using now cosine law. Cosine law, I think you hopefully remember, cos A is b square plus c square minus 2bc, sorry, minus a square upon 2bc. Sine law, a by sine A and this equaled 2r. So in cosine law, I think if you remember, one of the questions that we did long back insofar as triangles were concerned was that if sides of a triangle are 3 consecutive natural numbers, and it is an obtuse angled triangle. Find its area, perimeter, anything, or sides. So we say if the sides are n minus 1, n plus 1, this is the largest angle. If it is obtuse, its cosine is going to be negative. So, cos of the largest angle, say C, is this has to be less than C, and this will now conclude the things. Won't it? You can see this is definitely positive. So, it is n square minus 4n is less than 0. So, n is less than 4, and you can see cannot be 1, and you can see cannot be 2. If n is 2, what you get? The sides are 1, 2, 3. They will not be able to form a triangle. And if you remember long back when we said if sides of a triangle are integers and one of its side is 1, it has to be an isosceles triangle. Okay. So, what the only thing left is n is 3. So, if n is 3, sides are 2, 3, 4. Area I think now is a very trivial conclusion. So, I am not getting into it. So, length of sides, angles are involved. Cosine law is a very good way to deal with a situation like that. If suppose two sides and one of the angles is given, if the included angle is given, suppose you are given two sides, say A, B, okay. And you are given the included angle, then this can be determined uniquely. I think it is very easy to observe that C square you can simply write as A square plus B square minus 2 AB cos C. C can be determined uniquely. But if the angle is not included, okay, suppose the situation is like this, okay, that I give you side A, or suppose I give you say this angle B, this side C. Okay, I give you side C, angle B, and side A is given. A opposite C, C is given, angle B is given. C, okay. And I give you side B. B is also given. This is not the included angle. I think you can very easily make it out. That what I have done is drawn a horizontal line, and then at angle B I have taken length C. Now, if I am given side B, what I will do is with this as center, I will draw a circle of radius B. If radius is less than this, you won't get any triangle. If the side B is less than C sin B, okay. If B is less than C sin B, no such triangle is formed. Isn't it? If B is greater than C sin B, suppose you draw a circle, it is intersecting this at 2 points. Then I think you can very easily see there are two such triangles. Isn't it? This is a C1, C2. But if has to be less than C. you have two triangles. In case you come across a situation where the side B exceeds side C, so circle that you will get will intersect this like this. So in effect you are getting only one triangle. This triangle has to be ruled out. So if B is greater than C, we get one triangle. In fact, if we remember in the previous class what we did, so these things are per se not to remember. Simply write cos B C square so you have to find side A. It is a quadratic in A. And solve this quadratic. Don't try to remember these facts. If D is less than 0, you can very easily see this is the case. You can find discriminant. I am not getting into it. Okay. See, by quadratic, let me tell you just once. What is D? 4C square cos square B. Or this is what we were saying. If B is less than C sin B, D is less than 0. If B is greater than C sin B, this discriminant is positive. And you can see this. If C square is greater than B square, the product is positive. So you get two positive roots. If B is greater than C, this is negative. So you get one positive and one negative root. Side of a triangle cannot be negative. So therefore, this is the situation. Sometimes you can see, because you are given side B and angle B. In this case, the two triangles that you are getting, you can understand B is given, angle B is given. Both the triangles in this case, both triangles have same circumradius, isn't it? B by sin B is to R. B is fixed and sin B is fixed for both the triangles. So we can very easily conclude that even when you get two triangles, they will have same circumradius, not in radius. In radius would be different, you can see. So these are called ambiguous cases in a triangle. My request, humble request is just do this process. Don't get involved into these things. Okay, that will be a bit cumbersome. This on most occasions is very helpful in the sense that you don't need to remember expression, just do it algebraically. Proceed it in the manner as was needed. Two sides and an angle was given. You proceeded by cosine law. It is very easy to interpret that this is a quadratic, whether it has positive roots, negative roots, non-real roots. Accordingly, we can conclude how many triangles are possible. Okay. Now, if somebody says, what is the area of this triangle? Getting it? Suppose I am asking you, what is the area of this triangle? Can anyone tell me? Sometimes they say, if there are two triangles ABC1, ABC2, what is the area of triangle AC1 C2. So you can see the difference of roots here. Area of A, let me draw it in a fresh page. So difference in area will be half C. A2 minus A1, difference in roots of a quadratic, root delta by A, root delta by A, and delta is, sorry, root D by A. A here is 1, so it is root D. So half C sin B, 4 into B square this is the area, difference in area. In the previous class, I wanted to take up a question where you are simply asked, don't again, I am again saying, don't remember the formula. There is no point in remembering the formula, okay. That is a tedious ask. What is simple is that think along quadratic lines and resolve it accordingly. Now, let us take some more problems based on say cosine law. So, sides angles being provided is a good enough hint for cosine law. In fact, if we don't know Stewart's theorem, then cosine law is a very good way to find length of angle bisectors or length of say medians. Length of median, because we are aware of Stewart's theorem, we use Stewart's theorem in determining length of medians. Else, cosine law would have been of great help. Okay. Now, let me take a good problem, I would say, of cosine law. I like this problem. It is a problem from S.L. Looney, and it is a good problem. So, I would say that the question says a circle of radius r is drawn and on it is taken a point O. On it is taken a point O with O as center. A circle of radius three r by 2 is drawn. On the smaller crescent shaped area. On the smaller crescent shaped area, a circle of radius r by 8 moves from one extreme to another. From one extreme to another. Always touching the circle of radius r internally. Find the length of arc covered by center of this smaller circle as it moves from one extreme to another. This is a very good 5-mark question, okay. We have done some simpler problems earlier. This is a good problem in that sense. So, just look at the language of the problem, think about it, advising all of you to just give it a thought, pause the video, think about the problem, comprehend it, draw an appropriate diagram, and then try to fathom how to do it. Take your time, take 5-10 minutes. If it is not possible for you to come up with a plausible solution, or you are not getting a headway, then look at how we started with solving it, then again pause it and then proceed. So, take your time. These when we are preparing for examinations like this, one of the key aspects is patience. Try to concentrate, give substantial thought on the questions that appear, because not everything would be at the click of a button, not everything would be grasped or understood, or you being able to solve it in a very short span. So, I am requesting all of you to please take some time, give it a thought of your own, and then only proceed ahead. Now, I am moving ahead, you can pause the video and then proceed. So, you are given a circle of radius r. So, let me draw a circle of radius. Suppose this is a circle of radius r. O is a point on the circumference. Now, with O as center, you draw a circle of radius 3r by 2. Now, in the smaller crescent, say this is the crescent of a moon. If you remember, we say crescent of a moon. Now, in this region, you are moving a circle of radius r by 8, which is always touching this blue circle. Say it's and it keeps moving, say it can keep rolling. So, to what point will it roll? It will roll to a point where it starts touching the larger circle externally. This is one extreme and this is, say, another extreme. It cannot go further ahead. And it keeps on moving, touching this, and then ultimately it will stop here. So you can say this is one orientation. Now what can we conclude from this? We can conclude that because the circle is always touching this blue circle internally, let me draw it separately. This is the blue circle. This is the white circle. Center of this circle, center of this circle. Distance between the centers is R1 minus R2. The radius of this smaller circle is R by 8. So, R minus R by 8. So, if it moves an angle theta, it is moving in a circle of radius 7R by 8, whose center is center of the original circle. So, this point is C. So, our circle of radius R by 8 is moving in a circle, the center of the circle of radius R by 8 is in itself moving on a circle of radius 7R by 8, because it is always touching this blue circle. What is length of the arc? If this angle is theta, okay, and this radius is R, what is length of this arc? R. If theta is 2 pi, you say 2 pi r is the circumference. If theta is pi, you say pi r, that is semicircle. Fine. Now look at it. In this extreme situation, let me draw this triangle. You can say if this angle is theta, on the right will also be theta. So, length of path is into 2 theta. Now, can we find this theta? If this is theta, this is going to be pi minus theta. And I think rest we can very easily see. This is R, this is 7R by 8 always, and in the extreme situations, this white circle and this yellow circle are touching each other externally. So, what will be this side? 3R by 2 plus R by 8, 13R by 8. We know all the three sides. Finding the angle, cosine law is better, because if sine theta is half, we have to think in two different directions, whether the angle can be acute or obtuse. But here that is, but in cosine law that is sorted. So, cos pi minus theta is r square plus 49 r square by 64 minus 169 r square by 64 upon 2 7r by 8. So, you can see r square gets cancelled out. 64 cos pi minus theta, let me write it here only. 64 plus 49 minus 169 upon 2 into 7 into 8. You will get, because 64 and 8. Okay. 49 minus 169 minus 120. 120 minus 64, 56, minus 56. So this is minus 56 upon 112 minus half. What is cos pi minus theta? Minus cos theta. So cos theta is half. I think now we can very safely say theta is pi by 3. This is 7r by 8 into 2 theta is 2 pi by 3. This is 7 pi r by length of the path. This is the length of the path traversed by central resistance. I would say it's a very beautiful problem, and application of cosine law was the key in dealing with this. Okay, application of cosine law was key in dealing with the problem. So this is what I am saying, that in case geometry turns out to be a bit demanding, then trigonometry is a very good way to proceed. So we have taken some questions of sine law, some questions of cosine law. Now we will move ahead and deal with other formulae. Length of median, I think we had already found using Stewart's theorem. So I hope you remember it. That can be of use here also. Cosine law, if you want to do one more problem, another beautiful problem I saw some days ago was ABC is an equilateral triangle. ABC is an equilateral triangle. P is a point inside the triangle. If PA is 3, PB is 4, PC is 5, find side. In fact, all the sides are equal. Now take an equilateral triangle. Okay, PA is 3. PA is 3, PB is 4 and PC is 5. 3, 4, 5. 3, 4, 5 for a lot of reasons turns out to be a right angle triangle, and therefore a lot of our thinking goes into determining whether an angle be 90 degree, but these are not sides of a triangle per se. That is an issue. So, because if we randomly start taking angle theta alpha, that would be too much. Okay. So, how do we get to it? This is 3, this is 4. If we are able to somehow draw triangle 3, 4, 5, we generally feel very happy about it because you get a perfect right angle triangle. The purpose is to find side of this triangle. So, if you look at it very carefully, this distance is 5. Now, just look at it. It's a fantastic idea that if this is rotated by an angle 60 degree, this is AC, I rotate it by an angle 60 degree about A. C will come to point B, B will get rotated by 60 degree, you will get an equilateral triangle. Okay, so this is in fact, okay, so this is point P. C comes here, P also gets rotated. This is going to be always 3. Okay, so okay, this say P comes here. This is going to be 3, isn't it? This is going to be 60 degree. We have rotated this by about A by 60 degree. This is 60 degree. And as needed, P reaches here, so PB. So this is say D. This becomes 5. This becomes 4. See, this gets rotated by 60 degree. Okay. And what happens? This distance 5 is now here. This distance 4 is here. So, this is the situation. This is 3, this is 3, this is 60 degree. So, this is also 60 degree. And this side is 3, isn't it? This is 3, this is 4, this is 5. So, what is this angle? 90 degree. So, you can think of triangle PAB. Now, think of triangle PAB simply. You are given two sides. Three, 4, and what is this angle? 150 degrees. You can find side AB, cosine law, two sides and the included angle. So, cos, so AB whole square is 3 square (25) plus 12 root. So, side of the triangle is root of 25 plus. Another beautiful problem, the crux was rotation, not cosine law. Cosine law was a very trivial conclusion of what we were thinking about, what we had to do. But if you see, it is also a very beautiful problem. I will rate it as a 5-mark problem, because this thought that because it is an equilateral triangle, because if you rotate by 60 degree, the distances would be such that you will get a right angle triangle. The aim was, can we do something to get a triangle like this? And incidentally, it turned out that if we rotate about A by 60 degree, it could have been any other also. So, but then that would have made some other angle 90 degree, but that is fine. The primary idea was rotating it, and once you get into it, you can see that it is a beautiful problem that we have been able to solve. So, I would recommend all of you that the previous two problems, they were good problems. Okay. Even if you were not sure and you Instead of solving it on your own, you went ahead and saw the whole video. I am again suggesting that, say, after this lecture is over, read the problem and try to do it on your own. Even after seeing how the things are to be taken up and solved in the two problems, even post of the class, if you are able to solve it on your own, that will be of great help. That means you have grasped the notion, and what was to be needed is something that you can fathom if once you are told. This rotation part, we will come across other questions where you will see how on occasions rotation is of help. Okay, just the thought came to my mind. I solved it, say, 5-10 days ago. Student asked me this problem, and I just remember it's really a beautiful problem. Okay. Now let us go to other formulae, half angle formulae in trigonometry in solution of triangle. Okay. So half angle formula. Okay. So what are half angle formulae? See, cos A is 2 cos square A by 2 minus 1. So what is cos A by 2? Isn't it? Fine. So cos A by 2 is, you can see, B plus C plus A. So cos A by 2, B plus C plus A by 2 is S. B plus C minus A by 2 is S minus A. You can also write this as 1 minus 2 sine square A by 2 and do the similar exercise to get sine A by 2. I am just writing it. Okay. So it is, I would request all of you to do it on your own. S minus B, S minus C by BC. Similarly, for other angles, you can find tan A by 2. What is tan A by 2? Just divide them. Sin A by 2 upon cos A by 2. And I think this would give you a good enough hint. SS minus A, S minus B, S minus C, Heron's formula. So this is delta by S into S minus. You will see that this is more useful. And similarly for tan B by 2, tan C by 2. Tan A by 2 is delta upon S into S minus A. Okay. So cot A by 2 is you can very easily see that cot A by 2 plus cot B by 2 plus cot C by 2 is denominator is going to be delta. Delta is area of the triangle. 3s square minus, you can see S into S minus A plus S into S minus B plus S into S minus S into A plus B plus C. This is 2S, this is S square by delta. If you remember our last class, we said cot A is cos A by sin A, cos A is 2BC sin A, which was 4 delta. Some people ask you in a triangle, what is sigma cot A by 2 upon sigma cot A? 4 delta is common, and what you get is A plus B plus C whole square in the numerator, and in the denominator what are you going to get? Just write it thrice cyclically. So, what will it be? I think you are able to guess, okay? B square will appear twice with plus and once with minus. A square appears once with minus, 2 with plus. So, all in all, this is the result that you have. Not necessary that you remember it. Cot A by 2 is something that is useful, and I think from this you can also gather if sides of a triangle are in AP, they are equimultiples. See, A, B, C are in AP. So, minus A, minus B, minus C are in AP. If you add S to all of them, they are in AP. You multiply all of them by S, and now you divide them by delta. In sequence and progression, hopefully you would have seen it. If sides of a triangle are in AP, so are cotangents of half its angles. Side sin A, sin B, sin C will definitely be in AP. Okay, see, a formula of trigonometry, how is it useful? ABC in AP. So, cot A by 2, cos A, cot B by 2, cos B, cot C by 2, cos C. Because cot A by 2, and what is cos A? 1 minus 2 sin square A by 2. This is cot A by 2 minus 2. What is cot? 2 sin A by 2 cos A by 2. And we know already, even though this is a fact that we have just now known, but if you remember this, cot A by 2, cot B by 2, cot C by 2 are in AP. Sin A, sin B, sin C are in AP. Okay. So, difference of corresponding terms of an AP will also result in an AP. Suppose you have one sequence A1 plus D1, A1 and A1 plus 2D1, and there is another sequence A2. If you corresponding terms are added or subtracted, the resulting sequence will also be an AP. A1 minus A2, A1 minus A2 plus D1 minus D2, A1 minus A2 plus 2 times D1 minus D2. So, resulting sequence 2 is an AP. If sides are in AP, sin A, sin B, sin C are in AP, cot A by 2, cot B by 2, cot C by 2 are in AP, that is good enough. We must be able to quickly recall it. This is just a question that we have gone through. Okay. So, half angles tan A by 2, see, expressions involving radical signs, square root and stuff are rarely used, even though I am not saying that do not remember it. Tan cot, you would see that they would turn out to be more useful because it does not involves root, even though you can say delta, but delta is something that we have commonly dealt with. Okay. Now, let us say we discuss circumradius. Okay, so in circumradius of a triangle, what is used is delta is half BC sine A, and sine A by sine rule is A by 2r. So, delta is ABC by 4r. This you can see is an expression whose utility involves knowing almost everything of the triangle, sides ABC, and therefore, in solving problems, this is not something that we go to at the very beginning. Because more often than not, so much data will not be provided to us. We started our sine rule with this. Mostly, this is the way out to find circumradius. One side and one angle and the side opposite to it. If it is known, we can very safely find circumradius. If you look at it in terms of the problem solving requirements, this much information is rarely available. A side and an opposite angle is good enough to determine the circumradius. Okay. So, suppose somebody says, let me ask you a question, okay. In triangle ABC, let me think. In triangle ABC, suppose we are given that angle bisectors meet the circumcircle at P, Q, R. And we have to find ratio of area of these two triangles. Both the triangles have same circumradius, isn't it? Generally in examinations, this is given with data. Okay, I am not getting into data. What to do, that is the primary thing. So, if triangle ABC is known to us, what will we do? We will say we are asked area of ABC, a known triangle, upon area of PQR whose vertices are points where angle bisectors have met the circumcircle. So, what do we do? Area is half BC sine A, B is 2R sine B, upon, you will see R remains the same. So, sin A, sin B, sin C upon fine. Now, just we have to find angles of this triangle. This is angle bisector, this is A by 2. Angle in same segments are equal. So, if this is A by 2, this will be A by 2. This is A by 2. So, this will be A by 2. Okay. This chord B by 2 subtends B by 2 here. This chord subtends B by 2 here, it will subtend B by 2, and similarly C by 2, C by 2. Okay. So, A plus B by 2 upon sin A plus B, see A plus B by 2 is sin pi by 2 minus C by 2. So, cos A by 2, cos B by 2, cos C by 2. This is 8. If you remember, what are the formula of half angles? S minus B, S minus C upon BC. Let me write it. See, somebody may only give you sides and ask this question. So, S minus B, S minus C, S minus C, S minus A, S minus A, S minus B. So, I can give you sides of a triangle as say 3, 4, 5 or something like that. What is this ratio? So, I think you can very easily solve it. Somebody may also ask you that whether this ratio is greater than or like this. If you are able to see, please solve it. This ratio is always going to be less than equal to 1. Okay, just think about it. How would you get it? Okay, instead of telling you everything at this moment only, this I will leave to you as an exercise, so that when I start the next lecture, I will tell you how. Okay, so as I told you in the last class, circumradius primarily is used. The formula for circumradius that is used is ABC by 4 delta, which on occasions may not be of great help because so much information is rarely provided, and therefore, a viable alternative in that is to use sine law. A by sine A is 2R. Now, moving ahead in this class, we will read about in radius and x radius. And stuff related to it. Okay. So, for in radius, what we can go through is that you are drawing a triangle and a circle is touching all its sides. That means center of the circle is equidistant from the 3 sides. Now, earlier we have gone through the part where we said that points which are equidistant from two intersecting lines will lie on the angle bisectors. Points on angle bisector are equidistant. So, in effect, the in-center of the circle is the point of intersection of internal angle bisectors. Since I is equidistant from all the three sides, it is the intersection of the angle bisectors of the angles of the triangle. Insofar as its value is concerned, we can say area of triangle BIC, area of this triangle, half base into height, area of this triangle half base into height, and area of the third triangle half base into height is nothing but area of this triangle. So, R is equal to delta by S. The good thing about this is any polygon having an incircle, if it has an incircle, has radius area upon semi-perimeter. Because even if it is a quadrilateral, suppose it is a quadrilateral, then we will have 4 such triangles. So, area of this triangle plus this triangle plus this triangle plus this triangle. So, if any polygon has an in radius, then its radius is delta by S. That is always to be kept in mind. Now, if you want to find other expressions for in radius, that is a separate argument, but please this is will be the most widely used expression because of its generality. Further, in a triangle we can have other expressions also. This is A, B, C. This is R, this is B by 2, this is C by 2. So, this side BC, which we denote by A, is R cot beta by 2 plus cot B by 2 plus cot C by 2. Fine. This is a right angle triangle. If we simplify it further, we write this by cos by sine, cos by sine. So, in the denominator we have sin B by 2, sin C by 2. And what do we get in the numerator? Cos B by 2, sin C by 2. Cos B by 2, sin C by 2 plus cos C by 2, sin B by 2. So, this is nothing but, we know this formula in trigonometry, the most widely used formula arguably, sin B plus C by 2. Now we already know from the extended sign law that A is 2R sin. So this is R cos A by 2 sin B by 2 sin C by 2. So small r in terms of capital R is, you write this as 2 sin A by 2 cos A by 2. Fine. So cos A by 2 gets cancelled, everything gets jumbled up together. So it is 4R sin A by 2 sin B by 2 . This 2 is a expression that for a triangle, this is for a triangle that we are expected to remember. This is a very good hint. In that we can say that in a triangle sin A by 2 sin B by 2 sin C by 2 is always less than equal to 1 by 8. So small r is always less than equal to r by 2. In equilateral triangle, small r and capital R have the relation that capital R is 2 times small r. Barring that, r will always be less than equal to r, capital R by 2. So this is one expression. Other thing that we must remember, first that needs to be remembered is r is delta by s, and that is irrespective of the polygon involved, whether it is triangle, whether it is quadrilateral, whether it is pentagon. For other polygons, it is not necessary that it has an incircle. Provided it has an incircle, its radius is delta by s. Okay, this is significant in determining this. Okay, moving ahead. What we can say is that another thing that we need to remember, is suppose somebody is asking you to say find BD, if these are point of contact. So to determine these lengths. Okay. Now, if this length is say x, this would be a minus x. Now tangents from an external point are equal in length, so CE would be a minus x. So this is b minus a minus x. So this is x plus b minus a. This whole side has length c, so c plus a minus b minus x. Okay, so x c plus a minus b minus x. So what is x? That is s minus b. So if a circle, we can draw the diagram again. If a circle is touching the sides at D, E, F, this is S minus B, this similarly would be S minus C, this is S minus A, S minus C, S minus B. So even if we don't remember it, the process is very simple. We should ideally be able to deal with it. Okay. This is b by 2. You can say tan b by 2 is R by S minus B. If you remember, what is tan B by 2? Delta by S into S minus B. So, you can also, this is R. So, R you can say is S minus B tan B by 2. Similarly, the expression could be, and you can have one more expression. So, in trigonometry, you have seen that there are a lot of expressions involved. So, there are multiple ways to represent the same thing. Okay. These things are to be kept in mind, the fundamental notions, as I have been telling you always, that whenever you come across any expression, please be through the process of how did you derive it, how did you come to it. That will be helpful in solving problems. As we see, you will get lot of problems which will involve in circle as well as circumcircle. Some of the questions that we will initially take up, you will see, are comparatively reasonable, might only be using delta by S, or the notion of that angle bisectors are equidistant from the sides. Okay. And then we will move to say x circle and x radius. So, let me take a very simple problem. The problem says that in a triangle ABC, the in circle touches sides BC, CA, AB at D, E, F respectively. If BD, CE, AF are three consecutive natural numbers with BD less than CE less than AF, and CE is equal to, say, let me give you some number. Let it that initially be kept it, we should keep it very simple. Find largest angle of the triangle. Let us write it in a different manner, as the diagram is. So, this is 6. So, this would be 7, and these two would be 5. By some other data we could have find n. Now, this is the largest side. Okay. This is the largest side of this triangle. So we can very easily find what is cos A. 144 plus 121 cosine of the largest angle. Suppose somebody asks find cosine of the largest angle. So we have very easily been able to determine it. Okay. Now let us move to a better problem, say, है ना? That is ABC and PQR are two equilateral triangles having same sides BC, CA, AB are parallel to respectively. Okay, these sides are parallel. If in radius of these triangles is 2 units, find area of region common to both of them. Okay, so this is our question. What is the area of the region that is common to both the triangles subject to the given condition? What is the given condition? That you have two equilateral triangles, their sides being parallel and they are of same size, that is, since they have same incircle, same circumcircle. So the figure that you can possibly draw is you draw a circumcircle, inscribe an equilateral triangle in it, and then now you have an incircle inscribed in this triangle. So I think it is pretty clear and it is very easily identifiable that what you get by the symmetry of the figure is a regular hexagon, isn't it? See, and the incircle is nothing but in radius of this regular hexagon. Now, in's radius is always delta by s. In radius is always delta by s. In radius is given to us as 2. So, this angle is 60 degree, this is 2. So, what will the base be? 2 This is a right angle triangle. This is 2. So this is 2 by root 3. So all in all it is 4 by root 3. So what is delta? R, which is 2, and what is S? 4 by root 3, 4 by root 3, 4 by root 3, 6 times and half of it. So it is 4, 4, 4. It is 12 by root 3. So what is the required area? 8 root 3. Okay. So the region common to both the triangles is 8 root 3. Fine. So you see, it is a very simple problem once you are able to draw the figure. Because of the symmetry, because of the two equilateral triangles involved and parallelism involved, it becomes a very symmetric thing, and we are able to conclude this. This is comparatively, we initially when we have started, we have deliberately taken problems which are easy to handle. As we move on, we will take up some better problems. Fine. Now suppose somebody says, let me take some problem where you will be required to put in some efforts. Fine. Suppose I say in a triangle, in a right angle triangle ABC, in a right angle triangle ABC, angle is 90 degree. Find AB plus AC upon R plus R. So capital R is circumradius, small r is in radius. So it is a right angle triangle. So dealing with it, this is A. Now if you draw its in circle, this is R and this is R. This length we have seen, just now we saw, if you remember. S minus B, S minus C, S minus C. So what did you get? This is S minus C. And you see, this is an angle bisector, so this angle is 45 degree. So S minus A is small r. Further, capital A is 2r. And in a in a right angle triangle, circumradius or circumcircle is a circle with BC or hypotenuse as diameter. So you have S minus A as R. So what is S? So what you can write here? S minus A is B plus C minus A by 2 is R. So B plus C, A is 2 times capital R. So B plus C is 2 times R plus R. So what is being asked? What you have asked is B plus C by R plus R. So it is nothing but 2. Further, what you get is a very important thing. This is the in radius of a right angle triangle. If ABC are sides where A is hypotenuse, this in fact if ABC are integers, R will always be an integer in a right angle triangle. If sides are integers, then if sides in a right angle triangle are integers, then its in radius 2 is an integer. You can see either all three are even, in that case it is definitely an integer. In case there is an odd number, a square plus b square is equal to c square suggests that there will be two such odd numbers. So, their sum or difference, whatever they might be, their sum or difference will ultimately be an even number, and the third side will definitely be even. So, either ways, if the sides of a right angle triangle are integers, so will be its in radius, and you have got a very precise expression and a very beautiful expression for their for its formula or for determining it, b plus c minus a by 2. Fine. Now, let me take up a different problem which may involve some more calculations. Angle A is 90 degree, AB is 20, AC is 15. In circle, touches AC at P and AB at R from C. From B, let us from B a line is drawn from B a line is drawn joining it to P. This line meets the incircle at D also. Okay, D is different from P. Find length. What is the length? AC, P, A, B, R, B, D. So, this is our question. Another right angle triangle, A, B, C. Okay. Okay. So, this is the triangle involved. Now, what is being asked is in circle touches AC at P, AC at P and AB at R. from B a line is drawn joining it to P. This line is being drawn. This is called D. So, we have to find BD. I think we can very easily see, we can find this length, that will give you BP. We can find this length, okay, because we will be able to find AR, and I think now we are done. BP into BD, what we use is BP into BD is BR square. And what are these two? Since this angle is a right angle triangle is 45 degrees, this is R, this is R, this is R, and this is R. Okay. So, these sides are going to be R. And what is R? We just have, generally we can find, but R is B plus C minus A by 2. So, this I think is 15, isn't it? AB is 20, sorry. This is 15, so this will be 25. So, R would be 20 plus 15 minus 25 by 2, which in turn would be 5. Okay, so this is 5, meaning thereby BP (400 plus 25). So this is 5 root 70. This is BP. BD is something that we need to determine. BR is 15. So BD is 225 BR square upon BP, which is 5 root 70. So this is 45 upon root 70. Okay. So we generally get problems where a bit of nuance is needed. But in all the questions, it is not about, as have always been the case right from the very beginning, that we use the expression delta by S, but we have to be conscious of the fact how did we get to it. See, in all the problems that we are doing, we are drawing a diagram, and if needed we go to delta by S. Otherwise, on occasions drawing an appropriate diagram turns out to be sufficient, isn't it? Now, let me digress a bit, or let us, it is a polygon we have not seen. So, let us solve a problem which will involve a polygon, okay, not necessarily a triangle and encircling it. So, let me say ABCD, ABCD is a trapezium with AB being parallel to CD. Further, AD is perpendicular to AB and AB is 2 times CD. Given that let me use the data, given that in radius of this polygon is R and its area is delta. Find R given delta is equal to, what should we say, 4. Let us say it is 4. Okay. So, what is the situation? We have a trapezium AB, CD. AD is perpendicular to AB. Okay. So, AB is perpendicular to AD. So, you can draw something like this. Now, what is being provided with is this is twice this length, this is 90 degree. This polygon has a incircle. So, let us draw that incircle. A rough sketch would suffice. Okay. Now, if this incircle has radius r, these are two parallel tangents to it. So, their distance would be 2r, meaning thereby one side of this trapezium is 2r. This is x. So, this 2 would be x and this 2 would be x, because AB is twice CD. Now, a very important aspect that needs to be remembered, you would have seen it in your NCERT also, that if a quadrilateral has a incircle, if a quadrilateral has a incircle, you can see this tangent is equal to this, these two are equal, these are equal, and so what do we get? Sum of opposite sides, that is PQ plus RS is equal to PS plus QR. Okay, so please keep this in mind. You would have solved it in your NCERT book of class 9th or 10th, that if a quadrilateral has a incircle, the sum of opposite sides, sum of both pairs of opposite sides are equal. That is what we are going to utilize here, that if this is x, this is 2r, this is x, the third side 2r plus BC is 2x plus x. So, this is 3x minus 2r. Since we are given that delta is 4 and we have the universal expression that r is delta by s. So, one expression is delta is rs. So, delta is 4. What is s? You can write s as 3x. This is one expression. The other that we have is that in this right angle triangle, this side is 2r, this side is x, and this is 3x minus 2r. So, 4r square plus x square is 3x minus 2r whole square. So what you have is 4r square plus x square is 9x square minus 12rx plus 4r square. So we have 8x square is 12rx, meaning thereby x is equal to 3r by 2. Now the question was to find r. This is 4 and x can be written as 3r by 2. So this is so you have r square is 8 by 9. So r is 2 root 2 by 3. Again, insisting on the very basic principle, as from very first question we have deliberately said, don't just put in the expression. Using the expression is the last step that you will be needed. Always draw an appropriate figure, try to get the information provided, try to write it down, and the important aspect in such examinations as IOQM is that you don't just jump to an expression. It is never a brute force method that you just write a formula, put values and get it. See, this is the formula that we know. This was arguably the last step that was needed. Okay, so just go through the information provided in the problem, write it, and then see, this is the thing. We may not necessarily remember it, but then we have ample time to reduce it, that from an external point the two tangents drawn are of equal length. So it's just a culmination of that notion. So again, all the questions that we have gone through, we have insisted on that basic simple fact that it is not about reproducing a formula. You know an expression. See, in all the question, ultimately at the end of the day we used delta by s. That is a universal formula, whether it was a triangle or here we are dealing with a quadrilateral. Okay, that has to be, that is something that we have in our pocket. So therefore, just don't jump. It is never a brute force method that you are given expressions and just you have to put in and jumble it up and then manipulate it. Think and then if possible pen down the expression. Now moving ahead, that just draw an appropriate diagram and then try to apply basic notions, and at the fag end if required use the formula what is needed. Okay. Sorry. So insofar as in circles are concerned, let us take one more problem. Suppose we are given not suppose say ABC is a right angle triangle. ABC is a right angle triangle. Angle ABC is 90 degree. Okay, this 2 is provided. Further, a circle is drawn touching AB and BC at D and E respectively. This circle meets the hypotenuse AC at F and G such that DF and EG are diameters of this circle. Okay. A, B, C. If CE is equal to 2, find area of circle outside this triangle. So, this is our question. Okay. You are given right angle triangle, draw an appropriate diagram. ABC is a right angle triangle, angle ABC is 90 degree. AB, BC are the sides AB and BC are tangents to this circle. This thing is to be kept in mind that circle meets hypotenuse AC and F and G such that DF and EG are diameters of this circle. So, okay. So, this is draw a line like this, that will be better. A, B, C, D, E, F, G. What is BE is 2? What is 2? CE is 2. That will make it very small. So, let BE be 2. Do the calculation so that calculations are proper. Okay. So, let BE be 2. So, this length is 2. Fine. So, we have to find this area. This is our question. So, how would we proceed? So, this is whatever is this radius. This radius is 2. Okay, okay, okay. So, that simplifies the process. This is 2. This is also 2. Radius of circle is 2. Okay. This is 2. I think then it's over. BE. Sorry, BE instead of BE, I think I gave you the data correctly. That will solve the problem completely. CE I gave you correctly. Sorry. There will be nothing left that will be required. Okay, if BE is given to be 2. Need to find BE. Okay, so this is 2. Fine. So, how do we proceed? That thing you can see, this is R, this is R, R, R. Okay. This is also R. This is 45°. These two are parallels. This will also be 45°. Fine. 45, 45. So again, this is R. So 2R is 2. So R is 1. So R. So this is just quarter of the circle and just subtract the triangle. So quarter. This is pi by 4 minus half. This is the portion of the circle that lies outside this triangle. Okay, again question done by very basic steps. Another question that we use very elementary steps to solve them. Fine. Now, the portion that we have to go through now is regarding X circles also. In circle we saw what in circle is. Insofar as X circle is concerned, see, suppose you take a triangle. Draw the external bisectors. So, the thing with I1 would be this point, if I say it is I1, it will be since this lies on angle bisectors, it will be equidistant from the three sides. Okay. So, external bisector of BC and internal bisector of angle A. Okay, so let me draw it properly. I drew it initially by rough hand. Let us draw a circle first. Okay, this generally is the better way. A, B, C. These are the three angle bisectors meeting at I1. So, to find radius, we use the same notion. This side is C, this side is B, and the base is A. So, what we do is that we draw perpendiculars. From I1 to the two sides, rather to the three sides. They all will be equal to radius of the circle, which is generally denoted by R1. Now, look at it very carefully. See, area of this triangle is half base into height. Area of this triangle is half base into height, and subtract area of this triangle minus half A into R. What you are left with? What is left? See, this triangle, and subtract this triangle. So, you are left with the original triangle only. So, this is delta. So, delta is R1 C plus B minus A by. So, delta is R1 into S minus A. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, delta is R1 C plus B minus A by. So, R1 is delta by S minus. Okay. So similarly, we can draw one circle here, external bisectors of AC and internal of B, and one circle here, internal bisector of C and external bisectors of angles A and C. So R1 is delta by S minus A, R2 is delta by S minus B, and R3 is delta by S minus C. Okay. Just as we had the expression of 4R sin A by 2 sin B by 2 sin C by 2 for in circle, there will be similar expressions of that notion here also. And the way to proceed, if you remember the way we did there, exactly the same way we will be proceeding here. Okay. So let me just give you a brief idea. So what would we suppose this is the in circle? Okay. This is R1, this is D, this angle is 90, and this is pi minus D by 2, so this is B by 2, and similarly this will be C by 2. So we can say BD plus CD is A. Okay. So what is BD? R1 tan B by 2 plus tan C by 2. This is 2R sin. Now take LCM. Write tan as sin by cos and take LCM. You have cos B by 2, cos C by 2. What will the numerator be? Sin B by 2 cos C by 2 plus sin C by 2 cos B by 2. Sin, this is 4R sin A by 2 cos A by 2. So sin B plus C by 2 is cos A by 2. So what is R1? 4R sin A by 2 cos B by 2 cos C by 2. If you remember properly, the expression for R is 4R sin A by 2 sin B by 2 sin C by 2. So you can say just that because the two bisectors of B and C are external, we simply replaced B by pi minus B and C by pi minus C in the formula of R. So sin pi minus B by 2 is cos B by 2, sin pi minus C by 2 is cos C by 2. So similar expressions you are going to get for R. So we have already gone through most of the things. At the very end we are left with say x radii and distance between special points. X radii in last class we discussed. I hope you remember in last class we said we formed x radii. So x radii we wrote as R1 is delta by S minus A is 4R sin A by 2 cos B by 2 cos C by 2. This is what we read. I hope you remember from our last class. Further, similarly you have R2 as delta by S minus B, that would be 4R sin B by 2 cos C by 2 cos A by 2, and similarly R3.
4r sin c by 2 cos a by 2 cos b by 2. Okay. R, I am absolutely sure you remember the general formula of delta by S, and for a triangle it is R, as we have already gone through. Delta by S is a universal formula, that is any polygon having an in radius is the in radius is delta by S. Fine. Now, some relations between R1, R2, R3 and R. One relation that is very useful is that 1 by R1, 1 by R3 is equal to 1 by R. Okay, you can simply see to it S minus A plus S minus B delta. So, 3S minus A plus B plus C, which is 2S, this is 1 by R. So, this is one relation that holds for R1, R2, R3. Another relation that holds is 1 by R1 square plus 1 by R2 square is A square plus B square plus C square by delta square. You can see this is S minus A whole square plus upon delta square. So, what does this become? 4S square minus 2 times upon delta square. Fine. 2S is A plus B plus C. So, this is also 2S. This and this gets cancelled out and you get the desired result. Yet another relation which I feel one can remember is R1 plus R2 plus R3 minus R is 4R. Okay. So, since you have to find 4R, it is better that we use this expression R1 plus R2 plus R3 minus R. Okay. So, R1 plus R2 you have cos C by 2 common, R3 minus R you have sin C by 2 common. So, R1 plus R2 is 4R cos C by 2 into sin A by 2 cos B by 2 plus sin B by 2 cos A by 2. So, R1 plus R2 is 4R. This is sin A by 2 cos B by 2 plus sin B by 2 cos A by 2. This becomes sin of A plus B by 2, which is cos C by 2. So, 4R cos square C by 2. R3 minus R, you have 4R sin C by 2 as common, and then you have cos A by 2 cos B by 2 cos of A plus B by 2, which is sin C by 2. So, this is 4R sin square C by 2. So, R1 plus R2 plus R3 minus R is 4R. this is one thing that may on occasions be needed. Okay. Now, say somebody asks you to say for my equation for a cubic equation whose roots are R1, R2, R3 and R. So, R1, R2, R3, sorry, that will be 4-degree equation. So, R1, R2, R3. So, x cube minus R1 plus R2 plus R3 into R into x plus R1, R2 minus this we write as 4R plus R just from our previous question that we did. This, if you remember, here we can use R1, R2, R3. We can write this as R1, R2, R3 into 1 by R1 plus 1 by R2 plus 1 by R, which is 1 by R. So, R1, R2, R3 you can say is S minus A, S minus B, S minus C upon delta Q. Sorry, I wrote it just the other way around. One is not, very sorry. Delta cube by S minus A, S minus B, S minus C. This gets, it is S delta, delta S. So, the equation becomes, this is delta S upon R. R you can write as delta by S. So, it is S square. So, the equation becomes x cube minus 4R plus R into x plus S square x minus product we just saw as S delta. Okay, so this is the equation whose roots are R1, R2, R3. On occasion somebody may give you and then ask you about the triangle, give you this relation and ask you about other things in the triangle. Fine. Now, you may be given information regarding this, but primarily what is of help, as I have been constantly conveying you, is that these relations are just that they are there. They are generally not required directly. We must know the working, how to get to them, followed by some manipulations, but it is always to be preceded by the basic steps. We must know how did we reach to this point. Okay. Now, let us discuss a triangle whose vertices are the x centers. A triangle whose vertices are x centers of the triangle. Okay, it is called x central triangle. So, if this is a triangle, say, if this is the triangle, let me and suppose I draw its internal and external bisectors. The diagram may not be properly drawn. Say something like this. So this is our triangle. These are our X centers. It is not drawn properly, but so be it. Now these are internal angle bisectors, so this angle is 90 degree. This angle is 90 degree. This angle is 90 degree. So this point I is orthocenter of I1, I2, I3. Okay. Further, if you see further, if you want to know sides in terms of say ABC, so this angle is, we have to find these angles. This angle is pi minus b by 2, so this angle is b by 2 and this angle is c by 2. So angles of this triangle are b plus c, that is pi minus a by 2, pi minus b by 2, pi minus c by 2. These are angles of this triangle. Insofar as sides are concerned, so this is say R1, okay. This is R3, and similarly this is external angle bisector, so this will again be b by 2. So what is side I1, I3? What is I1, I3? If you write it, say I1, I3 is R1 upon sin b by 2, isn't it? This is hypotenuse, plus R3 upon, this is, no, R1 upon cos b by 2, R3 upon cos b by 2. So what is R1 upon cos b by 2? 4R sin a by 2 cos c by 2, sin c by 2 cos a by 2. So this is 4R that is 4R cos b by 2. Okay. So this is the sides are 4R cos a by 2, 4R cos b by 2 and 4R cos c by 2. Instead of results, we must know the working. Okay. Results are rarely directly asked for. We must know how did we arrive at them. Further, in radius suppose somebody says what is the circumradius? So A by sin A 2R. So you can say R1 is 2R. For I1, I2, I3, ABC is the triangle which is formed by foot of perpendiculars. Okay, and you can see these two angles are equal. So, I1, I2, I3 is X-central triangle of ABC, and ABC is called orthic triangle of I1, I2, I3. And it is a special pedal triangle. Okay. Very, very important information that must be known is that suppose we a light ray comes along this line, after getting reflected by I1, I2, it will move like this. Angle of incidence is angle of reflection. After getting reflected at this point, it moves like this. So, it reaches this point. So, this is the triangle with least, again I am saying, this is the triangle with least perimeter whose vertices are on sides of the triangle. Okay, because light ray travels along a path so such that it covers the least possible distance. Angle of incidence is angle of reflection. Okay, see what I am trying to convey is that suppose you are given a triangle and you are being asked to find the points on this triangle, one on each sides of this triangle, such that the perimeter of the new triangle that you form is least. So, what we do is that we draw altitudes and then we say this is the triangle with least perimeter. This is the triangle with least perimeter. It is called orthic or pedal triangle. Pedal triangle is, see, for pedal triangle, from any point if you draw perpendiculars to the sides and join this, this is called pedal triangle with respect to this point P. So, this orthic triangle is nothing but pedal triangle with respect to the orthocenter. Okay. Now, if you want to know sides, if we have solved this one, I think from here we can conclude what are the sides of pedal triangle. So, this is, I think the side angle came out to be pi minus a by 2. Okay. So, this angle is pi minus a by 2. Okay. If this is X central triangle, if this is A, this is pi minus a by 2. Okay. So, if this is theta, this is pi minus theta by 2 is A. Okay. So, theta is pi minus 2. So, angles are pi minus 2A, pi minus 2B, pi minus 2C. if this triangle has circumradius r, orthic triangle has circumradius r by 2. So, sides are 2r, which is r sin pi. This is r sin 2a, r sin 2b and r sin 2c. Okay. And what is the circumradius is r by 2. What is worthwhile is remembering this much. देखिए ना, the orthic triangle is a triangle whose sides are, sorry, whose vertices are the foot of perpendiculars drawn from vertices to the sides, and this is the triangle whose vertices lies on sides of the given triangle, with the new triangle having the least possible perimeter. Okay, this angle being this equal to this angle ensures that. Okay, so please keep this thing in mind. This is on occasions helpful even in this year's ISI. The question was asked that so that for every acute angle triangle there exist points on the sides such that if a ray of light starts from point, after getting reflected by the other two sides, reaches the same point. That simultaneously also ensures that this is the triangle with least possible perimeter. Okay. So, there are ways to ask the same question. Some details that we must know of some of the triangles, some of the special points, the distance of orthocenter from sides in an acute angle triangle, distance of orthocenter from sides and vertices. The diagram is being drawn for acute angle triangle. So, this side is C, this is C cos B, we need this angle, okay. This is C. What is this angle? This angle is C, 90, 90, this is C. So, you can say CH, sorry, BH upon C cos B is equal to 1 upon sin C. So, what is BH? C is 2R sin C, 2R cos B. Sin C gets cancelled. So, this is 2R cos B. So, this is base, this is 2R cos B cos C. Fine. So, this is the distance of orthocenter from the sides and vertices. From vertex, if you want to remember, it is simple. From vertex A it is 2R cos A, from vertex B it is 2R cos B, from vertex C it is 2R cos C. And from side BC it is 2R cos B cos C, from CA it is 2R cos C cos A, and similarly. Okay. Now moving ahead, this result will be helpful if you want to prove this. See, we have used the result that circumcenter centroid orthocenter are collinear. And OG is to GH is 1 is to 2. So, one way in trigonometry we establish it is like this. Suppose you draw a triangle, say this is altitude, okay. This is our orthocenter. Midpoint. This is midpoint. Above it will be our O. AM is the median. Now you can very carefully see what we say is that let OH meets median AM at P. We have to show that P is nothing but centroid of this triangle. So, how do we go about it? This is 90. So, this will also be 90. This is 90 because this is perpendicular. AH we have just calculated as 2R cos. OM. Now, in a triangle, this angle is A, this is also A. So, at the center, this is R. So, what is this? This is R cos A. These two are parallel lines and this angle is definitely equal to this angle. So, these two are similar triangles. So, OP upon PH is AP, sorry, is PM upon AP is OM upon AH. So, what is OM upon AH? Half. So, P divides MP in the ratio 1 is to 2. Hence, P is centroid of this triangle. So, P is centroid of this triangle. This is what we had wished to establish. Simultaneously, we have proved that this is the centroid and this ratio is 1 is to 2. A very pertinent and useful result. You will see that it is used very often. Lot of times this is of great help. So, in, not only in geometry but also lectures for geometry IOQM. This is the lecture where we would be learning distances between special points, in center, orthocenter, circumcenter.
So, these are the points that we are looking for. Fine. Now, one of the primary objectives in all these questions would be to use either geometry or cosine law. The important aspect in all these things, say distance between, suppose I say in center and ortho center, in center and circumcenter, circumcenter and ortho center, circumcenter and in center and ortho center. Centroid is altogether a separate issue, because these three involve angles. So, angle chasing might help you in dealing with them. In the so far as centroid is concerned, it's bit different, because when we draw medians, they generally don't involve angles. You get midpoint, so that will primarily be a notion of length chasing. Here we will use length chasing and angle chasing and then proceed. For example, distance between let us first standard distance between in center and circumcenter. One way to deal with them is to deal with this specific issue is because it involves two circles, angle chasing and using properties of circle. Other is, of course, as I told you earlier, angle chasing. So, let us first deal with it in pure geometrical way, then we will deal with it in using trigonometry, because in other cases trigonometrical approach on occasions is of great help. So, suppose this is a triangle, this is a circle, and let us inscribe a triangle in it. Okay. Now, let me also draw it in circle. Suppose this is its in circle. So, A, B, C is the triangle. Say I is in center of this triangle, and say O, for example, let this be the circumcenter. So, we have to find distance between in center and circumcenter. So, this approach primarily uses the notion of geometry. So, what we do is that we draw AI and say let it meet here at say L, and then from L we draw diameter of this larger circle, that is the circumcircle, and let this point be M. Okay. Now, we have to find IO. So, what we do is that we draw I, the diameter passing through I, and let it be PQ. The perpendicular is say D. One thing that you can very easily see, that AI into IL is OP, we have to find IO is equal to IP into I. Okay. Because these are for concyclic. Now, the purpose is to determine AI into IL. Now this angle is 90 degree and suppose this angle is alpha. This angle is 90. Which other angle you know is 90 degree? See, this is diameter of the circle. So let me join B and M. Fine. Now we can say these two angles are equal. So triangle ADI and triangle ADI MBL are similar triangles. Fine. So from here I think we can find AI. No, it will not involve IL. Okay. Let me see what do we get. AI is opposite to 90 degree and ML is opposite to 90 degree in MBL is equal to ID upon BL. So AI into BL is ID into ML. What is ID? Small r. What is ML? This is the diameter, 2r. So what is left is to determine BL, relation between BL and IL. BL and IL. Okay. Now, since this is the in center, okay, so we can find this angle. Suppose this angle is B by 2, isn't it? Uh, uh, See, this angle is A by 2, A by 2. Okay. So chord CL subtends an angle A by 2 here. So this will be A by 2. Okay. B by 2. So this angle is C. Angle in same segment. So this is A plus B by 2. So this is also A plus B by 2. So which two sides here are equal? These two sides are equal. IL and BL are equal. That serves our purpose. So from this triangle we can say IL and BL are equal. So AI, BL is nothing but IL. So this is 2RR is IP into I. What is IP? Now if this distance is D, IP is R minus D. And what is IQ? R plus D. D is the distance we are looking for. So 2RR is R square minus D square. So D square is okay. So the distance between in center and circumcenter is root, sorry, R square minus 2R. Fine. This is a very good way to say that R is always greater than equal to 2R. And we did it some other way also.
but radius is always at least twice the in radius. In a equilateral triangle, they coincide, so this becomes 0. R is equal to 2R. Fine, so this is a geometrical way because it involved circles, two circles. We could use in fact, everything here we use is geometry. We could have proceeded it using trigonometry. In trigonometry, or so to say in algebra, the algebraic ways are generally consistent. That is the thing. Therefore, you can apply it. It generally requires less ingenuity to apply methods of trigonometry because processes are more or less fixed. Okay. Now, if we move ahead and say, sir, now let me tell you the same thing using trigonometry. So, how do you do it? This is a triangle and say this is your circumcenter, this is your incenter. Okay. I, O. A, B, C. So, this distance OB is capital R. This distance R is R, sorry, cosec B by 2. And our purpose is to determine this angle and use cosine law. That is how we proceed here. So, see, the process is very simple. Now, how do you get to this angle? This is circumcenter. So, if this is circumcenter, this angle is A, so angle at the center is 2A. So, this angle is A. So, this angle is pi by 2 minus A. And what is this angle? B by 2. So, our required angle theta in the diagram is B by 2 minus B minus pi plus 2. So, A plus B, see, A plus B minus pi is minus C. So, what do you get here? A minus C by 2. Now, IO square is R square plus R square upon sine square A by 2 minus 2 R into cos A minus C by 2. Okay. So, what is this? This is 4R square, sorry, R is 4R sin A by 2, sin B by 2, sin C by 2. So, this would be 16R square sin square B by 2 minus 8R square sin B by 2, sin C by 2 into what you are left with is cos A by 2 cos C by 2 plus sin A by 2 sine c by 2. So, this is r square. Now, see sine square a by 2 sine square c by 2 plus 8r square sine b by 2 sine c by 2. And what you are left with is sine b by 2 sine c by 2 minus a minus c b by 2 na. So, sine a by 2. So, what you are left with is b by 2 c by 2, and this is sine a by 2. What this angle is b by 2. Okay, this angle is a. So, this is pi by 2 minus a, absolutely fine. B by 2 minus pi by 2 minus a. So, b minus pi plus 2a. A plus this angle is a minus c by 2. Is there some error in between? Sine b by 2 sine c by 2. This is not cos b by 2 cos c by 2, isn't it? Oh, this is b by 2. Okay. Very sorry. This is a by 2. A by 2. A by 2 and cos a by 2. Okay. So, what is IO square? So, IO square is r square plus 8r square. This is minus cos a plus c by 2. So, it becomes minus sine b by 2. Minus, so minus into 4r sine a by 2 sine b by 2 sine c. So, this is algebraic method. Everywhere this is how we will proceed. So, this is the distance between in radius, in center and circumcenter. Of course, this is a more elegant way to deal with it. I just told you this because in others, see, the process will remain the same. If you want to find distance between orthocenter and circumcenter, this is the process we will follow. This is the good thing. Of course, it is algebraic, so it is based on processes. In geometry, you always require a bit of ingenuity, a bit of niche, a bit of elegant thought to deal with things. Fine. So, this is to be kept in mind because the expression is reasonable. Suppose I say, let me solve a problem in this, the direct result of this would be in an isosceles triangle, angle ABC is equal to angle AC. The orthocenter of triangle ABC lies on its incircle, or let's say circumcent. Incircle. Find cos of angle. So in this problem, I will tell you how to find the distance. Okay. Now, this is a simple figure. Because it is an isosceles triangle, this will be the angle bisector, this will be the altitude. What you are given is that the altitudes are like this. This is H, this is I, this is D. There are ways and means to deal with it. If you remember our last class, one thing is we say that this distance is small r. For that we need to know distance between in center and ortho center. One way to deal with it is like this. Other way is we know distance between ortho center, sides and vertices. Distance of ortho center from this. I hope you remember in last class we wrote it as 2r cos B cos C. This is in this particular case 2r. Okay. So, r B is equal to C is equal to pi minus a by 2. Okay. So, what you will do is r sine square a by 2, isn't it? Is r sine a by 2, sorry, 4r sine a by 2, sine b by 2, sine c by 2. So, sine a by 2 is 2 times 1 minus, sorry, 2 sine square b by 2 is 1 minus cos b. What is cos b? Sine a by 2. Sine a by 2 is 2 minus 2 sine a by 2. So, sine a by 2 is 2 by 3. If sine a by 2 is 2 by 3, we can say cos a is 1 minus 2 sine square a by 2. This is 1 by 9. This is how we used it. Now, if we wanted to use this distance, so insofar as this problem is concerned, we didn't require the expression if we remember this, the distance of ortho center from sides, which we did in our previous lecture. I hope you all remember it. Now, we could have also said that this distance is equal to small r, distance between ortho center and in center. So, now let me first write an expression for ortho center in center. Okay. So, distance between ortho center and in center. So, we will proceed in a similar manner.
H. Fine. Now you have in center, so say this is the in center. Okay. Say this is in center. Okay. So you draw this line. B, C, A. Okay. Now, distance of orthocenter from B is 2r cos B. This is r cosec B by 2. This is B by 2. And what is this angle? If we extend it further, this is 90, this is C. So, this angle is 90 minus C. So, R angle theta is 90 minus C minus B by 2. So, this is 2 180 minus 2C minus B. This is 180 this is A minus C by 2, isn't it? So, we know all the requisite things. Now, we will apply the formula. 4r square cos square B plus 4r cos B into cos of A minus C by 2. You see the expression, okay, may not turn out to be as beautiful as has been the case with other situations, but the process that is being followed remains the same. What we do is that we write it as 1 minus sine square B, and then we tend to manage it. So, let me write it formally. 4r square cos square B plus 16r square sine square A by 2 minus 16r square cos B sin A by 2 into cos A by 2 cos C by 2 plus sin A by 2. So, this becomes 2, 4 and 16r square minus cos A by 2 sin A by 2 minus 16r square, say cos A by 2 sin A by 2, that becomes sin A. So, 2 4r square. So,
sin A sin C cos B upon 4 minus cos B. So what you get in turn is, let me write it from here. What do you get is 4r square cos B into cos B minus sin A sin C, isn't it? And what you are left with is 16r square sin square A by 2 sin square C by 2 into 1 minus cos B. Now here, if you think correctly, see, uh, let me write it here, 4r square cos B. What you are going to get is minus cos A cos. Cos B is minus cos A plus C minus sin A sin C minus 32 2 into 4r sin A by 2 sin B by 2 sin C by 2 whole square. And what is this? Minus times cos A cos C minus sin A sin C. So sin A sin C gets cancelled out. So what we are left with is 2r square minus 4r square cos A cos B cos. So this is the expression. Okay. So this is the distance between in center and ortho center. This would have been a tedious exercise. Suppose we know it and we say this is equal to small r square. That I think would have taken us a bit, longer to resolve the previous question. Fine, but the process remains the same. And similarly, distance between ortho center and, that is I think a reasonable expression. Distance between ortho center and circumcenter. And circumcenter. So we will again draw the same diagram. This is the utility that we have. This is the utility of trigonometry or algebraic methods, that they are consistent. The situation, depending upon the situation, we don't generally change the methods. Whereas in geometry, corresponding to a situation, we need a bit of ingenuity to deal with them. Suppose this is A, B, C. Now we suppose circumcenter is this point. Fine. If this is O, this is R, this is 2R cos B, this angle is pi by 2 minus, we just did it, I think some. This angle, we just saw it. What is this angle? This is C, this is pi by 2 minus C. So, this angle theta is pi by 2 minus C. This is A minus C. Okay. Now, OH square is R square plus 4R square cos square B minus 4R square cos B into cos A minus C. So, this is cos A plus C with a minus sign, that is why we have taken it as common, plus cos A minus. Okay. Now, this is R square minus 8R square cos A cos B cos. A better expression, much better than the previous one that we have got. Isn't it? So, these are the distances. We must know the method. See, some beautiful questions may appear here. Now, somebody may say, I think I remember one beautiful problem asked earlier, that if this triangle is isosceles, okay, so we know all the angles. Now, from knowing all the angles, we are able to determine some relations. Fine. So, say one of the triangles is isosceles or stuff like that. That is a very relevant thing. Okay. This is, suppose this is asked, orthocenter and circumcenter. Now, if this triangle is isosceles, so these two sides or these two sides are going to be equal. These two are generally not equal. Okay. Suppose somebody says circumcenter lies on, just as the problem we did, I thought it is the problem of where we will use R square minus 2RR, but unfortunately I used orthocenter. Distance between orthocenter and in center we have found out. If somebody says distance between circumcenter and in center is small r, or somebody says circumcenter lies on the in circle, so that will give you R square minus 2RR is R square. And somebody may ask you what is R by R. So, you can use quadratic to solve it. Or now, once we know the distance between orthocenter and circumcenter, so we know that centroid lies on this line and this ratio is 1:2. So, OG and GH is calculated from here only. Okay. OG, suppose we want to calculate OG and GH, then this will be the thing that we will be using. Cos A cos B cos C, is there a good expression for cos A cos B cos C? What is R cos A? 90 degree A. This is R cos. This is R sin. Is there a good expression for cos A? But distance between OG and GH would be simply 1/3 and 2/3 of these distances. Suppose somebody says find GH, so it will be 2/3, or say if you take square 4/9 of this. Cos A cos B cos C, is there a good expression for cos A cos B cos C? In terms of sides, somebody says in terms of sides, is there a good expression? If we write a square, that will be a very big thing to write. That is definitely not something that we should opt for. Cos A is B square plus C square minus A square upon 2BC. That will be too big an expression. Leave it, sir. I roughly recall that it is a good expression. Cos A cos B cos C. No. Now, so these are distance between special points. That was the purpose. Now, this is all in all the theoretical notions that we needed to know for what we have to do in geometry. Pure geometry we went through. We went through stuff that are required from very basics. We went through Seva's theorem, Menilow's theorem. Then we did a bit of trigonometry followed by SOT. Basic proportionality theorem was also discussed. So, all in all, what we have done is that we have covered almost everything. Definitely there is some lack of practice in the classes, in the sessions that we took. So, in one or two sections that we are going to take further ahead, we will take only problems. More or less all the theory is covered. We will take up some practice sessions of problems that could be expected, because now we will not be confined by the notion that what we have taught, what is remaining, what is not remaining. Everything that almost needs to be covered to the best of our knowledge has been taken care of. Moving forward, we will take up problems where we may use trigonometry, where we may use geometry. So, I have chosen some problems from previous year questions, 24, 23, 22, so that you get a feeling of what exactly you do when you solve a problem. Okay. So, without much ado about anything and without wasting much of your time, let us now proceed. So, this is a question, this is one of the easiest questions that has been asked. So, sometimes you wonder why questions like these appear. You may feel shocked when you see the solution. Okay, so let ABCD be a quadrilateral. Angle ADC is 70 degree. Suppose A, B, C, D. Okay. Angle BAD. Okay, this is 110 degree. So, this is 110 degree. Okay, now ADC is 70 degree. ADC 70 degree. Okay. And ACD. This is 70 degree. This is 70 degree. ACB. Angle ACB is 10 degree. This is 10 degree. Okay. So, you have to find the measure of angle CAB. So, this is our question. Okay. So this angle is 40 degree. Fine. Now, if this is 40, okay, now we have to find CAB. So this is the angle that we need. ADC is 70 degree. ACB is 10 degree. BAD is 110 degree. Sorry. BAD. Sorry. BAD. This is 110 degree. ACD. ADC is 70 degree and ACD, ADC. ACD. Okay. So let me draw an equilateral triangle. Okay. This is 110 degree. ADC 70 degree. And then ACD is also 70 degree. CAB. How come? BAD is given to is 110 degree. So this becomes 40 degree. BAD is 110 degrees. So CAB is going to be 70 degree. What is the use of ACB being 10 degree? Again, that is what I told you, that this is one of the easiest problems that you can think of. Probably they wanted to ask something else. It turned out that incidentally they have asked this. So this is basically, even your school text might have, this also gives you a situation that these two are parallel. Okay, 70 degree, 70 degree, 70 degree, 110 degree, ADC. Okay, again, we don't expect such easy problems, but this is the problem of 24 or 23, I don't exact, 24 most probably. So you also can, you rarely get problems of this nature. In fact, even I was surprised when I solved this problem, that am I missing something, you know. So we generally don't expect questions of this nature. Now this is, consider a square ABCD of side length 60, EF be the points on CD. So I have chosen problems sequentially, okay, from very easy problems to reasonable, and then we'll move ahead. ABCD, EFB points on CD. CD is also C, okay. You divide it in the ratio, you trisect it. CE is EF is FD. Line BF and AE. BF and AE meet at M. So area of triangle MEB. So this is 16. Okay. Now this is 16 by 3. This is 16 by 3. This is 16 by 3. Okay. So triangle MEF is similar to triangle MAB. Okay. So you have to find area of triangle MAB. So if this height is H, this height is going to be 3H. And this whole height is 16. So 4H is 16. So this is 12 and this is 4. So area of triangle MAB is very simple, half 12 into 16. This is 96 square units. So 2 marks problem on occasions may be demanding, but on occasions they may turn out to be very, very reasonable.
These are the problems that we are expected to definitely solve. Easy problems, we must have a knack of picking what are the problems which are reasonable in nature and then proceed. That will be a very, very important factor in attaining the maximum possible potential that you have. Okay. So, these again you see these are very simple problems. Even in our classes that we took, in the sessions that we have taken, you would have seen that the problems there were comparatively more demanding. These would have been the problems at the very, very initial stages. But whatever we have gone through in the initial stages do hold key as we move on, and on occasions they are specifically asked. So, similarity, congruency, parallelogram, parallelism, those things, alternate, uh, opposite angle, vertically opposite angle, these things are to be kept in mind at all points of time. Fine. This is a bit problem, bit lengthy. Let ABC be a triangle in XY plane where B is at origin. BC be produced to D such that BC is to CD is 1:1. So, let me draw the figure in a separate sheet. See, BC is produced to D. First, followed by CA be produced to E such that CA is to AE. CA is to AE. Okay, so let me suppose this is point A. This is produced to E. This is 1:2. CA is to AE is 1:2. AB be produced to F such that AB is to BF. Okay, is AB is to BF is 1:3. Is 1:3. Now, be the centroid of triangle ABC. Okay, and AB is produced to F such that AB is to BF is 1:3. Let G, centroid of triangle ABC. Okay, centroid of triangle ABC G is given as 32, 24. Now, DEF. DEF. This is given to you as origin. GK. Okay, okay. Centroid of DEF is said to be K. Okay, now since coordinates are given, let us utilize B is 0, 0. This is say alpha, beta. So this is 2 alpha, 2 beta. Say vertex A is gamma, delta. Now in coordinate geometry, you would have gone through all of these things. Okay, this is primarily a problem of coordinate geometry, not pure geometry. Pure geometry, it would have been a beautiful problem. Now, what is given to you is 1:3. This is gamma delta, so this is -3 gamma -3 delta. And we have to further find C. So, this is 1:2. Okay, so if this is x, y, what you have is x plus 2 alpha by 3 is gamma. So, x is 3 gamma minus 2 alpha. And in the similar vein, this is 3 delta minus 2 beta.
Okay. Now, if you look at it very closely, these are DEF. Now, centroid of DEF is, if you look at it very carefully, 2 alpha, 2 alpha, 3 gamma, 3 gamma, they all get cancelled out. Centroid of GEF, DEF is 0, 0, which is your point K coincides with B. So, you have to find GK, which is as good as distance between B and G. Okay, so this turns out to be a comparatively simpler exercise. 8 you take off outside. So, this is 4 square plus 3 square. So, this is 40. Isn't it? This is what? Length GK, this turns out to be 40. You understand that the angles that are given, sorry, the answers that are to be given are 2-digit numbers from 00 to 99. Okay, so you write 2 digits even when answer is say 4, you write it as 04. Now let me now move ahead. This is the x radii of a triangle R, 21 by 2. So this is R1. What is R2? 12 and R3 is 14. If the sides of triangle are roots of x cube, okay. So sides are, that is x cube minus a plus b plus c into x square plus ab plus bc plus ca into x minus abc. This is the quadratic. So P is a plus b plus c, where abc are sides. Q is ab plus bc plus ca, and R is abc. So what we have to find is PQR. Okay, now R1, R2, R3 are known to us. So what we know is R1 is delta by S minus A. R2 is 12 and R3 is 14. Okay, S minus A, S minus. Further, S by delta. That, and now suppose if we have to find A, B, C, okay, let us first multiply them. Okay, so what you get is R1, R2, R3 is delta cube upon S, S minus A, sorry, fine. In fact, if you multiply it by R, you will get delta square. So R you can very easily find. Okay. Okay. So if you multiply it by R, it becomes, this is delta square. Also what we know is that will give you AB plus BC plus C. Okay. This you can easily find. ABC. 1 by R1, so R is delta by S. Okay, AB plus BC plus CA. We have to find the integer. Okay, that we have to effectively find PQR. So delta square. Okay, we will get delta and then we will find that. Fine. Now 1 by R1
S minus A, S minus B, S minus C is, see when you add them up 3S, so this is 1 by R. So this is 2 by 21 plus 1 by 12 okay, so you will get R from here. So 7 for your 20, 56. Why are we writing 7 again? What is the LCM? 3 into 7 into 4. So this is 8 plus 7 plus 6. So this is 8 plus 6, 14, 21 by, this is 1 by 4. So R is 4. If R is 4, you find delta. Okay, once we find delta square, so if R is 4, R into R1 into R2 into R3, this becomes 4 into 21 by 2 into 12 into 14. So 2, 2. So delta square, what is delta square? 2 into 3 into 7. 12 is 4 into 3. And 14 is 2 into 7. So what is delta? 2, 2, 3, 7. So delta is 4 into 21, 84. S you can find, okay, now S you can find, you know delta, R is delta by S. S is delta by R. Delta you have found out 84 by 4, this is 21. So S is 21, so A plus B plus C is now 42. Okay. Now R1 is okay, A square plus B square plus C square, that is how you get ABC. S you know. Okay. Now you see another important result that we have is 1 by R1 square plus 1 by R2 square is delta square S minus A, S minus B. So you have plus S square. This is A square plus B square plus C square by delta square. So you get A square plus B square plus C square. And do we have some expression for what is R1 R2 plus R2 R3 plus R? See, R1 R2 is delta square by S minus A, S minus B, S minus C into S, isn't it? So this is S square. Okay, we would have found S directly. Okay, anyways, this is S square. Now from these calculations, 1 by R1 square, delta square we are aware. These expressions we are aware, we can find a square plus b square plus c square. Once we find a square plus b square plus c square, we know this, we can find ab plus bc plus ca, okay. So now let me do the calculation. 1 by R1 square is 4 by 441, okay. 4 by plus 1214, 1 by 144, 14 is 196 plus 1 by 16 is delta square is 84, okay. Delta I think is 84, so 84 into 84. Now this is a very typical calculation if you think of it. So what other way we can find AB plus BC plus CA? R1, R2, this is S square. Okay, what is S square? Okay, A plus B plus C whole square by 4. It will be more or less square plus, that will be calculative. AB plus BC plus CA. S we can get from there, okay. This is a very demanding calculation in my eyes. What is A square plus B square plus C square? 84. See, 4 into 84 into 84 by 441 is 21 into 21 plus 84 is sorry, plus okay. So this is 4, 4. So A square plus B square plus C square is 64 plus 49 plus 14 into 6, sorry, 36 plus 441. So this is 10 times 0, 2, 4 to 6, 3, 9, 4, 13 and 6, 19, 590. This is A square plus B square plus C square. We already know A, B, C. So we have known A plus B plus C, I think we calculated as 42. 42. A square plus B square plus C square we have calculated as 590. 590. So from here we can say 42 into 42. So 42 square is 1604 plus 320. 1604 plus 320 is 1924. Okay. Isn't it? 842 into 4, 16888. Eh? What is 42 square? 40, 1600. 40 into 2 into 2. 160. Okay. 1600 plus 160. 1764 is 590 plus 2 times AB plus BC plus CA. So AB plus BC plus CA. 295. So 7, 8, this is 587, AB plus BC plus C. Now the only thing that is left is to find AB plus BC plus C, sorry, A into B into C. So we know S into S minus A into S minus B into S minus C is 84, that is 21 into 4. Okay. So you get 21 cube minus 21 square into A plus B plus C, which is 42, plus 21 into AB plus BC plus CA. So you calculate ABC as 21 cube as 21 into 587, 7, 5, 4, isn't it? 0, 3, 1. So 21 into 130. 13 1 ja 13. 2730. So this is ABC. So ABC is 2730. This is 2730. This is 587. 587. Now you have to add all of them. So this is 9, 8 plus 4, 12, 3, 15, 1, 6 and 7, 13, 3359. So this is root of 3359. So 60 square is 3600 to 60 minus 1 whole square is 3601 minus 120. 3481. Okay. 3481. So 58 square is 3604 minus 240. 3364. So the nearest integer to this is going to be 58. So you look at the calculation involved, maybe the solution could have been simpler. I just whatever identities I could remember, I just penned it down. But look at the time it has taken, and maybe there could have been a better way to calculate it. I don't deny it, but just I took a question. I thought it is very doable. I just took it, है ना? So I think there might we might involve better identities to solve it. That I am not denying it, but just whatever is struck to my mind. Okay, this is the utility. Even though I don't find that this question is very good, uh, or it is up to that point where it should be asked in examination, because it is asking so many facts. Formulae application, explicit application of formulae, I don't think so that is the intent of paper setters. Anyways, it has been asked, we cannot deny it. Now the next question is, in a triangle ABC, let E be the midpoint of AC. Okay, in triangle ABC. E be the midpoint of AC. And F be the midpoint of AB. The medians BE and CF. The medians BE and CF intersect at G. So this is what we say is centroid. YZ, okay. YZ are midpoints of BE and CH. Okay, ZYZ, okay. Now, we know area of triangle BGC. Area of triangle BGC is 1/3 area of triangle ABC. So here it is 160. 1/3 of 480. I think we can very easily conceive of this notion. Okay, that they are all parallel. That much I think we don't need to prove is very explicit. Now if these are similar triangles, so we know BGC. Now this is 2/3 of this median. BY is half, so 2/3 minus half. So if BE, see if BG is 2/3 BE, okay. So GY is 2/3 minus half of BE. So BE by 6. So BG by GY, okay. BG by GY is so GY upon BG is 4. And now we are through. These are similar triangles. We have found the ratio of sides. Okay. If this is the ratio of side, ratio of areas will be square of it. This is 160, so area of triangle GYZ is going to be 10 square units. Okay. See, the previous problem just involved calculations. These are better problems. These are the problems that are meant to be asked in examination. Fine. So now moving ahead to our next problem. So you are given a triangle ABC with AC side, one of the side is given as 20 is inscribed. So you are also given its circumcircle. A tangent is drawn to it to omega through B. Okay, at vertex B you are drawing a tangent. Fine. So you draw a tangent at vertex B. Fine. Now this has been named as T. Now the distance of T from A is 25. So you draw perpendicular from A to T, perpendicular from C to T. This is 25, this is 16. If S denotes the area of triangle ABC, okay. Now let us first assume, say O is the circumcenter. This is 90 degrees. Say these perpendiculars are M, N. Right? Now let me now we have to find area of these triangles. One of the sides is known to us 20. Now if you look at it very carefully, see these are perpendicular. So whatever is the length of perpendicular from O to AM. So this is MNOP, say S. So these two are going to be equal. This is a rectangle. Now we can find OS by saying this is 25, this is 25 minus R. This is R, so we can find OS as (25) into 2R minus 20. This is OS. And therefore, we can say AB is root of 25 square plus 25 into 2R minus 25. So AB is 5 root 2R. In a similar vein, we can say BC is 4 root 2R. Let me not get involved in all the calculations. Now, insofar as area is concerned, area is half AC into AB into sine of angle between them, sine A. So, half AC is 20. Okay, what is AB? 5 root 2R. And sine A. So, BC is 4 root 2R. This is 2R sine A. So, what is sine A? 4 so 2R, 2R, 2R. 2 is 10. So, delta is 200. Okay. So, this is S, sorry, so S by 20. S by 20 is nothing but 10. So, these are better problems. These are much better problems that we have gone through. Okay. So, moving ahead to our next problem. This is again a problem from probably 24 or 23, that in a parallelogram ABCD, a point P on segment AB is taken. in parallelogram ABCD, AP is to AB is 61 is to 2022. AP is to AB. So this is 61 lambda, say for example. PB would be 2022 minus 61, 1961 lambda. And the point Q1 segment AD is taken 61 by 2065. Okay, so 2065, 5 minus 1, 4, 6 minus 6, 0. Okay, this is the situation. AD such that if PQ, now we are drawing PQ. This is the line PQ intersects the diagonal AC at T. So we have to find AC by AT to the nearest integer. Okay. So in the section on geometry, lot of questions were done when you were given, suppose something like this, you draw a line parallel to the base, isn't it? So something like that we are going to do. You see, this is 2004, this is 1961. So if I draw a line parallel to PQ, I can draw either from B or from D. If I draw from this is 1960. Okay. If I draw from D, since this is 2004, if I draw a line parallel, it will meet outside this parallelogram. So what I am preferring is I am drawing it from B. Okay, and let it meet here at E, and this is say F. So let's see. I think you are able to gauge this fact that what this will yield is that this much part by the basic proportionality theorem is 1961 alpha, and this much part whatever is remaining 2004, and this is 1961, 35 alpha. No, 2004, 33 alpha. 2022 plus 33. 33 or 43. 2043. 43 alpha. Let us see what will be utilized. Okay. Now, by similarity, we will be proceeding now. Okay. So we have to find, what we have to find is AC by AT. So we can find AE and then AC. Okay. Fine now. Now, if you look at it properly, these two are definitely similar triangles, APQ and ABF. They are similar triangles. So we can find ratio of AT-AE. Okay. Okay. First and foremost, what we do is that this triangle and this triangle, these two triangles are similar. Okay. AEF, BEC. These two triangles are similar triangles. Okay. This angle, and this has to be equal. So
we can say opposite to this angle is AF and opposite to this angle is BC. And opposite to this angle is AE, is something that we are interested in, and opposite to this angle is opposite to this angle is EC. Now AF is 2002 alpha, okay, sorry 2022 alpha, and BC is 2065 alpha. So we get AE by AC, and now you can see we can find now AT by AE, and that we will be through. So AE upon EC, you can also see if you add 1 to both the sides, AE upon AE plus EC is nothing but AC, and this is AE upon EC. So we would like to have AE with us. So let us say EC upon AE, and then we add 1. So you get AC upon AE is 4087 upon 2022. Fine. I think we can say EC upon AE and then add to both the sides. See, I think the rationale behind this is that these two, again we will deal with two similar triangles and then we will conclude. So we have found AC is to AE. Now we can find from these two similar triangles, this one and this bigger one, ABF, two another similar triangles, because we have drawn this parallel to PQ itself. So we will be able to find AT by AE. So I think now we can very easily conclude that AT by AE by similarity would be 61 upon 2022. Okay, this is this triangle and this larger one, ABF, they are similar triangles. Now we have to find AT by AC or AC by AT. So it is basically nothing but 4087 upon 61. So the nearest integer, 61, we can say 408. So 6 is 36, 366, isn't it? So 408 and 366 to 427 is, in fact it is an integer in itself. The answer is 67. Okay, so no point discussing nearest integer, it is actually an integer. The answer is 67. Fine. So simple application of basic proportionality theorem and we are through. Similar triangles, you get basic proportionality theorem by similar triangles only. So that is why if you knew the proof, if we have done basic proportionality theorem at the very initiation, this is how we initiate. You draw a line parallel to the base to come to the conclusion that we are looking for. A beautiful problem, a question on geometry. Lot of questions that we have done did require a lot of notion of trigonometry. Okay, but here it is a pure geometry problem. So in that sense, it's a beautiful problem. Another question is in a trapezoid ABCD, the internal bisector of angle A intersects the base BC or its extension at point E. So you are drawing bisector of angle A. So, let this be A. Base is BC and the triangle in discussion is DAE. Okay, AB. So, let me say this is ABCD. Fine. Now, you are drawing bisector of angle A. These two angles are equal. Okay. This is the figure that we have drawn. It could be outside, but I think it is. But it will not. It is not going to change the overall scenario. So if this is theta, this is also theta. This is also theta. We have to find angle DAE. That is whatever angle you say, this angle or this angle. Now ABE. Okay. Inscribed in the triangle is a circle touching the side AB at M. Okay. AB at M and side BE at P. So you are drawing in circle to this triangle. This point is M and this is P. Further, AB is to MP is X. So if this is X, AB is 2X. Okay. If this is X, AB is 2X. Now we have to find this angle. Okay. So we have to find angle DA in degrees. See, if you are able to look at it very carefully, these two are equal, these two. This is equal to this, tangents from external points. Okay. Since these two are equal, this is basic proportionality theorem again, these two are going to be parallel. Okay. Okay, fine. I think you are able to gauge this. This is X. See, this is equal to this. So, base, this is the basic proportionality theorem. No, but why are these two equal? Yes. Lengths are equal. Sorry. My mistake. No. These two sides are equal. This is theta. These two sides are equal. So, since these two sides are equal, BE and AB are equal, these two are also going to be equal, so they are parallel. So, these two triangles are, this angle will also be theta, this angle will also be theta. Now, okay. Now, I think you can very easily make it out. Okay. What we have to say is that, fine, if this is y, this is y, this is y, this is y, this is 2x minus y, and this is 2x minus y. Now we can say x upon 2y. Okay, x upon 2y. Similarity we will use is 2x minus y upon, what is this whole length? 2x, isn't it? So this 2 gets cancelled. You have x square is 2xy minus y square. So x square x minus y whole square is 0. So x is equal to y. Okay. So all in all, what we are getting is that in this triangle ABE, let me draw it separately. ABE MP. So this is x, 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 x. Fine. So you can see that it is an equilateral triangle. I don't think so we need to extend it any further, okay? Because we know what these lengths are. This is S minus B. I hope you recall this is S minus B, this is S minus A, this is S minus. S minus A is S minus B is S minus C, so ABC are equal. So all the angles of this triangle are 60 degree. So theta is 60 degrees. Another problem on basic proportionality theorem. That is what I am saying, the basic things that we have gone through, they are ultimately the questions that are asked in examination. Okay, not see, if you see, rarely you come across questions which asks you Severs theorem, Menelaus theorem, at least in IOQM. Even though that we must know it, because as we move on to next stages, it will be necessary that we know them. But at this stage, look at the beautiful problem they have asked. This is really a very good problem. Another problem, see, let ABCD be a unit square. Suppose M and N are points on BC. Suppose M and N are points on BC and CD respectively, such that the perimeter of triangle MCN is 2. So let me draw this in a separate slide. This is a square A, B, C, D. M is on BC and N is on CD. M is on BC, N is on BC. Okay. So perimeter of this triangle, which triangle? MCN. MCN, that is what? MCN is 2. Fine. Let O be the circumcenter of triangle MAN. Okay, we have to draw triangle MAN also. Let it has circumcenter somewhere, say O. Is it called O? Let me. O be the circumcenter. And let P be the circumcenter of triangle MON. Angle MON. Somewhere, see here, maybe outside, I don't know. For convenience sake, let us assume this. Okay. All in all, it is going to be like this, I think. If this is theta, this is 2 theta, and this is 4 theta. Fine. OP upon OA whole square is something that we are asked for. OP
upon OA wholes. Now, sum of these two sides is 1 plus 1, 2. Perimeter is also 2. That means BM plus DN is MN. So, now let us say if we say this is X, this is Y. Okay, so this would be 1 minus X, 1 minus Y, and this would be X plus Y. OP upon OA. This is P. Okay. So, drawing two circles would make this a very cumbersome thing. So, let us not get involved into it. I have already mentioned the angle theta. So, what we have to do is that these are circumradius only, na? OA. So, let us say the triangles R2 by R1 whole square. Also, we can say MN is 2R1 sin theta, isn't it? And it is also 2 R2 sin 2 theta. So, R2 by R1 is sin theta upon sin 2 theta. So, this is 1 upon 4 cos square theta. So, all in all, this question has now reduced to determining this theta, in case we are able to do so. This is X, this is 1, this is 1. Now, we can also have a geometrical thought on this. Otherwise, if you look at it, we can go by brute force. This is root 1 plus x square. This is root 1 plus y square. Y and x are related by, see, this is a right angle triangle. So, x plus y whole square is 2xy is 2. So, it is x, so y is 1 minus x by 1 plus. So, this is one relation. So, one thing is to go by brute force, that this is root 1 plus x square. So, x plus y. Let us first go by a brute force method. Okay. Sorry. So, Mn is x plus y. So, it is x 1, this is Mn. An is root 1 plus y square. Y you already know in terms of x will, cos theta. I am assuming that we get it independent of x. Then only this question has any meaning. So, first we are doing it by brute force, then we will see a geometrical way to get into it probably. We will try to think. At the very first instance, we are doing it by simply brute force method. Let us put this, even though I think we should, okay, let us try once we have started now, we should not change the course in between. So, cos theta, let us write it next. Cos theta is AB square, sorry, AM square plus AN square, okay, AM square so AM square is 1 plus x square plus AN square is 1 plus y square. Okay. Okay. 1 plus y square minus Mn square. Mn square is x plus y whole square upon 2 so what do you get? X square y square gets cancelled. It is 1 minus xy, isn't it? 2 my upon now we will substitute y. What is y? 1 minus x by 1 plus x. This is okay. Root. So this is 1 plus x upon, see 1 plus x will get cancelled out and 1 plus x square, and this is again 1 plus x whole square plus 1 minus x whole square. So this is root so this is 1 plus x square it incidentally turns out to be independent of x. See, because this question had an answer, fixed answer, I was pretty sure that x will get cancelled out. Otherwise, if it turns out to be a function of x, then the question becomes meaningless. So, we were pretty sure that it will turn out to be independent of x. Insofar as the question is concerned, this is so 1 upon 4 cos square theta or simple 1 upon 4 cos square theta is 1 upon 4 into half. This is 1 upon 2. So, this is simply brute force method. Students preparing for Olympiad are not expected to, are generally, I would not say not expected, are expected to use some elegant geometrical way. I do presume and I still believe that there is a good geometrical way to deal with it. Okay. Let me tell you one of the ways. So, you are drawing this figure. Geometrical methods are very elegant when they work out. The benefit of having algebraic method is that they are very process oriented. But again, then the charm is lost. That cannot be denied. This is theta. This is alpha, this is beta. Okay, so one thing is that alpha plus beta plus theta is 90 degree. So, we already know the answer. We have to show that alpha plus beta is theta. Okay, so the alpha plus beta is theta. But again, even otherwise, what we do is that we rotate this triangle ABM by 90 degree. So B comes to point D, M shifts. Okay, see this triangle ABM, we just rotate it by 90 degree. So where do we land up? This gets horizontal, this gets vertical. So AB coincides with AD. M has now reached the point M dash, and this is alpha. This is root 1 plus x square, this is root 1 plus x square. This is y, this is x. Okay. So you can very easily see, what you can see? Triangle ANM dash and triangle AMN are congruent. You can see all their sides are equal. X plus y, x plus y. I think this is why the problem was asked, not the brute force method. That are you able to conceive, are you able to think around these lines? And now you can very easily see alpha plus beta is theta. Okay, so you have theta is 45 degree. Rest all is a trivial conclusion. Fine. If we are not able to come up with an elegant geometrical solution, then definitely properties of triangle, solution of triangle, trigonometric, or so to say algebraic methods are definitely advisable. But as a mathematics student, definitely this gives you more joy and gives you goosebumps than solving it by brute force method. Again, in the examination, we have to do better than others. So, we have to be pragmatic and take an appropriate call. Okay, it is not about appreciating the beauty of the problem, it is about solving the problem then. So, whatever method turns out you are able to think of first, that is the way you should proceed. Okay, because on occasions some laborious problems have been given, as we saw in R1, R2, R3. Okay, that we did by simply putting in values. No thought process was involved as such, and we used certain facts. Okay, so this concludes this session and the whole series of geometry. As we move on, we will probably come up with one more session where we will take more PYQs. Here we have taken some PYQs based on our assessment of the different sort of problems that you encounter. So, we saw problems that could be solved by purely geometry. We saw problems that were that involved only formulae. We also saw a problem where we involve bit of trigonometry and bit of geometry. But again, the substantial content is definitely pure geometry. Okay, and if we have a notion of trigonometry and if we are comfortable with the properties and solution of triangle, we have an extra edge that in case we are not able to think of a very elegant way of dealing with the situation, we are able to do it otherwise. So, I hope the whole series, the whole geometry series and the other series that you are continuously taking up is helping you in your preparation and is helping you gain confidence in so far as questions is concerned. And the simple aspect which I have said right from the very beginning to this last session is that knowing the basic notions and their proofs would go a long way in dealing with the problems that you are ultimately going to encounter in IOQM. This session, the depth of the coverage, especially the problem part, is limited to IOQM. You have seen that as we will move on, we will take up other sessions post IOQM, and probably before IOQM we may take up one another geometry session, lengthier geometry session where we will take more PYQs. Thank you very much for motivating us and encouraging us so that we keep on running this, and I am absolutely sure that you will keep on motivating us and your feedback would help us in coming up with better series now onwards. Thanks a lot.